Hello everyone. Welcome to the first lesson in College Calculus 1. Before we begin, we're going to be doing a review. But before we even begin that, I actually wanted to briefly talk about one thing I've noticed a lot of times when viewing people learning and or teaching things like college calculus or introduction to statistics, which is I want you to know that what we're doing is not easy. So if you feel like you're struggling with the material, know that you're not alone. Right? It seems easy when somebody with years of experience is teaching it and everything makes sense when you're following along, but then you go to do it yourself and suddenly things don't work out. This is not unusual. In fact, most people struggle when the topic is new to them. For example, I actually struggled with college calculus whenever I was an undergrad. But then over time, using it, doing things like physics classes, beginning to teach, things like that, it's all become secondhand to me. So I actually tend to teach it where I'm going to be doing very specific steps every single time. Whereas once you feel like you have a good enough understanding, you might just skip a lot of these steps. Most people do. But I wanted you to be aware that the reason you're going to see me a lot of times say what rule we're using for every step, it's because I want this to be accessible to anyone as they're on their learning journey, and know that, again, just because something has clicked with you, someone else may still find it difficult. And I really want to have these building blocks set up so that somebody could follow along and hopefully it'll start to sink in and make sense to them. So now let's look at our review. We're going to first start by looking at some things we're going to be using a lot in calculus, that we're going to be looking at a few things just so that everybody's on the same page. This may be relatively new to you, it may just be a quick refresher, or this might be something that you really are fine with and you don't really need to follow along with and you can jump straight to the chapter 2 material. So first let's talk about functions. So a function f is a rule that assigns each element x to a set D, and exactly one element, f of x, in a set E. The set D is called the domain of the function. So this would be, for example, what are the values that when you plug x in, what outcome do you get? What are the possibilities? So this would lead to your possible values, which would be your domain. The number f of x is the value of f at that x. So for example, if you ever see f of x, what this is saying is that you're taking this x value and you're transposing it onto some new set of values, right? So you have some x, and it's saying, what is this value once the function has acted upon it? The range of f is the set of all possible values of this f of x. So where the domain is all of the possible values that your x can be, right? So it might be something like, this can be any value from 3 to 7, where 3 is not included and 7 is. Your range is going to be, once this function has acted on this x, what are the possible values you can get? For example, maybe something like every value from negative infinity up to positive infinity. The domain of f is either given, or it's usually going to be all real numbers, which we write like this. It's a double line R, for which f of x is defined. So that is to say, usually we're going to have something like this. X is going to be all real numbers. Or you might have some restriction based on specific values we cannot put. For example, if my function f of x was equal to 1 over x, this would mean that x can be anything except 0 because we can't divide by 0. In this case, you would have a different domain for this function because I can input any positive or negative value except 0. So how do we represent functions? Well, there's 4 main ways we can do it. The first is verbally. That is the description in words of what the function is doing. For example, it doubles whatever is input. This would be a function where you take whatever input, let's say it's 4, and you double it. You can do it numerically, which is to say you'll have a table of values. You could do it visually using a graph, or you can do it algebraically, which is where we're going to have some explicit formula, which of course this is what we're going to be using mostly in this course. So now let's talk about some of the notation we're going to be using in order to define our intervals that we talked about earlier with things like domain, range, things like that. So for example, you're going to have less than or greater than. And in interval notation, these would be represented by either an open parentheses, which means that it's at that value and above, but not including that value. Or you could have an open parentheses at the end, which represents that it is less than that value. It's up to that value, but not including it. You could also have less than or equal to, which we represent as a square bracket, which means that it is every value bigger than this value, including this value. And we have greater than or equal to, which is a closed square bracket, which means everything up to that value, including it. So examples of this might be something like from -3 up to +4. So this means that it would be all the possible values from -3, so -3, -2, -1, 0, 1, 2, 3, 4. And it's every value from -3 up to 4, but not including either of those values. So the way we would show this is whenever you have this open parentheses, when you're actually showing it on an interval, you would use an open circle. This represents that it goes up to that number, but does not include it. Whereas in the square brackets, might be something like, I'm going to make it a little bit smaller in this one. Let's say that we had -1 to +2. So similarly, if I have an interval representing this, I would have -1, 0, 1, 2. And I show this by putting a closed circle. And this just means that it's every value from -1 up to +2, where -1 is included and +2 is included. So what about if we have something that is a little bit of both? Well, you can actually mix and match these. For example, you could have something like -2 up to +1. And in this case, it's everything above -2, not including it. So -2, -1, 0, 1. So we'd put an open circle. Up to 1, which is included, so we put a closed circle. Now, you may not always have both an opening and closing depending on what the specific interval is. For example, right now we looked at two values that's greater than this and less than this, or greater than or equal to this and less than or equal to this, or greater than this but less than or equal to this. But what about if we had something like x is less than 3? So in this case, if we were to draw it out, let's say we have 0, 1, 2, 3. Well, because this is not equal to, it means that it's everything that is less than 3, but not including it, so it's an open circle. And then I'm just going to go all the way off. And if I wanted to turn this into interval notation, I would have to consider, well, if it's going off in the negative direction and it just keeps going, there's no end point to it, this means that it goes to -infinity. Now, anytime you have infinity or negative infinity, you will always use parentheses because there is no end point to it, right? We're not getting to infinity or negative infinity. We're approaching going in that direction forever and ever and ever. So that it's from negative infinity up to 3. If we had something like x is greater than or equal to -2, it'd be the same idea. We have that this is -2, -1, 0, 1, 2, and it's everything greater than, but also including -2 to the right. So if I wanted to write this as interval notation, this would be square bracket -2, because this is my starting point, and then I'm going off to infinity, which again will always be parentheses. And then last, let's look at one more example where we have -6 is less than or equal to x is less than 5. So if I were to draw this interval, I'm just going to kind of skip all the numbers in between, but let's say this is -6, this is 5. Because this is greater than or equal to, this -6 is included. Because it's less than 5, this 5 is not included. So I would have a closed circle on -6, I would have an open circle on 5. And then writing this in interval notation would be, because the -6 is included, it'd be square bracket -6 up to 5 parentheses. Next, we're going to talk about another type of function you might encounter, which is called a piecewise function. So a piecewise defined function is defined by different formulas for different parts of our domain. That is, our different x values. So let's say, for example, you had the absolute value of x. Now, absolute value just takes any value and it makes it positive, meaning that we're going to actually look at two different parts of this. We're going to look at when x is positive, and we're going to look at when x is negative. And pretty much what this is saying is if x is greater than or equal to 0, we just put x, right? So if I say 3, which is greater than or equal to 0, I get out 3. If I plug in 0, well, because this is greater than or equal to 0, I just get out 0. Now we need to look at what happens if x is less than 0. Well, what this is saying is that if x is a value that's less than 0, I need to take whatever that x value is, and I need to take the negative of it, meaning that, if, for example, if I had negative 3, so negative 3 is less than 0, I plug this in, negative 3. So whenever you have a negative and you take the negative of it, you get positive 3. So you can see that this is actually a piecewise function. We have to consider what happens at each part. So now let's look at what it would look like if we graphed this. Well, if we graphed this, right, we have our axes. And when x is greater than or equal to 0, meaning starting here, if I plug in 0, I get 0 out. And what's happening is as it goes up by 1 in the x direction, it goes up by 1 in the y direction. So it's going to look like this. Oops. Now, what happens with my negative values? Well, as my x goes into the negative domain, my y values will be the positive equivalent. So this is what our absolute value would look like, both as a piecewise function, right? So if we have an x that's greater than or equal to 0, we leave it. If we have x that's less than 0, we change it to a positive. And then this is what the graph would look like, no matter what value I plug in. If I plug in a 1, I get out a 1. If I plug in a negative 1, I also get a 1. Because what's happening is it's taking any of these values, which if we weren't inverting it, it would look like this. Whereas x went to the negative, y would also be negative. What we're doing is we're saying, okay, take that value and make it positive. Next, we're going to look at function symmetry. So if you have a function that this is true for all values of x, where f of x, so any value x I plug in, would be equal to the same function with any values I plug in for negative x, this is considered an even function. So if every x I plug in the domain, this is true, this is called an even function. So an example of this might be something like f of x equals x squared. So if I plug in negative 1, I get out negative 1 squared is positive 1. If I plug in positive 1, 1 squared is positive 1. If I plug in negative 2 squared, right? So I'm squaring a negative, so it's negative 2 times negative 2 gives me 4. If I plug in f of 2, I get 4. If I plug in f of negative 3, this would be 9. If I plug in f of 3, this would be equal to 9. So this is called an even function because anything that happens on the negative values in this case would also occur for the positive values. They're going to be equivalent. So this is an even function. So this means that it has symmetry. Kind of like when we were doing the absolute value, right? If I plugged in 1, I got 1. If I plugged in negative 1, I got 1. If I plugged in 4, I got 4. If I plugged in negative 4, I got 4. So they end up with the same values, so they're equal to each other. So these are even functions. Odd functions, on the other hand, are whenever, if I plug in some negative value of x into my function, this would be equivalent to plugging in positive value into that function, but it would be the inverse of it. It would be opposite of it. So for example, if I plug in f of negative 1, this would be the same thing as taking f of positive 1 and then just taking the negative of that. So an example of this would be the function f of x equals x cubed. So let's say, look at it. If I plug in 2, I get 2 cubed, which is 2, 4, 8. So I get 8. If I plug in f of negative 2, this would be equal to -2 times -2, which gives me +4, times -2 gives me -8. So it's the same value I got when I plugged in positive, but the negative. Same thing if I plug in f of 3. This would be 3 times 3 is 9, times 3 is 27. If I plug in f of -3, this becomes -3 times -3 is +9, times -3 gives me -27. So you'll see that these values are equivalent, except for it is with the negative in front of it. So whatever you get for the positive, you get the negative of that same value. So you get the same magnitude, but the positive is one direction, positive or negative, and then the negative would be the opposite. So when looking at these, if you wanted to think of it graphically, your even functions are functions that are symmetric about the y-axis. That is to say, whatever is happening on one side, let's say you have something like this, would be symmetric across the y-axis, meaning that you could almost think of it like they're a mirror image. Whatever's happening on the positive is also happening on the negative. If we were looking at the odd functions, these will be symmetric about the origin. That is to say, if I have a value that goes like this, then it's sort of like I'm flipping it over the origin. It would look like this. If I had a value that was going over here, it would go down here. If I have a value that's, let's say it's growing this way instead, something like a logarithmic function. Well, in this case, if I had an odd function, it would look something like this. So it's symmetric about the origin, which is to say, right here. You could think of them as mirror images across this. Or you could think of it like rotating it 180 degrees, right? So if I have something like this, where it's going like that, by rotating it 180 degrees, it's doing the same thing, but on the opposite end. A function is called increasing on an interval if I plug in some value x1, if it is less than plugging in x2 into that same function. So this would be an increasing function if this is true on some interval. So what this pretty much means is that if I had something like this, if I plug in x1, let's say I have a value here, if I plug in x2, because it is greater than whatever output I get, it would be greater than. It could be anything here, then this would be an increasing function. A decreasing function would be when I have that f of x1 is greater than f of x2. Now notice in this, both of these, I have f of x1 is less than f of x2, and for decreasing, I have f of x1 is greater than. Notice that there's no equality in this. Now there is actually a term for things like that, which would be non-decreasing or non-increasing function, which means that basically if it were non-increasing, it would mean that it can go down or it can stay the same. If it were non-decreasing, it would mean that it could go up or it could stay the same. So it's increasing if this is strictly true, that if I plug in one x value, as I move my x value higher, my function would also have an output that is higher. A decreasing function would be as my x value increases, my y value that I get would decrease. A non-increasing function would mean that it can go down or not change, and a non-decreasing function would mean that it could go up or not change. So in that case, you might have something like this, where maybe you have an x here, it can go up, it can go up, it can stay the same, but in the end, it cannot decrease. Next, I want to talk about the difference quotient. Now, this one is actually pretty important because we're going to use it a lot in this course. But the difference quotient is that you have f of x plus h minus f of x divided by h. And what this means is if I have some function, let's say that I have my xy axis here, and I don't know, let's say this is what my function looks like, something like this. What the difference quotient is saying, that if I have some value x, this is my outcome from my function, whatever the line tells me, right? So if I were to come over here, I would get some value. And then I have some new value, which has a difference of h. So we'll call this one x1 and this one x2. So what we're looking at when we look at the difference quotient is what is this value here? And we're saying, okay, if I take the outcome at f of x and the outcome at f of x plus h, what is the difference between those two, which means what is the difference of your actual output. So this would be f of x plus h minus f of x. And then we want to divide by the distance that we've traveled. So basically we're looking at how far is our distance between x1 and x2. And really all this is telling us is it's just giving us our slope and the difference formula, right? If you think about if you wanted something like, the distance between 2 points, x1, y1, and x2, y2, what would we do? We would take the change in y divided by the change in x. That's all this is. In this case, it would be y2 minus y1 over x2 minus x1. Well, in this case, h is the difference between x2 and x1. The top, the y values, are the difference between whatever outcome you get, which we'll call y2, minus y1. So it's really just taking the difference for each of these data points, and then from there, we can figure out what the slope is between them. Something like that. Let's do some examples to test out what we've looked at so far. So let's say that we have the function f of x equals the square root of x plus 5. And we want to know what is the domain of each of these functions. So if you remember, the domain are what values that can x take, where I would get some output. So because this is under a square root, we know that this term has to be greater than or equal to 0, right? I can have the square root of 0, which would give me 0, and I can have the square root of any positive value, but I can't have a negative. So pretty much what we have is that this x plus 5 must be greater than or equal to 0. So then what I'm going to do is I'm going to subtract 5 from both sides, and I would get that x is greater than or equal to negative 5. So what does this mean? It means that I could plug in negative 5, and I would get negative 5 plus 5 is 0, square root of 0, good to go. I could plug in a value that's greater than negative 5. So if I plugged in negative 4 plus 5 would give me positive 1. Square root of 1 is 1. Let's say, for example, I plugged in negative 3. Negative 3 plus 5 would give me positive 2. Square root of that would give me square root of 2. So this means that I can plug in any x value starting at negative 5, including negative 5, and up. So writing this as an interval would be square bracket negative 5 up to infinity, because I can plug in any value that's larger than or equal to negative 5. The next example is, what if we have the function g of x, which is equal to 1 over x cubed minus 9. Now, whenever you're doing the domain of a function, generally what you're looking for is not what values you can plug in for x, but what values you cannot plug in for x. Now, based on this, is there anything that I can't have? Well, I cannot have a 0 in the bottom. So pretty much what we're saying in this case is that I cannot have x cubed minus 9. Oh, sorry. This should be a square. X squared minus 9 cannot be equal to 0. Well, then what would make that equal to 0? So let's find out. So we go x squared minus 9 equals 0. So then I just add 9 to both sides, and I get x squared equals 9, which means that I cannot plug in. So what would make this true? It would be that if x is equal to 3, or if x is equal to negative 3. Meaning if I plugged in 3, 3 squared is 3 times 3 is 9. If I plug in negative 3 times negative 3 gives me positive 9. So these are the two values that x cannot be. X cannot be equal to negative 3, and x cannot be equal to positive 3. So these cannot be true. So then if I were to write my interval, this is going to end up, first of all, looking like this, where I have every value except negative and positive 3. So I'd put a circle over each of these, but otherwise everything else is shaded in. And if I wanted to write this in interval notation, this would be every value from negative infinity up to negative 3, but not including negative 3. And then I would use a union to connect the next part of the interval, which would be starting at negative 3, but not including it, up to positive 3, but not including it, And then last, union positive 3 up to infinity. And this would be the interval for all of the values that I could plug in for x in this function, which would be pretty much anything other than negative 3 and positive 3. Now, what about this function? We have h of x, some function h of x, which is equal to 3x plus 5. So as I said before, we first want to look at, is there anything that we can't plug in that would cause it to have some sort of issue? Well, in this case, no. We can plug in anything. So this means that it's all real values. So if we were to draw this out on our number line, it would be everything. Or to write it in interval notation, we would have every value from negative infinity up to positive infinity is fair game for this function. And in one last example on domains, let's say that we have y is equal to the natural log of x plus 2. So as before, we have to consider what values a natural log can take. So a natural log can be any value that is greater than 0. Because if you were to graph out a natural log, it looks kind of like this. Meaning that it will approach 0, but it will never touch it. Meaning that whatever is in here can go approaching 0, but it can never be 0. So we'll have x plus 2 must be greater than 0. So again, we're just going to figure out what value makes this true. By subtracting 2 from both sides, we have that x must be greater than negative 2. So if we were to draw this number line out, if we have negative 2 here, it is not included because it's greater than, not greater than or equal to, and it's everything to the right of negative 2. Next, we're going to do an example looking at using the difference quotient. So let's say that we have the function f of x is equal to 9x minus 5. So if in this case, we have our f of x. Now, if you remember, our difference quotient was f of x plus h minus f of x divided by h. So in this case, we already have f of x. We need to figure out what f of x plus h is. Now, the way you do this is whatever is inside the function, you just replace with x. So in this case, it would be 9 times x plus h minus 5. And then we're going to distribute our 9. This is going to be equal to 9x plus 9h minus 5. So this is our f of x plus h. This is our f of x. Now let's plug them into our difference quotient. So this is going to be equal to 9x plus 9h minus 5 minus f of x. So we're taking the negative of this. So this is going to be minus 9x plus 5. Now, this is all divided by h, and we're going to do some cancellation. So minus 9x is going to cancel with positive 9x. Minus 5 is going to cancel with positive 5, and we're going to be left with 9h divided by h. The h's will cancel, and we'll be left with 9. So the difference between f of x when it's 9x minus 5 and f of x plus h, again for the function 9x plus 5, would end up being a difference of 9. For the next example, we're going to look at this function here, f of x equals x over 4, but we're going to look at it specifically at the point 2. So we're going to say when x is equal to 2. So in this case, we're going to plug in 2 for this, it would be 2 over 4. And then if we were to find our f of x plus h, this would just be, again, we plug in x plus h wherever there's an x. So this would be x plus h divided by 4. And then again, because we're doing it at x equals 2, we're going to replace 2. So this would be 2 over 4. And this one would end up being 2 plus h over 4. So we're doing this at f of 2 and f of 2 plus h. So now if we were to do this into our difference quotient, f of x plus h, we had that this is equal to 2 plus h over 4 minus f of x, which we just said is 2 over 4, and then we divide the whole thing by h. Now, because these are fractions in the top here, and we're adding or subtracting them, this means that they have to have the same denominator. Well, they do. It's 2 plus h over 4 and 2 over 4. So in this case, it becomes 2 plus h minus 2 over 4 divided by h. So now what happens, we have 2 and minus 2, so these are going to cancel. So we have h divided by 4 divided by h. So the next thing we're going to do is we're going to consider that this h is kind of the same thing as h over 1. So we have a fraction divided by a fraction. So when we're doing fractional division, what we do is we multiply by the reciprocal. So we take this value here, and it kind of does this. This h comes to here, this 1 comes to here. So this becomes h times 1 is just h divided by 4h. So then we cancel those. We're left with 1 over 4. So what's happening is that when we have this f of x, which was x over 4, at point 2, if we go up by some amount h, we will go up by amount of 1/4. So whatever value we plug in as h, it will be 1/4. So if h is 1, we go up by 1/4. If h equals 2, then we go up by 2/4, and so on. For our last difference quotient example, we're going to be looking at the function f of x equals x squared plus 3. So again, looking at our difference quotient, we have f of x plus h minus f of x. We have f of x, so we need to figure out what is f of x plus h. So we do f of x plus h. Anywhere we have an x, we plug in x plus h. So this becomes x plus h squared plus 3. Now we have x plus h squared, so what we're going to have to do is we're going to have to FOIL this out, which is first, outer, inner, and then last. Or you could think of it like this, right? If we have x plus h times x plus h, we're going to multiply the first terms, then we're going to do the outer terms, then we're going to do the inner terms, then we're going to do the last terms. That's what FOIL means. So this ends up becoming equal to x squared, x times x is x squared, so outer x times h, so plus xh, inner x plus h, and then last, h times h is h squared. So then this means that our f of x plus h is x squared plus, in this case, 2xh plus h squared, and then of course we have to include that plus 3 that we had there. So now we're going to plug these in to our difference quotient. So what we have is f of x plus h, we said was x squared plus 2xh plus h squared plus 3 minus our f of x. So minus x squared minus 3. And this is all divided by h. So next thing we're going to do, we're going to look see if there's any cancellation. Well, we have positive x squared, we have negative x squared. We have positive 3, we have negative 3. This leaves us with 2xh plus h squared over h. So now what we're going to do is the fact that both of these terms have an h in them, we're going to pull an h out. So this is going to be h times 2x plus h, and this is all still divided by h. These h's will cancel, and we'll be left with 2x plus h, which means that our difference between our x values is going to be 2 times whatever value we plug in for x plus our difference, our h here. So now what we're going to do is we're going to look at some of our essential functions that we're going to be using when we're doing calculus. So the first is when we have what is called a linear function. So a linear function is just any graph that is linear, or a line, that is not a vertical line. So the most common forms you're going to see are going to be the slope-intercept form, which is just going to be y equals mx plus b, where m is the slope of the line, that's how much it's increasing, and b is our y-intercept. So if we were to kind of graph it like this, b would be where it's going to cross here, and then slope would determine how much is it increasing, right? Is it increasing by some amount? Is it increasing by more? Is it increasing by less? So this slope, you can think of, we usually call it rise over run, and this will tell you what the slope is. So whenever x value I plug in, it would be starting at that starting point b, x times m would tell us where we end up to get all of our different y values. When we have more than one point, we may actually want to use what's called the point slope formula. So the point slope formula is just that we have y minus y1 equals m times x minus x1. In fact, we're going to be using this one a lot in this course. So basically what it's saying is that if I have some point x1, y1, and I know what the slope is because we're going to find that using derivatives, I can plug in x1 and y1 into this, and I can figure out what is the equation that represents this line that is the tangent at a specific point. And this will all make sense when we get to that when we're doing derivatives and stuff like that. The next kind of function we want to look at is called a polynomial function. So a polynomial function is just going to have the form, p for polynomial, is going to be an to the x to the n power plus a n minus 1 x to the n minus 1 power. And then we would do this going on and on, right? So this would become a n minus 2 x to the n minus 2. And we do this until we get down to, so plus a1 x to the 1 plus a 0. And what this means is basically a higher order function where if we were looking at our basic function, right, this would be if you have a single x, right, an x to the first power, so just in terms of x. This would be when you don't have x. This would be something like y equals 4. This would be y equals 2x plus 4. Then of course we have, what about square functions? You have, y equals 3x squared minus 2x plus 4, things like that. And pretty much a polynomial function can have up to n number of powers. This is just different powers. The numbers an through a1 are coefficients. So this would be the coefficient for your x values. This would be your coefficient for your x to the n values, or your nth power values. And n is the degree of the polynomial. So for example, if I have a cubic function, that means that I have terms in terms of x to the x cubed. This would mean that my n is equal to 3, because I would have some a3 x cubed plus a2 x squared plus a1 x1 plus a0. Which you can think of your a0 as your intercept, like when we were doing our linear function. Then there's your power functions. So a polynomial of the form f of x equals x to the p power is called a power function. That means it's being raised to some power p in this case. So it'd be like this polynomial function, except for all you have is whatever the highest power is. So if I had x cubed, then this would be a power function. It's a cubic function, right? It's cubing whatever value I put in. If I have p equals 1 over n, then this is called a root function. So what this means is I have f of x is equal to x to the 1 over n. This is the same thing as saying it is the nth root of x. This is something that's actually going to be used a lot in this course, because a lot of times we're going to have to deal with multiplying, adding, subtracting powers, things like that. And it's easier a lot of times to think of it in terms of its power function versus thinking of it in terms of a root. And then similarly, if we have f of x equals x to the negative 1, the way that this works is it ends up being equal to, sorry, this should be n, 1 over x to the n. So anytime you have a negative power, this is the same thing as doing 1 over x to the positive power. And again, these are all things we're going to use quite a bit. For example, if I had something like 1 over x to the 1/3, then this is actually equivalent to saying that I have 1 over the cube root of x. So this might be the form that you originally have whenever you're doing calculation. You can convert this to 1 over x to the 1/3, which then you can further convert this to x to the negative 1 over 3. And this makes it a lot easier to deal with certain things. For example, when we're learning about the power rule, this makes the derivative super easy. Can't really apply it on this one very well, but in this form, it actually becomes very easy to do. Next, we have rational functions. So a rational function is just a ratio of two polynomials. So that is, say, something like f of x is equal to px over qx, where in this case, qx cannot be equal to 0, because in that case you would have 0 in the denominator of a fraction and doesn't really work out. We have our trigonometric functions, which would be things like sine, cosine, tangent, secant, cosecant, cotangent. And of course, we're not going to go deep into detail on those. We will use some when we're doing the course. But if you wanted to find out more, I would either look at a trigonometry course or book, or actually even some calculus books will actually have the trigonometric functions in the appendices. Next, we have exponential functions. So exponential functions are of the form, this is a rational function. And then we have exponential functions, which is just going to be of the form f of x is equal to b to the x, where b is going to be your base, and b is positive for an exponential function. So basically, this would be your base, and you're now taking it to some x power. So notice, usually we have x to a power. An exponential function is some value to some x value. Now, the reason that we're saying that x would need to be positive is because, remember, unless you're restricting this x, so for example, you could have x be, b be something different depending on if you have a very local interval. But what would happen if, for example, my b was equal to -2? And then my x, what happens if I put x to the -1? Well, this becomes, x to the 1/2. So if x is equal to the 1/2, then this would be -2 to the 1/2. Well, 1/2, if you remember from what we were just talking about, would be the same thing as saying this is the square root of -2. In which case, now we're dealing with complex numbers. So for most functions, then this would mean that this doesn't really work, which is why our b would need to be positive. Now here I put greater than or equal to. Now you might see actually a problem with this as well, right? And this is why you should always think about what it is that each of these things would represent. Because what if, again, b was equal to 0, and I had x is equal to -1. So then this would be 0 to the -1 power, which is the same thing as saying 1 over 0 to the 1 power. Well, 0 to the 1 power still would be 0. This really doesn't work. So really, this is actually just b is greater than, which is why specifically I said that it's positive, not greater than or equal to 0 or positive or equal to 0. So I actually did that on purpose. I just wanted to kind of show you kind of the thought process of when I make some random statement like that, b has to be a positive value. There is a reason for it. And if you kind of break down, okay, what would happen if I plug in a negative? What would happen if I plug in a 0? Then you can get a much better understanding of why these things would need to be true. Next, we have our logarithmic functions, which would be of the form f of x is equal to log bx, where again, b is our base, and it must be positive, greater than 0. Now that we've learned a little bit about functions, we're going to look specifically at translations of those functions. So let's say that you have some function f of x. What would happen if you were to add some constant to it? Well, in this case, what it's going to do is it's going to take whatever function you have and it's going to raise it up by c amount. For example, let's say that we have f of x plus 4. Well, remember, whenever you have f of x, you're going to be getting some outcome, right? So if I plug in a value and I get out 3, well, f of x would be 3. So let's say I plug in some x here and I get 3. Well, then this is telling it, okay, take that and raise it up another 4. And that's exactly what this would do. It would transition it up. If you have f of x minus c, this would take whatever function you have and it would shift it downward. Next, if we have inside of our function, so if we have f of x plus c within the function, this is actually going to cause us to move to the left. And this is because what we're doing is we're saying, okay, whatever value we had here, let's say this is equal to 4. If we had f of x is equal to 4, now f of x plus c is equal to 4 would mean that we are shifting the whole thing over to accommodate for that, right? So let's say that my original function was something like this. And if I wanted to say, okay, but I want x plus c to be also equal to 4, for this to be true, I would have to shift the entire thing by shifting it over to the left to make this true. Similarly, if I have x minus c, this is going to shift it to the right. Let's test this out to show this. Let's say that my f of x is just equal to x squared plus 2, right? Well, what would happen if I were to add c within this? Well, we'd have f of x plus c is equal to, now what happens? I take whatever's within the parentheses and I replace x with it. So this becomes x plus c squared plus 2. Of course, I'm going to FOIL this out. Just like before, this is going to end up giving me x squared plus 2xc plus c squared plus 2. Now again, if I had this equal to some value, what's going to happen is this is going to have to shift in order to account for this. So now let's test it out in action. Let's say that x is equal to 2. So this would end up being 2 squared is 4. 4 plus 2 equals 6. Well, this is going to be 2 squared is 4 plus 2 times, this would be 2 times 2c, so plus 2c plus c squared plus 2. So this would end up being 6 plus 2c plus c squared. Now, if I plug in, let's just make it 1 for c, this would end up being 6 plus 2 times 1 plus 1 equals 9. So what's happened? We've actually shifted to having a higher y value. So if I wanted to keep it equivalent, then what happened is the whole thing has to shift to the left, because now what's happening is that I have actually raised it so that it would need to be at the same sort of value, x equals 2. It would have to be shifted to the left to now be equal to the outcome of y that I had here, which was, in this case, 9, and this one was 6. This is not drawn to scale. Now let's talk about reflections of our function. If we have y equals, which y is just a way of saying a function, is negative f of x, this is going to reflect over the x-axis. Basically, whatever it's saying is whatever value I would have gotten that was positive, now I'm taking the negative of it, so I would get the negative. So if I had a value here and a value here, it would look like this. So instead of being like this, it now is going to be like this. I'm reflecting it across the x-axis. If I had y equals f of negative x, this is going to reflect over the y-axis, right? So this means that if I had some value here, this would be equivalent to flipping it over the y-axis. Again, this would be something like, if I just had, let's say f of x is just equal to x. So if I have f of x equals x, and I'm plugging in 4, so this would be equal to 4. So f of 4 equals 4. If I were to take the negative of that, so negative f of x, negative 4. So instead of it being equal to 4, it's now equal to negative 4. Vertical and horizontal stretching will move a graph so that it's closer to one of our axes. So for example, if we have y equals c times f of x, what this is going to do is this is going to vertically stretch, meaning it's going to stretch it in this direction. So if our original graph was something like this, what it's going to do is going to stretch it this way, meaning that it will be closer to our vertical axis. If we had y equals 1 over c times our function f of x, this is going to be kind of compressing it down, and it's going to cause vertical compression, meaning it's going to go further from our y-axis, because it's going to take the same function and it's going to compress it down, right? So this would be 1 over c f of x. This is f of x. This was f of x, and this was c times f of x. What about if we have something within the function? So if we have y equals f of something multiplied by every x value, there's going to be horizontal compression, meaning that if I have my x and y axes, if I have some f of x, what's happening is it's taking this and it's compressing it in, meaning that it's going to be further from the horizontal axis. Similarly, if I have y equals f of 1 over cx, this is going to be horizontal stretching, which means that it would be something like this. If this is my f of x, just like this was f of x, this was f of cx, this is going to take this function and it's going to horizontally stretch it, meaning that it is going to be closer to the horizontal axis. You can actually combine functions together. So these combinations of functions are where we have two functions, f and g, and these can be composed into a new function. So this composite function, which is denoted as f of g of x, is really just you're taking the function of the function g of x. So you're taking g of x and then you're putting that into your f of x to get some new composite function, or think of it like a multi-step function. It's a function made up of two functions. So let's do a quick example on this. Let's say that we had f of x equals x squared plus 1, and g of x is equal to 2x plus 5. So if we're looking at f of g of x, then what this is going to be is we're going to take our g of x and we're going to plug in whatever g of x is wherever we have an x. So this is going to be equal to 2x plus 5 squared plus 1. And then, of course, just like before, we're going to FOIL this out. So we're going to multiply the first terms. This is going to be 4x squared. We're going to do the outer and then the inner terms, which is going to be 2x times 5, which is going to be 10x. There's going to be two of them, so there's going to be 20x. And then last terms, plus 25, and then, of course, plus 1. So this is just going to become 26. So this is going to be 4x squared plus 20x plus 26. And then if I wanted to, I could possibly simplify the fact that every single one of these has a 2. I could pull that 2 out and then make it a simpler function, depending on whatever I have on the other side of the equation. What about if we went the other direction? What if instead of f of g of x, we did g of f of x? Which, remember, is just the same thing in this case of g of f of x. So whatever we have as f of x, we're going to plug that into g of x. So we're going to take x squared plus 1 and we're going to plug it in here. So we have 2 times x squared plus 1 plus 5. And then this is going to be, I'm going to distribute the 2. So this is going to be 2x squared plus 2 plus 5, which would be 2x squared plus 7. In this example, we have table data for our x values when x equal to 1, 2, 3, 4, and 5. We have our function f of x when x equal to 1, our f of x is equal to 5. When x is equal to 2, f of x equal to 2. 3, 2, 4, 1, 5, 4. G of x is when x is equal to 1, g of x gives us 2. When x is equal to 2, g of x gives us 3. So now what we want to do is we want to see how does a composite function work when you have the outcomes of each of our functions. So in this case, let's say that we had f of g of 1. So what we're saying is this. We're basically saying f of g of 1. So g of 1 is what is g of x when x equals 1? Well, in this case, it's equal to 2. So this becomes f of 2. And f of 2 would be equal to 2. Right? Because it's what is it when x is equal to 2, f of 2 would give us 2. What about when we have g of f of 5? So again, this is g of f of 5. Well, when x is equal to 5, my f of x is equal to 4. So this would be g of 4. When x is equal to 4, my g of x would be equal to 5. What about if we had f of g of 2? So again, when x is equal to 2, g of x will be equal to 3. So this would be f of 3. And then when x is equal to 3, f of x would be equal to 2. And then last one, what about if we have g of f of 4? So f of 4, so when x is equal to 4, f of x is equal to 1, so g of 1. And this would be equal to, when x is equal to 1, you get 2. Next, we're going to talk about exponents, which we're going to be using a lot in this course. So let's say that we have a and b, and they are positive. And x and y are real numbers. So x and y are part of the real number set. The first rule that we have is going to be that if we have b to the x times b to the y, this is going to be equal to b to the x plus y. Our second rule that we're going to need to know is that if we have some constant a times some constant b, and this is to the x power, this is going to be the same thing as a to the x times b to the x. Our third rule is going to be that if we have b to the x over b to the y, this is going to be equal to b to the x minus y. Our fourth rule is going to be that if we have some constant a divided by some constant b, and this is taken to the x power, this is the same thing as saying a to the x over b to the x. Our fifth rule is that if we have b to the x power taken to the y power, this is equal to b to the x times y power. Our sixth rule is going to be that if we have any constant to the 0 power other than 0, this is going to be equal to 1. Our seventh rule is going to be that if we have a to the minus x, this is going to be the same thing as 1 over a to the x. So a negative power will make it 1 over the constant to that power. And our eighth rule is going to be that if we have a to the x over y, this is going to be the same thing as taking a to the x power and taking the yth root of that a to the x power. These are all really important rules that we're going to be using a lot, because a lot of times when you're doing calculus, the part students struggle with most is the algebra. It's you get it into some form, but then what can I do with it in order to cancel things out, simplify, things like that. While talking about exponents, I also wanted to bring up Euler's number, which is represented by e. And this is a number that is roughly equivalent to 2.71828, so on and so forth. It's an irrational number that goes on changing forever. The function f of x equals e to the x is a natural exponent. And the nice thing about this is it actually has some really nice properties when we're doing derivatives. Another thing is that the Euler's number e is special because the slope of the tangent line at f of x equals e to the x at 0, 1, it has a slope of 1. Next, what I want to do is I want to cover some definitions that we're going to be using and are often going to come up in a lot of math classes, but particularly in calculus. And the first is a one-to-one function. So a one-to-one function, which you may also see it as 1-1. And what a one-to-one function is it's a function that can never take the same value twice. That is to say that if I have some function and I have the value x1, it will never be the function at x2 where x1 does not equal to x2. So what this means that if I plug in some number into my function and I plug a different number in, meaning that they're not equal to each other, it will always be a different number. So an example of this might be something like if we were looking at a natural log or something like this, where it'll never be the same number twice. No matter what x value I plug in, I will always get a different outcome from my function. One of the nice properties of a one-to-one function is that it passes both the horizontal and the vertical line test. So some of you all may have seen the vertical line test to test whether something is a function, where if you were to cut it in any place with a vertical line, it doesn't cross through the function more than once. But also, if it's one-to-one, it also will pass the horizontal line test, meaning that if I were to cut this with horizontal lines, it would not pass through the function more than once. This can be especially useful when we're looking at our next thing, which is inverse functions. So an inverse function is that when you have your domain of a function, x, and your range of that function, y, the inverse of it will have a domain of y and a range of x. So what this means is that the way we write an inverse function would be f of minus 1 x. And this is basically just telling me that this is the inverse of my function f of x. And then if I were to take the function of the inverse, that is to say, if I were to say f of negative 1 of x, what this is going to give me is this is going to be equal to whatever was within the function, because the inverse function undoes it. So if I plugged x into the inverse function and then I took the function of it, it would undo that inverse function. I would just be left with x. Similarly, if I have f of x and I take the inverse function of f of x, this also will undo the function. So whatever x you plug in, the function will transform it into whatever outcome you get. The inverse function will undo that and take you back to x. The graph of an inverse function will reflect this function over the y equals x line. So when y equals x, that is to say this line here. So if I have some function that looks like this, what it's going to do is it's going to take this and reflect it across the y equals x axis, and it will be something like this. So all it will do is it will reflect across the y equals x axis. And then of course, one last thing, because of this property where basically everything is inverted, if I have on my f of x some point a, b, then this means that the inverse function will have some point b, a. Next, I want to talk about logarithmic functions. Now, I know most students hate these, but they are actually tremendously useful in mathematics. They're really good to act as a scaling factor, and if you have some, functions that grow very quickly, they can actually help bring it down into a scale that's very useful for us to analyze. So if b is greater than 0 and not equal to 1, then the exponential f of x equals b to the x is 1-to-1, and the inverse is the logarithmic function. That is, f of x equals log base b x. So what this means is that if we have b to the y, this will equal to x, and that means that if we solve for y, we have y is equal to the log base b of x. And this is kind of how we do this whenever you first learn logarithms. You learn about the logarithm function, and then you learn about the inverse function to figure out what your x would be and things like that. Now, this isn't really what we're going to be focusing on in this course. What I really want to be focusing on are the laws of logarithms. So just like before when we were doing exponents, we have a bunch of rules that really help us with our calculations. So the first is that if I have log base b to the x, this is going to just be equal to x. So pretty much the way it works is that I can pull this power out and it will just become x times log b to the b, log b of b, and then it'll just be x. The second law is that if I have b to the log base b of x, this is going to be equal to x. This is actually using these rules here. So if I have that y is equal to log base b x, this is the same thing as saying b to the y, which looking at this, we have that b to the y is equal to x. So it's actually just from our definitions of the function for the logarithm and the inverse. The third law is going to be that if we have log base b of 1, this is going to be equal to 0. The fourth law is going to be that if we have log base b of x times y, this is the same thing as taking the log of x plus the log of y. And this is actually one that we're going to use quite a bit in this course. Similarly, if I have log base b of x over y, this would be equal to the log base b of x minus the log base b of y. And then our last rule is going to be that if we have log base b of x to the r, this is going to be equal to r log base b of x. And this is kind of similar to what we were talking about up here of pulling the powers out, is that basically what this means is I can pull powers out. So this is also one that we will use quite a bit in this course. Now, generally, we're not going to be using logs in terms of base b. We're actually going to be using what's called the natural log. So the natural log is just going to be the log with base e of x. And you'll actually find this, for example, if you look at your calculator, you'll see that you usually have a special button just for this. And then these are the natural logs. So whenever you see natural log of something, this is what we're doing. We're taking a log with base e, and this we're actually going to be using quite a bit. But let's say that you actually had some logs and you wanted to change the base from one log to another. So if we had log base b for some value a, then what we could do is we could take the natural log of a over the natural log of the base that we had for this logarithm, which would just be equal to log of a over log of b, which then is going to be equal to log of x a over log of x on b. So again, we're not going to use this a ton, but it is useful to know this just in case you ever do need to change the base of your logarithm. Now we're going to talk about sequences. So a sequence is just an ordered list of numbers a1, a2, ... through an, and then it continues on. And sequences can be defined either explicitly with a formula or recursively. So for example, let's say that we have an equals 2n minus 3. If we were to start plugging in numbers into this, what would we get? So if we plugged 1 in for n, so a1, we would get 2 times 1, which is 2, minus 3 gives us negative 1. If we were to plug in 2, we would get 2 times 2 is 4, minus 3 is 1. If we were to plug in 3, we would get 3 times 2 is 6, minus 3 is 3. If we were to plug in 4, this would be 4 times 2 is 8, minus 3 gives us 5. And then, of course, this could go on and on. So you can see that what's happening with this sequence is that it's taking your input number and it is increasing it by 2 every time that you go up by a number, starting at negative 1. So negative 1 to 2, negative 1 to 1, 1 to 3, 3 to 5, 5 to 7, 7 to 9. And then this sequence would go on forever. So this explicitly defines what the sequence is. Let's say, for example, then that we have the sequence bn, and this is equal to negative 1 to the nth power divided by n plus 1. So what's going to happen when we start plugging numbers into this? Well, if we plug in b1, we're going to plug in 1 for the 1 power. So negative 1 to the 1 power is negative 1. And then 1 plus 1 is 2. So we get negative 1/2. If we plug in b2, when we plug 2 in, this becomes negative 1 squared. Negative squared gives us a positive. So this will be positive 1 over 2 plus 1 is 3. If we plug in b3, what we get is negative 1 cubed, which again will be negative 1. And then 3 plus 1 is 4. b4 is going to be 1 over 5. So looking at this sequence, what's happening is that it's actually alternating. So it's going from a negative value to a positive value, negative value to positive value. But each time it does, the denominator is going up by 1, meaning it's actually getting closer and closer and closer to the origin. It's bouncing back and forth from negative to positive, but each time it's getting a little bit closer. It's approaching with every single number. Now, what if you actually have the sequence and you want to try to figure out what the explicit definition of that sequence is? So let's say, for example, you have 7, 11, 15, 19, and so on and so forth. And we want to figure out what is the sequence that describes this. So usually what I would do is I would consider what times some value n, or to some power, and then added something would cause the sequence to occur. So what's happening here is we're going from 7 and we're increasing by how much? 7 to 11 increased by 4. 11 to 15 increased by 4. 15 to 19 increased by 4. So this means that I know that every step of the way I should be going up by a factor of 4. And then I need to figure out, well, what would cause me to start at 7? So if I plug in 1 here, 1 times 4 is going to give me 4, plus what makes this 7. So this would be 4n plus 3. And then if we just check our numbers, 1 times 4 is 4, 5, 6, 7. 2 times 4 is 8, 9, 10, 11. 3 times 4 is 12, 13, 14, 15. 4 times 4 is 16, 17, 18, 19. And this seems to fit the sequence for the numbers that we have. Or let's say that we have 2 over 3, negative 4 over 9, 6 over 27, negative 8 over 81, so on and so forth. Now for this one, because it's going from positive to negative, generally this means that we're going to have some value to a power, which will basically go from an odd power, which would usually either make it negative or positive, and then you're going to flip it based on whether it's something like negative 1 to the n plus 1 power or negative 1 to the nth power. So the fact that our first term is going to be positive, this means that likely it's going to be to the n plus 1 power. So I'm going to start with this. So minus 1 to the n plus 1 power. So basically what's going to happen then is if I plug in 1, I get negative 1 to the second power, which means that this will be positive 1. If I plug in 2, this is going to give me negative 1 to the third power, which means it would be a negative 1. So okay, so that part looks pretty good. Now, just like before, I'm going to look at my numerator and see what would cause these numbers to occur. So basically what's happening is that it's increasing by 2 each time. So if I were to plug in 1 times what gives me 2? 2 times what gives me 4? 3 times what gives me 6? So this means that it's probably going to be 2n. And now we want to focus on the denominator. We have 3, 9, 27, 81. Now I can see from the sequence that this is going to be powers of 3. 3 to the first power is 3. 3 squared is 9. 3 to the third power, or cubed, is 27. 3 to the fourth power is 81. So I would say that this is going to be over 3 to the n. And now we have the function that describes this sequence. The last thing I want to talk about are recursive sequences. So recursive sequences are where you take the output from one step and put it into the next step. So it basically will change recursively from each step and what came before. So let's say, for example, that we have a1 is equal to 4 and an is equal to 2 an minus 1, which means the prior a that you had, so before this step, plus 5. So to begin our sequence, we have that a1 is equal to 4. So we're already given the first step. Now what I'm going to do is I'm going to take that 4 and I'm going to plug it into here. So I'm going to get 4 times 2 is 8, plus 5 is going to give me 13. And now what I'm going to do is I'm going to plug 13 in for the next step. So 13 times 2 is 26, plus 5 is 31. Then I'm going to plug 31 into this. So 31 times 2 is going to be 62, plus 5 is going to be 67. And this would be a recursive sequence. Each step, we basically are taking whatever we had and plugging it back in to get the next number in it. It's growing based off of the step that came before. Let's do another example. b1 is equal to 3, and we have that bn plus 1 is equal to 5 times bn minus 12. So again, we're going to start with 3. And then when we go up by 1, we are going to plug in here, and we're going to get 3 times 5 is going to be 15, minus 12 is going to give us 3. okay? So then I'm going to plug that 3 back in. 3 times 5 is 15, minus 12 is going to give me 3. And then it's going to keep doing that. So in fact, this recursive sequence actually is giving me the each same number because once I plugged in 3, I was actually getting the same number out. So it basically got stuck at that step where it would continue to be 3 no matter how many times I go through the sequence. And that's it really for our review for calculus. So starting in the next lesson, we're going to be diving into actually doing some calculus, starting with limits. And this is why we need to know stuff like this with sequences, how to use natural logs, exponents, things like that, because we are going to be using it all in this course. And as I talked about previously, that is really where students mostly struggle with this course. It's not that they can't get down how to take a derivative. Most students pick that up fairly quickly. The problem is once you then have done this derivative, how do you then put it into a form that's useful? Or more specifically, if you have a really complex equation, can you simplify it to a form that you can use your rules for derivatives to solve for? Hello everyone. In today's lesson, we're going to be looking at limits of sequences. So to begin with, first we're going to define what a sequence is. So a sequence is just an ordered list of numbers, A1, A2, so on and so forth, going on forever. So basically it's going to be an ordered list of numbers that has some way that it grows or shrinks or does something or cycles. And we're going to be looking at how would we determine what's going to happen, its behavior as it goes on. So what would happen in terms of a sequence as n grows? So let's say, for example, that we have an equals 1 over n. So the first thing we're going to do is we're going to just plug some numbers in. So if I plug 1 into this, I'm going to get 1 over 1. So the first value of my sequence is 1. When I plug 2 in, I get 1 over 2. When I plug 3 in, I get 1 over 3. When I plug 4 in, I get 1 over 4. And this is going to continue on. So what's happening as our n grows? Well, in this case, it's shrinking and shrinking and shrinking, and it appears to be that it's approaching 0. What about if we have the sequence Bn, which is equal to -1 to the n? So again, let's plug in our values. We plug in 1, we get -1 to the 1 power is going to be -1. If I plug in 2, I get -1 squared, which is going to be +1. If I plug in 3, I get -1 cubed, which is going to be -1. And then basically it's going to continue oscillating between -1 and +1, -1 and +1. So in this case, it does not approach any number. So this sequence will go on forever, going back and forth between -1 and +1. What about if we had the sequence Cn, which is going to be equal to n squared? So let's plug our numbers in. 1 squared is going to be 1. I plug in 2, I get 2 squared. This is going to be equal to 4. I plug in 3, 3 squared is equal to 9. 4 squared is 16, 25. So what's happening with this one is, well, in each step of this, it's growing, but it's starting to grow faster and faster and faster and faster. So basically what's going to happen is our terms are approaching infinity. And this is really kind of what we're looking at, is we're looking at the behavior as we go forward. So as we start at step 1 and we go forward, is it converging on some number? Is it diverging off to infinity? Is it going back and forth and oscillating between two values? And this is the idea behind what we're doing when we take a limit. Let's define what a limit is. A sequence, an, has a limit L if we can get the terms of an arbitrarily close to L by taking n sufficiently large, meaning that basically if we were to look at this sequence and take it and get it bigger and bigger and bigger, the n, not the sequence itself, what happens as that with the behavior as we continue this on? So what we're going to do is we're going to write this as the limit as n approaches infinity, and then we're going to apply this to our sequence. And if it approaches some value, this would be the limit. So it's going to be limit as n approaches infinity, an equals L, if the terms of an approach L as n becomes very large. That is to say that our sequence, an, will approach the limit L as n approaches infinity. Now, a sequence is convergent if a limit exists and is a real number. So if it converges to a specific number. So an example of this might be something like if I have some sequence that appears to be converging to a very specific number, then this would be convergent sequence. A sequence is divergent if no limit exists or the term approaches plus infinity or negative infinity. So this means that, for example, when we were looking at our sequences, when it was going back and forth from -1 to +1, that would be divergent behavior. It does not converge to a specific number. If it goes and grows up to infinity, this would be divergence. If it shrinks down to negative infinity, this would be divergence. So an example might be, let's say we have the limit as n approaches infinity, 1 over n. Well, what's going to happen as we plug in our sequence values? We plug in, this is the first one we looked at. We plugged in, it was 1 over 1, then 1 over 2, then 1 over 3, then 1 over 4. So what's happening as this is growing? Well, it's shrinking in this case, and this one is not going back and forth between -1 and 1. So what's happening is this is approaching 0, right? Because for every term in the sequence that we go up, we're actually getting smaller and smaller and smaller. We're getting closer and closer to 0. So if I were to plug in like a billion, this would be some tiny decimal. If I were to plug in a trillion, if I were to continue to grow my n, this term would get smaller and smaller and smaller, approaching 0. If we had the limit as n approaches infinity for -1 to the nth power, what's going to happen with this one? Well, if I plug in 1, I get -1. If I plug in 2, I get +1. If I plug in 3, I get -1, +1, -1, +1, -1, +1. And it's going to repeat this over and over and over again. So this means that a limit does not exist. What about if I had the limit as n approaches infinity, n squared? Well, what's going to happen with this one? Well, if I plug in 1, I get 1 squared is 1. I plug in 2, 2 squared is 4, 9, 16, 25, 36. It's growing, and it's growing faster and faster and faster with each step. So basically what it's going to do is it's going to go up, up, up until it's approaching infinity, which means this actually diverges. So this first one is an example of a convergent limit. It's converging on a specific number, in this case 0. The second one diverges. It doesn't have a limit that exists. The third one diverges because it is approaching infinity, which, like we said, if it approaches infinity or negative infinity, this would be a divergence. Here you can see some examples of what this behavior might look like. So our top left graph is a sequence that is converging. So notice it starts up kind of in the top left, and then each term that you go to the right on x, it's getting smaller and smaller and smaller until that y value is approaching 0. The top right is one that is converging on a value. So while this one is going up and then down and up and down, it is oscillating in our y values. It is oscillating around a single point as it gets smaller and smaller and smaller and converges on that single point. So it's converging to some point L. The bottom left shows a graph of what it might look like if it diverges to infinity. Notice that it's getting, as x increases, our y is getting bigger and bigger, faster and faster. And then the bottom right also is a sequence that diverges because it's not changing. It's not approaching some value, but what it's doing is it's going from one value to another, one value to another, back and forth, and it'll continue this cycle forever, never converging on a single value. So now let's define our limit laws. So we have our limit laws, which are that we have, so if our sequence an and bn are convergent sequences, so they're convergent sequences, and c is a constant, then the following rules will be true. The first rule is that if we have the limit as n approaches infinity, an plus or minus bn, so we're saying is if we have the sequence an and we're adding the sequence bn, or an and we're subtracting the sequence bn, this is going to be equal to the limit as n approaches infinity, an plus or minus the limit as n approaches infinity, bn. So remember before I talked about how I'm going to be showing a lot of steps? This is one that I will show a lot. For example, if we have some sequence and added or subtracted and we're taking a limit, a lot of times students will just jump straight in, taking the limit of the first, taking the limit of the second, figuring out what it is. But I'm actually going to break it down into, it's actually the limit of the first, it's the limit of the second, and then you add or subtract them, just to keep our steps consistent. The second law is that if we have the limit as n approaches infinity constant times one of our sequences, this is going to be the same thing as c times the limit as n approaches infinity of our sequence. So pretty much what it means is that if I have a constant times this sequence and I take the limit of it, I can actually pull that constant out, and it's the same thing as taking the limit of the sequence and then multiplying by a constant. So basically what it's kind of saying is that if I had some sequence and I multiplied every term by 2, it would be the same thing as taking the entire sequence and then multiplying that by 2. Our third law is that we have the limit as n approaches infinity on a constant c is going to be equal to c. Because what this means is that if I have some constant value and I take the limit of it, it's not changing. So the limit as n approaches infinity will still be c. Or if you wanted to try to use a rule like this, it would pretty much be that you're going to pull your c out and then you're taking the limit of 1, which is just going to be 1. So 1 times c would give you c. Our next rule, rule 4, is that if we have the limit as n approaches infinity, and we have an times the sequence bn, this is going to be the same thing as taking the limit of an as n approaches infinity times the limit as n approaches infinity on bn. Similarly, if we have the limit as n approaches infinity, an divided by bn, this is going to be equal to the limit as n approaches infinity on the sequence an divided by the limit as n approaches infinity on the sequence bn. Now, these actually are technically kind of the same rule, because if you think about it, this division, an divided by bn, would be the same thing as saying an times bn to the negative 1, in which case this would be, when we do this, it would become the limit of an times the limit of b to the negative 1, and then in that case, you just, this is actually kind of the same rule. The exponential, multiplication, and division are kind of the same. Next rule we have, number 6, is that if we have the limit as n approaches infinity, our sequence an, and this is to the p power, this is the same thing as taking the limit as n approaches infinity, an, the entire thing to the p power. Our 7th rule is going to be that if we have the limit as n approaches infinity, 1 over n to the power p, this will be equal to 0, or it converges to 0, for p greater than 0. And this is because basically what's going to happen is if I plugged in 0 power, this would be 1 over any value n to the 0 power is just going to be 1, so 1 over 1 is going to be equal to 1. If I plug in a negative power, it's going to actually bring it up to the top, which would make it bigger. Any power that's greater than 0 would make the denominator larger, which would then in turn make the entire fraction smaller as it gets smaller and smaller and smaller and approaches 0. Now consider a geometric sequence. So geometric sequence is just a sequence that takes the form bn equals ar to the nth power. So this means that it'll be ar squared, ar cubed, and so on and so forth. So if we take the limit as n approaches infinity of this sequence r to the n, we actually have to consider a few different cases. We have to consider the case when r is between 0 and 1, not inclusive. So in this case, it would be when you have values that are a fraction or a decimal between 0 and 1. In this case, what this is going to be is this is going to be 0 if this is true. If we have that r is equal to 1, then this means that we will get 1, and if our r is greater than 1, this means that it will approach infinity. So what this means is just with our sequence, if we have a power between 0 and 1, then as we take the limit of this, what's going to happen is the power is going to cause it, as the number gets bigger, to shrink. If it's equal to 1, it does not change the value, right? R to the 1 power will always be r. If this power for r is greater than 1, then what's going to happen is that as the limit increases, this power is going to get bigger and bigger and bigger, therefore it's going to get bigger, right? If r is a decimal, then as the power goes up, the value gets smaller. If r is 1, as the power goes up, nothing changes. And if r is greater than 1, the whole thing will get bigger. So if we add the terms of a geometric sequence together, we get an infinite geometric series. That would be S is equal to A plus AR plus AR squared plus AR cubed, so on and so forth. And this would be equal to A divided by 1 minus R. Let's look at a couple examples. Suppose that you have the sequence AN is equal to the square root of n. Then what's going to happen? Well, as I plug in my first term, square root of 1 is going to be 1. Then I'll have the square root of 2, square root of 3, the square root of 4, which is just equal to 2, the square root of 5, the square root of 6, square root of 7, square root of 8, the square root of 9, which is going to be equal to 3, and so on and so forth. So as n increases, what's happening with this? These values are actually getting bigger, right? We're going from 1, eventually we got to 2, eventually we got to 3. They're not growing quickly, but they are growing. So this means that as square root of n continues to grow larger, as n approaches infinity, this means that the limit as n approaches infinity of the square root of n is equal to, now of course remember we talked about powers. This can be thought of as n to the 1/2 power, and we can take a power out and take a power of the entire thing, which would mean that this is equivalent to the square root of the limit as n approaches infinity for n. So this, we just said, is going to be equal to infinity. So in this case, this is divergent. In the next example, we're going to find the limit as n approaches infinity, and we're going to have 1 plus 2 to the n squared divided by 5 plus 3n plus 4n squared. Now, looking at this term, this might look a little bit difficult. So what we're going to do is we're actually going to use a trick where we are going to divide by the highest power in the denominator. So we're going to divide everything by n squared. So if we did this, this becomes the limit as n approaches infinity, 1 over n squared plus 2n squared divided by n squared divided by 5 over n squared plus 3n over n squared plus 4n squared divided by n squared. And this will mean that, for first of all, these two n squares will cancel. This n square will just be left over as it cancels with this n. This n squared will cancel. So now we're going to be left with is the limit as n approaches infinity, 1 over n squared plus 2 divided by 5 over n squared plus 3 over n. And now if we were to consider the fact that this is just 1 over n squared plus 2, what we can do is, remember, with our rules of limits, we can take the limit of the top terms and the limits of the bottom terms, and then the limit of this plus the limit of this. This is going to be equal to the limit as n approaches infinity for 1 over n squared plus the limit as n approaches infinity for 2 divided by the limit as n approaches infinity, 5 over n squared, plus the limit as n approaches infinity, 3 over n. Which, remember, based on our rules we have, we could actually pull this 3 out, because it's the same thing as saying 3 times 1 over n. So I can change this to 3 times 1 over n. Similarly, this can become 5 times 1 over n. So now, if we take the limit as n approaches infinity, 1 over n squared, what's going to happen to this term? This term is going to go to 0. If we take the limit of 2, we talked about the fact that a limit of a constant is the constant. So this is going to be equal to 2. If we take the limit of 1 over n squared as n goes to infinity, this also will go to 0. 0 times 5 is 0. And then same thing, if we take the limit as n goes to infinity, 1 over n, this will go to 0, and 0 times 3 will also be 0. So then we're left with, oh, I forgot my 4. Sorry. So when we take the limit of this 4 also, we're left with 2 over 4. For the next example, let's take the limit as n approaches infinity for 2 to the nth power minus 1 over 6 to the nth power. And we'll see if this exists, whether it converges or diverges, and if it does have a limit, what does it approach? So the first thing I'm going to do is whenever I have a fraction of 2 terms divided by a single term, I can actually split this up. So this is going to be the limit as n approaches infinity, 2 to the nth over 6n minus, so what I'm doing is I'm taking the limit of the top and the bottom, or taking the limit of the whole thing, I'm splitting this into 2n over 6 to the nth, minus 1 over 6 to the nth. And then what I'm going to do is I'm going to take the limit of both of these terms individually. So remember, the limit of a plus b or a minus b became the limit of a plus b, limit of b, or the limit of a minus limit of b. So in this case, this would be the limit of 2 to the n over 6 to the n minus the limit as n approaches infinity, 1 over 6n. Now, based on this, what we can do is we can actually convert this 2 to the n over 6 to the n. Remember those exponent rules? Well, in this case, this is going to be the limit as n approaches infinity, 2 over 6 to the nth power, minus limit as n approaches infinity, 1 over 6 to the nth power. Okay, so now that we have both of these in terms of its nth power, because this one could also be considered 1 over 6 to the nth power, because 1 over 1 to the nth power still be 1. Now that both of these have this power, what's going to happen with this? Well, it's going to end up being a fraction going up to a power that's getting bigger and bigger. Remember, we talked about that with our geometric sequences. If we had that r was between 0 and 1, then our r to the n was equal to 0. So in this case, this is going to go to 0. This is also going to go to 0 as we take our limit as n goes to infinity for both terms. So this is going to end up being 0 minus 0, which means that it converges to 0. For this next example, if you look at my notes here, we have two different ones. We have a to n equals n squared divided by 2n plus 3n squared, and bn equals 3 minus 2/3 n, or plus negative 2 over 3 to the nth power. So the first part, if you look at these notes, what this is saying is one approach you could take is a more numerical approach to this, where you actually just start plugging in your values of n. N equals 1, n equals 2, n equals 3, n equals 4, and see if a pattern starts to emerge. So you can see an example here, which I'm not going to write down all these numbers, but if you look at the first one, an, it starts with 0.2, then 0.25, then 0.2727, then 0.2857, then 0.2941. And if you were to continue on with this, you would see that it seems to be approaching kind of around 0.4, right? Or somewhere in the 0.3 to 0.4 range. Looking at Bn, we have 2.33333, 3.4444, and notice that with this one, it's kind of alternating a little bit. It's going, starting at 2.33, going up to 3.44, going down to 2.77, or 2.70, and it's kind of going up and down. It's oscillating, but it's getting smaller. The jumps are getting smaller each time it does this. So in this case, it looks like it's actually going to be converging on something. So now what we're going to do is we're going to do both of these analytically to see what we get. So if we were to take the limit as n approaches infinity of our an which was n squared divided by 2n plus 3n squared. And we have our second one is the limit as n approaches infinity for bn, which was 3 plus minus 2 over 3 to the nth power. So for this first one, I'm going to use that trick we talked about earlier. I have an n squared in the denominator. I'm going to divide everything by n squared. So this is going to be the limit as n approaches infinity, n squared over n squared, divided by 2n over n squared, plus 3n squared divided by n squared. So these n squareds will cancel, leave me with 1. This n will cancel with one of these n's, and these n squares will cancel. This is going to leave me with the limit as n approaches infinity, 1 over 2 over n plus 3. And now, if I were to actually apply this limit, what's going to happen to these terms? Well, if I wanted to be specific about it, what I'm looking at is this, is I'm going to take the limit of 1 divided by the limit of 2 over n plus 3, which then I can split into the limit of 1 divided by the limit of 2 over n plus the limit, and all of these are as n goes to infinity. I'm just doing this to kind of go a little quicker, of 3. Well, the limit of a constant is that constant, so this equals 1. The limit as n approaches infinity, 2 over n, so as the bottom term, the denominator, gets bigger, this whole term is going to go to 0, plus, and then we have the limit of 3, a constant. So then this gives us 1 over 3. So what our first sequence was actually converging to was 1/3, or 0.33333 repeating. Now let's look at the second one. Limit as n approaches infinity, 3 plus minus 2/3 to the nth power. So first thing I'm going to do with this one is I'm going to split it just like we did before using our rules of limits. So I'm going to take the limit as n approaches infinity of 3 plus the limit as n approaches infinity minus 2/3 to the nth power. Now, this first term, because it's a constant, this is just going to be equal to 3. So this one we don't have to worry about. What we do have to consider now is this second term. For the second term, what I'm actually going to do is I'm going to do a trick where I'm going to split this into 2 terms. This is the same as saying negative 1 times 2/3. So this would be the limit as n approaches infinity, negative 1, times the limit as n approaches infinity, 2/3. And then both of these are to the nth power. So what's happening with this term as we take the limit as n approaches infinity? Well, it's going back and forth between negative 1 and positive 1, right? So nothing's really happening there. This term, if we look at it, this is a fraction, which is, again, between 0 and 1. So as n gets bigger, this power, right, we talked about this, we have r to the n. If r is between 0 and 1, then it's going to go to 0. 0 times anything else is going to be equal to 0. This is just going to leave us with 3. For our next example, we're going to look at whether the sequence an equals 2n squared plus n minus 1 divided by n squared converges or diverges. So we're going to do this, of course, by taking the limit of this sequence. So we're going to take the limit as n approaches infinity of 2n squared plus n minus 1 divided by n squared. So for this one, you could try dividing by n squared, but what's going to happen is you're going to end up with 2 plus 1 over n minus 1 over n squared divided by 1. You're still going to end up with that n squared denominator. You definitely can do that, and it would work. But what I'm going to do in this case is I'm just going to split this fraction. So this is going to end up being the limit as n approaches infinity, 2n squared over n squared plus n over n squared minus 1 over n squared. And it's going to give me the exact same value, because that's really all we're doing, is we're just splitting the fraction when we do that. So these n squares are going to cancel. This n is going to cancel with this n square, and we're going to be left with the limit as n approaches infinity, 2 plus 1 over n minus 1 over n squared. Now, using our rules of limits, I can split this into the limit of 2 plus the limit of 1 over n minus the limit of 1 over n squared. So this is going to be, again, I'm going to shorthand. I'm going to leave off the n goes to infinity, but they all do. So limit of 2 plus the limit of 1 over n minus the limit of 1 over n squared. And now we can look at these terms individually. Well, the limit of a constant is a constant, so this is going to be equal to 2 plus the limit as n goes to infinity, right, because these are all as n goes to infinity. And this term, 1 over n, this is going to go to 0. This one is also going to go to 0, and we're going to be left with 2. What about this sequence? Bn equals n squared divided by the square root of n cubed plus 4n. Okay, so now for this one, we're taking the limit of this. What I would want to do first is actually get everything either out of the square root or under the square root. So what we're going to do is we're going to take the limit as n approaches infinity, and I'm just going to jump straight to that step. So what I'm going to do is I'm going to put the entire thing under the square root. Now, if I wanted to make this a square root, I would have to consider what would cause it to be n squared, and this would be n to the 4th power, right? If I took the square root of n to the 4th, this would give me n squared. So this would be over n cubed plus 4n, and I'm taking the square root of this entire thing. Now, you might wonder why I'm doing this. Well, I'm doing this because then I can use one of those rules we talked about, where the square root of whatever's inside, I can take the square root of the entire thing. Because remember, anytime you see this is kind of the same thing as saying n over 4, n cubed plus 4n to the 1/2 power. In which case, what can we do with that? We can take the 1/2 power of the entire thing. So this is going to be the limit n over 4 over n cubed plus 4n, and then we take the square root of the entire thing. So now what I'm going to do within the square root is I'm going to do our trick we did previously. I'm going to divide by the largest power in the denominator. So this is going to be the square root of the limit as n approaches infinity, n to the 4th power over n cubed divided by n cubed divided by n cubed plus 4n over n cubed. So this n cubed is going to cancel with 3 of these n's. These are going to cancel, leave me with 1. This 1n is going to make this squared. So this is going to leave us with the square root of the limit as n approaches infinity, n divided by 1 plus 4 over n squared. Now what we can do with this is I can actually split this into the different parts, right? Because I can take the limit of the top divided by the limit of the bottom. And then this limit of the bottom I can take as the limit of 1 plus the limit of 4 over n squared. So this is going to be the limit as n approaches infinity, n divided by the limit as n approaches infinity, 1, plus the limit as n approaches infinity, 4 over n squared. And now I can actually evaluate each of these terms individually. What happens with the limit of n as n goes to infinity? It approaches infinity. So this is going towards infinity. What happens with the limit of a constant? Well, this term is going to be just the constant. So this is going to be 1. 4 over n squared. As n gets bigger and bigger towards infinity, this whole term is going to go to 0. So I'm going to be left with a term that is approaching infinity over 1 under the square root, which means that basically this is equivalent to saying infinity, so it diverges. For our next example, we're going to be taking the limit of this sequence, Cn equals 3 plus 5n divided by 2 plus 7n. So first thing we're going to do, we'll set up our limits. We have the limit as n approaches infinity, 3 plus 5n divided by 2 plus 7n. So what I'm going to do is just like before, I'm going to divide by the highest power of our n in the denominator. So in this case, it's just n to the 1. So this is going to be the limit as n approaches infinity, 3 over n plus 5n over n divided by 2 over n plus 7n over n. These n's will cancel, so we'll be left with the limit as n approaches infinity, 3 over n plus 5 divided by 2 over n plus 7. So as before, what we can do is we can take the limit of the top over the limit of the bottom. This limit of the top can be split into the limit of 3 over n plus the limit of 5. This bottom can be split into the limit of 2 over n plus the limit of 7. So we can actually kind of just evaluate them individually. So for this first term, when I take the limit as n goes to infinity, what happens when you have the denominator is approaching infinity? The whole fraction is getting smaller and smaller and smaller until it becomes a 0. It's approaching 0. The limit of a constant is just going to stay that constant. Again, limit of 2 over n is getting bigger, so the whole fraction is getting smaller, it's approaching 0. And then the limit of a constant is a constant. We are left with 5 over 7. What about if we had something like this? What about if we had a sequence dn, which would be the cosine of n pi over 2? Well, with something like this, if we were to take the limit of this sequence, so limit as n approaches infinity, cosine n pi over 2. What's going to happen as our n is increasing? Well, if you look at what cosine does, cosine basically just looks like this. It goes from 1 to -1, and then it's going to keep repeating the cycle. So in this case, this means that it's never going to converge because there's nothing causing it to shrink or narrow down to a specific term. So in this case, this one does not exist. This would just be a cycle that continues back and forth from -1 to +1. And that's going to be it for this lesson. When we come back, we're going to keep building up the building blocks we're going to need before we actually start getting into the main topic of this course, which is going to be, of course, derivatives. But limits are really our foundational thing that we need to understand in order to build up to doing that. So this is why it's kind of important that we understand what happens with these functions and sequences and series as we take some limit. In this case, we're taking a limit as n goes to infinity, and then we'll look at what about if we have limits that go to a particular point. So there's lots that we're going to be covering in this course. I know it was kind of jumping around in the beginning as we looked at a lot of review, and this one we're kind of just speeding through, and it's because I'm just trying to build some of the basic foundational stuff that hopefully have been covered elsewhere, and then we can actually jump into building up new skills with calculus. Hello everyone. In today's lesson, we're going to be looking at limits of functions at infinity. So first of all, let's look at our limits at infinity. So we have the notation, we take the limit of some x as it goes to infinity on the function f of x equals L. This means that our function f of x will go to L as x approaches infinity. So our line y equals L is the horizontal asymptote if our limit of f of x equals L, or if our limit as x approaches negative infinity equals L. So that is to say, our limit as x approaches infinity, f of x is equal to L, or our limit as x approaches negative infinity equals to L. And these are our limits at infinity. Now I want to note here that infinity is not a real number. So even though we write that limit of as x approaches infinity, f of x equals L, the function is divergent if the limit is either plus or minus infinity. So if you get the limit is equal to plus or minus infinity, it's actually divergent. And since infinity is not a real number, not all of the normal operations that we do hold. So for example, we might have infinity plus infinity equals infinity. So I just add some infinitely large number to some other infinitely large number, I'll still have infinity. If we did infinity times infinity, same idea. If I have some infinitely large number and I multiply it by some infinitely large number, I still end up with infinity. But if I have infinity minus infinity, well, what does this even mean? So in this case, this would be undefined. And similarly, if I have infinity divided by infinity, this would also be undefined, because what does it mean to take some infinitely large number and subtract off some other infinitely large number, or take some infinitely large number and divide by some infinitely large number? So as an example, looking at this graph, what would be our asymptotes based on this graph? Well, as x goes to infinity, which means that we're going to the right here, you'll notice that it looks like this line is approaching +3, but never actually touching it. So this would be the asymptote, or the limit, as x approaches infinity. As x approaches negative infinity, that is going on our graph to the left, it looks like this line is approaching -2, but never actually touching it. So this means that our limit as x approaches infinity on our function f of x is equal to +3, and the limit as x approaches infinity, negative infinity, on our function f of x will be equal to -2. So this means that we have y equals -2 and y equals 3. These are the two asymptotes that this function is approaching as the limit approaches infinity or negative infinity. In this example, we want to find the limit as x approaches negative infinity on the function 1 over x, and we want to try to figure out what this is equal to. And we also want to see what is the limit as x approaches infinity on our function 1 over x. So if we were to look at the behavior of this function, what happens as we go with larger and larger and larger numbers to the right? So as our x increases, we'll start with the going to infinity. Well, if I plug in 1, I'm going to get 1 over 1, which is 1. If I plug in 2, I'm going to get 1 over 2, which is 1/2, 1/3, 1/4, 1/5. So what's happening is, as I go to the right, I'm getting closer and closer and closer to 0. So I'm just going to kind of draw it like this for now. Now, what happens with this positive x approaches infinity, but as I get closer to 0, right? Because I know that I cannot plug 0 into this, because I would end up with 1 over 0. So if I plugged in 0.5, I would get 1 over 0.5, which is equal to 2. If I plugged in 3, I would get, if I plugged in 0.3, I would get 1 over 0.3, which is going to be 3.3, something like that. So what's happening is, as this value gets closer and closer to 0, the entire thing is getting bigger, meaning that it's going to be approaching infinity as it approaches 0. Similarly, if I'm looking at x that go to the negative infinity direction, if I plug in larger and larger x values that are negative, so -1, -2, -3, so on and so forth, it's going to get smaller and smaller and smaller, and it's going to approach 0. If I get closer to 0, so as I approach 0 from the left, what's going to happen is this is going to get smaller and smaller and smaller down towards negative infinity. So this would be a graph of what this function looks like, meaning that if I look at what happens as x goes to negative infinity, it's approaching 0. So this is going to be equal to 0. And if I look at what's happening as x approaches positive infinity, this is also going to be 0. So in this case, the limit as x approaches infinity is equal to 0. The limit as x approaches negative infinity is also equal to 0. So now that we have an intuitive idea of what it means to take a limit as x approaches infinity or negative infinity, let's look at what we would do if, we're using a couple examples, if we had functions that weren't so easy to visualize and we wanted to solve it analytically. So we're going to start with, in this case, the limit as t approaches infinity, 8t divided by 1 plus 4t squared. So in this case, I don't know what this function looks like on a graph off the top of my head. Now, I could put it into a computer or calculator and probably look at it, but sometimes you're not going to know what the behavior is off to infinity by just looking at a graph in a local frame. So you might have to zoom out, zoom out, zoom out. It's easier just to say, okay, well, let's just solve for what this is equal to as I approach infinity. And usually the first trick we do is we plug in infinity and see what happens. So in this case, if I were to plug in infinity, anywhere there's t, I would get 8 times infinity, which is equal to infinity, over 1 plus 4 times infinity squared. So infinity squared is infinity, 4 times infinity is infinity, 1 plus infinity is still infinity. I end up with infinity over infinity. So as we talked about, this is undefined. So that really didn't tell us anything. So now what we're going to do is we're going to try out some of our tricks. So our first trick we talked about was dividing the entire thing by the highest power of whatever parameter we're looking at, in this case t. Divide everything by that t squared. So this would be the limit as t approaches infinity, 8t over t squared, divided by 1 over t squared plus 4t squared over t squared. Now, of course, I'm going to do some cancellation. This t will cancel with one of these t's. This will be 1 over t squared, and the t squares will cancel here. So now what we're left with is the limit as t approaches infinity, 8 over t divided by 1 over t squared plus 4. Now, at this point, most people would just solve it by, again, going back to plugging in t to see what the behavior is. But just to be more explicit, what I'm going to do now is I'm going to use our limit rules to actually show how we're actually solving this. So first things first, I have limit of something in the numerator over something in the denominator. So this is actually equivalent to saying that I want the limit as t approaches infinity, 8 over t, divided by, now I have the limit as t approaches infinity, 1 over t squared plus 4, which can then be split into the limit of the first thing plus the limit of the second thing. So this is then going to be the limit as t approaches infinity, 1 over t squared, plus the limit as t approaches infinity, 4. And now that we have it in this form, we can actually solve for it, because we have this 8, which is constant, so I could pull this out. And this is going to be the same thing as actually taking 8 times the limit of 1 over t as t approaches infinity. This one, we don't have to actually make any change, so I'm going to leave this one, limit as t approaches infinity, 1 over t. And then this one also doesn't need to be changed. So plus limit as t approaches infinity, 4. Now we can actually look at all of our individual limits. What is the limit 1 over t? And we covered this previously, is what's going to happen is as this t gets bigger and bigger and bigger, it's going to be 1 over 1, 1 over 2, 1 over 3, is that this entire fraction is getting smaller and smaller and smaller until it goes to 0. This bottom term, same idea, we have 1 over t squared, which is going to also go down to 0. And then limit of a constant is just going to be that constant, so this is going to be 4. So we're left with 0 over 0 plus 4, which is 0 over 4, which is equal to 0. Next, we're going to look at the limit as x approaches infinity. And this is going to be on the square root of x squared plus 1 minus x. Now, in some cases, you're not going to be able to use the trick we talked about where you just divide by the largest power in the denominator, because in this case, we don't really have a denominator to a fraction. So we're going to need to use a different trick to be able to solve this, because if we were to plug in infinity, infinity squared is infinity, infinity plus 1, still infinity, the square root of infinity, still infinity, because that would just be infinity to the 1/2 power. So we have infinity minus infinity, which again we said was undefined. So what we're going to do in this case, if you ever see a term kind of like this, is we're going to do what's called multiplying by the conjugate. So the conjugate of this term is the same terms, square root of x squared plus 1 and x, except for now we're going to switch the operation from subtraction to addition. So this is going to be the limit as x approaches infinity, the square root of x squared plus 1 minus x, and then we're going to multiply this. So we're going to think of this as a fraction over 1, and we're going to multiply this by square root of x squared plus 1 plus x divided by square root of x squared plus 1 plus x. Now, the reason I can do this is because any term over itself, square root of x squared plus 1 plus x over the same thing, is the same thing as just multiplying this entire function by 1. So I haven't changed anything. So now what we need to do is we need to multiply this out. So for the bottom, we're just going to multiply 1 times this. It's going to stay the same. So this is going to be the limit as x approaches infinity. And this is going to be the square root of x squared plus 1 plus x. And in the numerator, we're going to have to FOIL this out. So we're going to do first term. So the square root of x squared plus 1 times the square root of x squared plus 1 is the same thing as saying the square root of x squared plus 1 squared. So the square and the square root will cancel. We'll just be left with x squared plus 1. Then we're going to do our outer terms. So we're going to have the square root of x squared plus 1 times x. And then we're going to do our inner terms, minus square root of x squared plus 1 times x. And this is actually why this trick works out so well. And then we'll do our last terms. Minus x times positive x is going to be minus x squared. So now looking at this, what do we have? Well, we have x times square root of x squared plus 1 minus x times square root of x squared plus 1. These are the same terms. We have a positive and negative. These two will cancel with each other. And remember, here we had x squared plus 1 minus x squared. So this x squared is going to cancel with this minus x squared. So this is going to leave us with the limit as x approaches infinity, 1 divided by the square root of x squared plus 1 plus x. And then, of course, using our rules of limits, I could change this to the limit as x approaches infinity of 1 over the limit as x approaches infinity, square root of x squared plus 1 plus the limit as x approaches infinity, x. So the limit as x approaches infinity on a constant 1 is just constant 1. The limit on x squared plus 1, you take the square root of the whole thing. We talked about this already. Infinity squared is infinity. Infinity plus 1 is infinity. Square root of infinity, still infinity. Plus, the limit as x approaches infinity on x is just going to be infinity. So we have 1 divided by infinity plus infinity, which is the same thing as saying 1 over infinity, which means that this goes to 0. Now, sometimes when you're dealing with certain functions, for example, trig functions, you might actually not be able to just take the limit, but you'll have to kind of look at the behavior of the function as it approaches infinity or negative infinity. So let's say, for example, that we were evaluating the limit as x approaches infinity, sine of x. So in this case, if you plug in a value, you're going to be getting values back based on your trig functions. But what happens with the actual behavior of our sine function? Well, sine function, starting at 0, will start at 0 in your, so when x is 0, y is 0, and then it's going to go up to 1, and then it's going to go down to negative 1, and then it is going to have this cycle, right? And of course, we have that this is going to be pi over 2, pi, 3 pi over 2, and 2 pi. Right? So this is when x is equal to pi over 2. This is when x is equal to pi. This is when x is equal to 3 pi over 2. And this is when x is equal to 2 pi. And then what's going to happen is it's going to repeat this. And it's going to repeat it. And it's going to repeat it over and over and over again, and in both directions. So it's going to be going from negative 1 to positive 1, repeating. Meaning that as I go to the right, towards infinity, I'm just going to keep cycling between positive 1, negative 1, positive 1, negative 1. So in this case, when we have this limit as x approaches infinity, sine x, we have does not exist as our answer, because there is no limit that exists, right? It's divergent in the sense that it does not converge on any specific value. It doesn't converge to 0, it doesn't converge to some L, it just will cycle back and forth between negative infinity and positive infinity. For our next example, we're going to be looking at the function x cubed. And we want to know what's happening as you take the limit as x approaches infinity and negative infinity. So we'll start with the limit as x approaches infinity, and we'll also look at the limit as x approaches negative infinity on x cubed. So what's happening as I take my x and it gets larger and larger? Well, first of all, let's see what happens when we have x equals 0. So if I plug in x equals 0 here, 0 cubed is just going to be 0. So I'm going to start right here. If I plug in 1, I'm going to get 1 cubed, which is going to be equal to 1. If I plug in 2, I'm going to get 2 cubed, which is going to be 2, 4, 8. So it's going to be something over here. If I plug in 3 cubed, it's going to be 27, and it's going to grow very quickly. So on the right side, we know that this is kind of what the behavior looks like. It's going to grow very rapidly on the right side. Now, what about if I starting at 0, I start putting in negative values? Well, I have negative 1. Negative 1 cubed is going to be negative 1. Negative 2 cubed is going to be negative 2 times negative 2 is positive 4. Positive 4 times negative 2 makes it negative 8. And then we're going to get negative 27, and it's going to look something like this. So based on this, what's happening as to x cubed as we go to the right as x approaches infinity? It's going to go to infinity. And what's happening to the left as x approaches negative infinity? It's also going to go to, in this case, negative infinity. So what's happening in this case, because this is an odd function, when I have positive values, I'm going to the right, I'm growing faster and faster and faster upward towards infinity. When I go to the left, my negative values will get smaller and will shrink smaller and smaller and smaller towards negative infinity. The next thing I want to talk to you about, though, is that not all infinities are equal, right? Because sometimes, because we're looking as x approaches infinity, or whatever variable we're looking at the rate that it grows or decays. Well, what if you have multiple things that go to infinity, but they grow at different rates? Well, then sometimes this will mean that one will grow faster than another, which actually can lead to the entire function converging to usually 0 or something like that. Or infinity. So let's look at what's happening with these. Let's say that, for example, we had the limit as x approaches infinity on e to the x. We have the limit as x approaches infinity, x squared. We have the limit as x approaches infinity, square root of x. And we have the limit as x approaches infinity, natural log of x. So what we're going to do is we're going to graph this out. So all of these, we're just going to look at what happens as x goes to infinity. So we're only going to be looking in quadrant 1 of our graph, of our Cartesian graph. So if we were to graph e to the x, it's going to look something like this. And this is our e to the x. If we were to graph x squared, it'll look something like this. If we were to graph our function square root of x, it'll look something like this. And if we were to graph our natural log of x, it would look something like this. So all of these do actually go to infinity, right? Because if I plug in e to the x, as my x gets bigger, my exponential causes it to grow very rapidly. Same thing with x squared. If I plug in 1 squared, it's 1, 2 squared is 4, 3 squared is 9, 16, 25, so on and so forth. It's getting larger and larger towards infinity. We already looked at square root of x before in our prior section, where, again, if I plug in numbers, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, square root of 16 is 4. So what's happening is while it's growing very slowly compared to the others, it is growing up until infinity, right? If I plug in square root of infinity, I get infinity. And last, I have my natural log, which also grows very slowly, but it does continue to grow on to infinity. So now you can kind of see how these grow at different rates. So for example, if I were to take something like the limit as x approaches infinity, e to the x over the natural log of x, these are both going to infinity. So you might think just by plugging infinity that this is going to be infinity over infinity, which is undefined. But you can also use the relationship that while they are both going to infinity, this term is growing so much faster than this term. Or what if I had it the other way? What if I had the limit as x approaches infinity, the natural log of x over e to the x? Well, in this case, the denominator is growing significantly faster, meaning that while they're both going towards infinity, the bottom term is getting bigger faster, meaning that the total fraction is getting smaller, meaning that this one is going to converge to 0 in this case. So let's look at an example of this. Let's say that we have the limit as x approaches infinity, x squared minus x. So in this case, we were to just plug in our infinity, we would get that this is limit as x squared would be infinity, minus limit of x would be infinity. So infinity minus infinity, of course, is undefined. So now what I'm going to do is I'm actually going to look to see, is the behavior different if I were to pull this x out? Because I have x squared minus x. Both terms have x. So I could rewrite this as the limit as x approaches infinity. So I pull an x out, and x squared, pull an x out, I'm left with x, minus x, pull the x out, I'm left with 1. Now if I were to take this limit, which again I still can by my rules of limits, right? I could take the limit of x squared minus the limit of x, or I could take the limit of x times the limit of x minus 1. So I'm going to get the limit as x approaches infinity, x times the limit as x approaches infinity, x minus 1. So this will be equal to infinity times infinity minus 1, which, if we consider what's happening here, is that this infinity squared is growing faster than this minus infinity, which we could kind of figure out intuitively here. X squared is growing faster than the x that is being subtracted from it. So in this case, our limit would be, in fact, infinity. So let's do one more example here where we have limit as x approaches infinity, x squared plus x divided by 3 minus x. So first thing I'm going to do is I'm going to use our trick where I'm going to divide everything by the power of whatever the largest power is in the denominator. Because if I were to plug in infinity right now, I'd get infinity plus infinity, which is infinity, divided by 3 minus infinity, which is negative infinity. So I'd get infinity over negative infinity would equal undefined. So in this case, what I'm going to do is I'm going to divide everything by x. So this is going to be the limit as x approaches infinity, x squared over x plus x over x divided by 3 over x minus x over x. Now, doing some cancellation, this x cancels with this x squared. This x cancels out with this x, leaving me just 1. This 3 over x is fine, and then x over x gives me 1. Now this leaves me with the limit as x approaches infinity, x plus 1 divided by 3 over x minus 1. And now with this, I actually could probably try plugging in infinity again and see what happens. So if I were to do this limit, really what's happening is it's the limit of the top over the limit of the bottom, which then this top becomes limit of x plus the limit of 1 over the limit of 3 over x minus the limit of 1. So what's going to happen is these constants will stay constant. This is going to go to infinity, and this is going to go to 3 over infinity. So this is going to be infinity plus 1 divided by 0 minus 1. Now, infinity plus 1 is just equal to infinity. 0 minus 1 is going to be minus 1, which means that I have infinity over negative 1, which is the same thing as saying that this goes to negative infinity. For my next example, we have the limit as t approaches infinity, square root of t plus t squared divided by 2t minus t squared. So I'm going to use the same trick. I'm going to divide everything by the largest power denominator. In this case, it's going to be t squared. So this is going to be the limit as t approaches infinity, square root of t over t squared plus t squared over t squared divided by 2t over t squared minus t squared over t squared. So the t squares cancel. This leaves me 1. This one just leaves me 1. This t cancels with one of the t's here. Now this is where you need to think about your powers, because the square root is the same thing as saying t to the 1/2. So what I can do is I can actually take this square root of t over t squared, and I can rewrite this as 1 over t to the 1/2, right? Sorry, negative. Because what I'm saying is by the t to the 1/2 is saying take the square root. The negative power is putting it into the denominator. So now I have 1 over t to the negative 1/2 times 1 over t squared. And of course, whenever we multiply t to a power times t to a power, you add the powers. Or in this case, because it's negative, we're going to subtract it. So it's going to be 2 minus 1/2, which is going to give me 1 over t to the 3/2. So this leaves us with the limit as t approaches infinity, 1 over t to the 3/2 plus 1 divided by 2 over t minus 1. So now that we're at this form, we should be able to plug in our infinity to see what's going to happen, right? Because again, laws of limits, if you do limit of the top over limit of the bottom, limit of the top becomes limit of the first term plus limit of the second term, limit of the bottom becomes limit of the first term, in this case minus limit of the second term. So 1 over t to the 3/2. What's happening with this in the denominator? Square root of t cubed. Well, what's happening is that this t cubed is growing faster than the square root is slowing it down, meaning that it's going to approach infinity. So we have 1 over infinity, which means this is equal to 0, plus 1, divided by, as I plug infinity into 2 over t, this is going to be 2 over infinity, which is equal to 0, minus 1. So I'm left with 1 over minus 1, which is equal to negative 1. For our last example, we're going to look at the limit as x approaches infinity, square root of 9x squared plus x minus 3x. So just like we looked at before, this case, if we plugged in infinity, we're going to get 9 infinity squared. So infinity squared is infinity. 9 times infinity is infinity. Infinity plus infinity is still infinity. Square root of infinity, still infinity. We're going to get infinity minus 3 times infinity, which is infinity. So infinity minus infinity, which is undefined. So we can't just plug in and see what it converges to. So the next thing we're going to do is we're going to say, can we divide by some power denominator? Well, in this case, there's no denominator because it's not a fraction. So we're going to then use our next trick, which was to multiply by the conjugate. So in this case, this would be equal to the limit as x approaches infinity. So we just write this again. This will be the square root of 9x squared plus x minus 3x. And then this is going to be times. Now, if you remember, the conjugate is going to be the same two terms, but we're going to change this operation. So it'll be square root of 9x squared plus x plus 3x. So this will be square root of 9x squared plus x plus 3x divided by the square root of 9x squared plus x plus 3x. And of course, this is the same thing as saying this is over 1, because any value that you have, you can always think of it as a fraction over 1. So we're going to multiply these out. So for the denominator, this is just going to be the square root of 9x squared plus x plus 3x. For the numerator, what we're going to do is we're going to multiply. Square root of 9x squared plus x times square root of 9x squared plus x. It's going to give me square root of 9x squared plus x squared. So the square root and the square are going to cancel, which is going to leave me with 9x squared plus x. Then I'm going to do my outer term. So that's going to be 3x times the square root of 9x squared plus x. So this is going to be 3x times the square root of 9x squared plus x. Next thing I'm doing my inner terms, minus 3x times the square root of 9x squared plus x. So this is going to be minus 3x square root of 9x squared plus x. And then I'll do my last terms, minus 3x times 3x is going to be, so negative 3 times 3 is going to be 9x squared. So there's going to be minus 9x squared. So now let's look and see if we can do some cancellation. Well, first things first, 9x squared and minus 9x squared. So the negative and the positive cancel with each other. 3x times the square root of 9x squared plus x minus 3x times the square root of 9x squared plus x. These are going to cancel with each other. So we're just going to be left with x in the top. So this is going to be x divided by the square root of 9x squared plus x plus 3x. So now let's see if we can plug, sorry, I forgot my limit. So now what we're going to do is we're going to see, can I plug in, by the way, you always need to leave your limit in the formulation of what you're doing until you've actually solved and plugged in that limit. So sometimes you might see, like, for example, here, I forgot my limit. This is incorrect because it is still the limit as x approaches infinity. The limit does not go away until you actually evaluate the limit at whatever x is approaching, or t, or whatever we're using. So in this case, you do need to keep your limits until you actually plug it in. So if we were to plug in our limit, infinity divided by, well, we talked about the square root of 9x squared plus x, we plug in infinity is going to be infinity plus infinity. So infinity over infinity, still undefined. So now what we're going to do is we're going to do our other trick, and we're going to divide by the largest power in our denominator. So in this case, it's going to be x. Now, you might see, okay, well, I have an x squared here, but if you look at it, it's actually the square root of an x squared, so it's still going to be x. So I'm going to divide everything, so I have my limit, didn't forget it this time, as x approaches infinity, x over x divided by the square root of 9x squared plus x divided by x plus 3x divided by x. Now, this x over x is going to cancel, leave me with 1. This x over x is going to cancel, leaving me with 3. So now I have the limit as x approaches infinity, 1 over the square. What I'm going to do is I'm actually going to pull this x inside. So I can think of this x as the square root of x squared. So by doing that, this term here is going to become 9x squared plus x over x squared under the square root, which then is the same thing as dividing this by x squared, dividing this by x squared. So this is going to be 9x squared over x squared plus x over x squared, all into the square root. And this x squared is going to cancel with this x squared. This x squared is going to cancel, sorry, this x, one of the powers of x here is going to cancel with this x. This is going to leave me with the square root of 9 minus 1 over x. So using that, we have the square root of 9 minus 1 over x plus 3. And then I'm going to plug my x in at infinity. So this is going to become 1 divided by, so the square root of 9 minus 1 over x. Plug in infinity into that x, we get 9 minus 1 over infinity. 1 over infinity is going to, as the denominator gets bigger and bigger, the entire fraction gets smaller and smaller. Same thing as saying 9 minus 0. So this is going to be the square root of 9 and then plus 3. Well, the square root of 9 is going to be, by the way, the limit is gone here because now I've evaluated it. So this is going to be 1 over, so the square root of 9 is 3, so 3 plus 3 is going to be 1/6. And that's all you need to do in order to evaluate a lot of these limits as x approaches infinity or negative infinity. Now, you'll notice in this section, I've been using a lot of tricks. And the thing is, sometimes you are not going to be able to evaluate a function based on just being able to plug in the value, or there might not be some trick that we can use. And later on, we will talk more about this. Numerical methods, or another method we'll talk about later is L'Hopital's rule, which will allow us to evaluate, in this case, indeterminate functions based on trying to solve what this is equal to, right? So right now, when I'm doing a lot of these examples using analytic approaches, these are examples where we know that it's going to give us an answer that we can find analytically.
Hello everyone.
Previously, we've been looking at what happens when you take the limit on a function as x approaches infinity. So now we want to ask the question, what about if we are approaching some specific limit, where instead of it going towards infinity or negative infinity, what happens with the behavior of a function as x approaches some specific value? So this might be a problem like this. We have this velocity problem. Suppose you have a ball that's dropped from the upper observation deck of a tower 450 meters above the ground. How could we find the velocity of this falling ball? So we first have the function that's describing the distance of this free falling object, s of t equals 4.9 t squared. So basically it is the distance that the ball falls, and it is accelerating by some time t squared, right? So that would control how far it's fallen. Next, we have our average velocity, which is the change in position over the change in time, which can be written as the function at time 2 minus the function at time 1, so where it was positioned at time 2 minus where it was positioned at time 1, over the difference between time 2 and time 1. And then how do we define and find this instantaneous velocity, right? So what happens as it's approaching some specific point? Right? So just kind of draw a picture, an idea of what this would look like. You have some cliff here, you're dropping a ball off this cliff, and we're pretty much saying, okay, well, what is the average velocity where it is here? This would be position 2, so s t2, and let's say from the initial position here, which would be s at t1, right? How much has it fallen on average? And it would just be the change in position, which in this case is from here to here. It's just subtract, so take s at t2, subtract off s at t1, and you get the distance between those two positions, over the change in time. How much time did it take to get from position 1 to position 2? And this would give us our average velocity. On average, at what speed is this ball falling? Where the position of the ball was described by s of t is equal to 4.9 t squared. Now this would be an example of what we're talking about, where we want to see, we have some definite limit, right? There's some point where the ball is going to hit the ground. It doesn't go off to infinity. So we can have any point, at this point starting from time 0 up to the time where it would hit the ground, or position 0 to whatever distance, right? So the fact that we had that this cliff was 450 meters would mean that we definitely would not have this ball dropping into infinity. So the notation we're going to be using for this phenomena is much like what we did when x was going to infinity, is that we'll have the limit as x approaches some value a on our function f of x, and this will equal to L, whatever this limit would be. This means that our function f of x is approaching this L as x goes to whatever value a is in this case, whatever we're approaching. So this means we can make values of f of x arbitrarily close to L by taking x sufficiently close to where x is not equal to a. So basically what we're doing is, let's say that a is here, and we want to know what's happening as we approach this a value. Well, we might take a value here, so let's say it's a1, and then maybe get a little bit closer, a2, a3, and what's happening as we get closer and closer and closer to this value a where x does not equal to a. Now the reason this is important is because oftentimes we're going to have functions that we can't actually touch a, right? For example, we might have something like this where, let's say that your function looks like this, where neither side coming from the left or the right, where this would be minus, this would be plus, neither of those can touch a because for some reason, whatever function this is, a is not an option. But we can look at what happens with the limit as we approach that point a, where in this case, because from the left, we're going off to infinity, from the right, we're going off to infinity, we could say that the limit on this function would be infinity. Now here on this slide, you can actually see a couple drawings to illustrate what this might look like. So in the first drawing on the left, we have some function that crosses through the point A, where we can take the limit as it approaches from both the left and the right, and also where it hits at that value A. And we will see that in this case, it's a continuous function because it approaches from both the left and the right, and it also intersects at that same point A. Whereas in the middle, would show an example of a function where it approaches some value a from the left, it approaches some value a from the right, but at that point a, there's suddenly a jump. You see the dot below. This means that at a, it has a different value. Then we have the third image on the right, which represents some function where you can see as we approach from the left and we approach from the right, they're approaching the same value, but it cannot touch that value. This might be something like, if you put this in the denominator of a fraction, it would end up making a 0 in the denominator. So in this case, it can be anything but that point. So in this case, it has what's called a hole, which means that there is a limit, right? From the left and the right, it does approach some value, but it can never actually touch that value. So what we're going to do when we look at the limit is we're going to look at what happens as we get sufficiently close to that value without ever being at that value. So let's look at some intuitive ideas of what this might look like if a function is convergent and if a limit exists and is a real number. So a function is divergent if there's no limit or if the function value approaches either positive infinity or negative infinity. So looking at these images, you can see on the bottom left, we have this function where it starts in the top left corner of the first quadrant and it moves downward as it approaches 0. So as x approaches infinity, you can see that this is converging down to 0. The second image shows an example of what a divergent function might look like. As x increases towards infinity, the y value is increasing exponentially up towards infinity. So in this case, it's diverging to infinity. The third image shows something where it might be some function where it is, in this case, going up and down. It's increasing, it's decreasing, it's increasing, it's decreasing. But each time it is shrinking and getting closer and closer and closer to some specific value. So in this case, as x approaches infinity, it's converging on some value. So in this case, we would say that it converges to some value L. So the limit as x approaches infinity is equal to L. And then the last image has points where it is at 0 and then up to some value. Let's say it's 1. So it goes from 0 to 1, 0 to 1, 0 to 1. In this case, it looks like it's not increasing or decreasing between those jumps. All that's happening is it's consistently jumping from one value to the next, back and forth, back and forth. This means that it's not converging, so therefore we would say this diverges as x approaches infinity. Now, a quick recap on how infinity works is that infinity is not a real number. So even though we will write the limit as x approaches infinity, f of x equals infinity, or as the limit as x approaches negative infinity, f of x equals, if you have it approaching some value infinity or negative infinity, we would say this function is divergent to plus or minus infinity. So since infinity is not a real number, not all operations will hold. We talked about this in the last lesson. If I can add infinities, right? Infinity plus more infinity would still be infinity. Infinity times infinity would just be infinity. But what does it mean if I have infinite objects or infinity and I subtract infinity from it? In this case, it doesn't really make any sense. So this would be undefined. Similarly, if I have infinity and I divide by infinity, this really doesn't make any sense either, so again, this would be an undefined outcome. Now, one approach you could take is, let's say that we have the limit as x approaches 1 on x minus 1 over x squared minus 1. Now, if we were to first test out plugging in 1 for every x value, what would we get? Well, 1 minus 1 would be 0. Divided by 1 squared is 1, minus 1 is 0. So we would get 0 over 0, which is undefined and specifically indeterminate. So one thing we could do is we specifically want to look at, okay, well, if we can't be at x equals 1, what would happen if we approach from the left, and what would happen if we approach from the right? So in this case, we're going to have two things we look at. The limit as x approaches 1, and we'll put a little minus sign, meaning we're approaching from the left, and this would be x minus 1 over x squared minus 1. We'll also be looking at the limit as x approaches 1 from the right, which would be a little plus sign, again, of x minus 1 over x squared minus 1. So we're going to be looking at what happens as we approach from left and right. Now, one method you could use is to use numerical analysis of this, where we're just going to say, okay, well, what if I plug in numbers and I get closer and closer to this value 1, and I see what happens? So we have an example of this where we might have our x values, and then what is the outcome of our function at those x values. So for example, if we plugged in 0.99, our function outputs 0.502. If we plug in 0.999, getting closer to 1, we get 0.50025. If I plug in 0.9999, I'm going to get 0.50002. So looking at this, coming from the left side, as I approach a equals 1, it looks like as I'm approaching that 1, I'm getting closer and closer and closer to the value 0.5. Now, of course, we talked about if I plugged in 1, we don't know what's happening here, right? This is indeterminate, so we have no idea. So now let's look at what this function might be approaching as we approach from the right. So we're going to be a little bit bigger than 1. So let's say that in this case we do 1.0001, 1.001, and 1.01. So we'll do the same sort of operation. We're starting, fairly close, and we're getting closer, and let's see what happens. So at 1.01, if I plug this value into this function, I will get 0.49751. If I plug in 1.001, I would get 0.49975. If I plugged in 1.0001, I would get 0.49997. So what's happening as I approach from the right? Well, from the left, it appears that we are approaching 5. As I approach from the right, it also looks like we are approaching 5. So in this case, the limit from the left and the right is 5 for both of them. So we would say the limit as x approaches 1 is equal to 5. As we approach from the left, it's approaching the value 5. As we approach from the right, it's going to the value 5. Therefore, the limit as x approaches 1 will be equal to 5, even though we cannot plug 1 into this function. So we don't actually have a value there, but we do approach 1. So this would look something like we were talking about, where in this case, it's just a little above 5, this one's a little below 5. So it might look something like this, where this would be at x equals 1, right? We can approach this value from both sides, but we never actually can be that value. So now what we're going to do is we're going to look at it analytically to see if this matches. Now, one quick correction I want to make. I forgot to put my decimal here. So this, every time I said 5, it should have been 0.5, but not a big deal. The whole thing stands, right? It was going towards, it was 0.5002, 0.50002. The other one was 0.499. So these were 0.5. So now what we want to do is we want to see, can we confirm this analytically, right? Because a lot of times you don't really want to plug in a bunch of numbers because it's kind of tedious, and if we can just solve for it, then why wouldn't we? So I'm going to rewrite my limit here. We have the limit as x approaches 1, and this was x minus 1 over x squared minus 1. And we talked about the fact that if I were to just plug in 1 into each of these x's, it would be 0 over 0, which is undefined. So now what we're going to do is we're going to first split this into its separate components, right? We have x squared minus 1. So what we can do is we can actually change this to x minus 1 over, and the square of this would be x minus 1, x plus 1. Now you might wonder, how did I know to do this? Well, a lot of times your clue for a problem like this would be, if it looks like there's probably some connection between whatever's in the numerator and the denominator, and the bottom is one of them is a square, then it probably is going to end up with some cancellation for a lot of these kind of calculus problems. So in the fact that I had x minus 1 up here, I was looking at this term here with the square in it saying, okay, well, could this be some square terms, two terms multiplied by each other, that I just brought together into 1? So in this case, I just kind of basically figured it out by the fact that if I did x minus 1, x plus 1, I know that if I were to FOIL this out, I would get x squared, okay, good, minus x plus x, and then minus 1. So the plus x and the minus x would cancel, therefore it would leave me with x squared minus 1. So that looks good. So now in this case, because I have x minus 1 at the top and the bottom, the numerator and the denominator, I'm going to cancel these out, and I'm going to be left with the limit as x approaches 1, 1 over x plus 1. Now, if I were to plug in 1 at this point, what happens? Well, I take the limit of 1. This is just going to be limit of a constant is constant, so this is 1. Plug in 1 to this, I get 1 plus 1 equals 1 half. Well, 1 half can also be written as 0.5. So we've actually shown that this function does, in fact, approach 0.5 whenever we are approaching x equals 1, taking the limit as x approaches 1 for this function. Right? And if we were to graph this, it looks something like this. Right, as x equals 1, we have that this is equal to 0.5. Sorry, it's open circle. And this would go off towards infinity. This would go off towards 0. And then we also have, at x equals -1, we have something like this. And this is because if I were to plug in -1, -1 minus 1 would be -2, but -1 squared becomes 1. 1 minus 1, we'd still end up with a 0 denominator. So in this case, we actually have a point that we couldn't approach either if we were coming from the left or the right here. But the reason I wanted to show this is because in this case, we're not worried about the rest of this function. We're only looking at right around here where a equals 1. We're looking at what happens as x approaches from both the left and the right. So for our next example, we're going to be looking at the limit as x approaches 0. Now in the slide, you'll see that it says pi over x. This was actually a typo. It should have been sine of pi over x. So in this case, we're going to, again, see what happens as we plug in our different x values and what outcome we get for our function at that x, right? So we're going to be looking at x and f of x. So if I were to just start with 1, because I want to approach 0, let's start at 1 and we're going to move back towards 0. And let's say that I plugged in 1 here. I would get sine of pi over 1. So sine of pi, this is going to be equal to 0. Now let's say that instead I decided to do 1 half. I'm going to take half the distance from that. Well, if I take pi over 1 half, this is the same thing as saying pi over 1 divided by 1 over 2. You fractional division, this becomes the sine of 2 pi. Well, sine of 2 pi is equal to 0. Well, what about if I did 1/3? It would be the same thing. In this case, it would be the sine of 3 pi, which is equal to 0. If I did 1/4, it would be equal to 0. If I did 1/10, it would be equal to 0. Or even if I did 1 over 100, it would equal to 0. So basically, if I have this fraction where each time I'm putting in 1 over some natural number, what's going to happen is it's always going to end up being that natural number times pi, which sine of that will always be equal to 0. So if you looked at this, you might say, okay, well, it just seems like the answer is 0. And if we actually look at the visual of this, though, what does it look like happening in the graph? Well, you can see that it's actually cycling between -1 and +1, -1, +1, -1, +1, and it's doing this over and over again. It's just we happen to be picking values where it was always hitting where our function f of x was equal to 0. And this is actually one of the issues you might run into if you're trying to do it numerically by picking numbers, because a lot of times when we're picking numbers, we will sort of arbitrarily pick some numbers a little bit away from that value that we're getting the limit for, and then we'll get closer and closer and closer and closer. But if you see behavior like this, well then, what does this mean? Does it mean that it converges to 0? No, not in this case. So in this case, because we know now looking at the image, the graph of this, that it's going from -1 to +1, we would have that this limit does not exist. So DNE does not exist because it's divergent, meaning that it doesn't converge on a specific value L. So now let's talk about our one-sided limits. So I've actually been kind of briefly mentioning this while kind of explaining limits as x approaches some value a, but let's formally define what these are now. So a left-hand limit is written as the limit as x approaches a with a little negative sign, f of x equals L. This means that our function f of x will approach that value L as x approaches a from the left side. That is to say that when x is less than a. The right-hand limit is written as the limit as x approaches a with a little plus on the function f of x will be equal to L. This means that our function f of x will approach L as x approaches a from the right. That is when x is greater than a. So there's one little typo in the slide, which is it should be x approaches a, like I said, not a approaches x like the slide shows. So for our next example, we're going to be looking at the limit as x approaches 0, and this will be 1 over x squared. if it exists. So the first thing we do is always just do a quick check. If I were to plug 0 into this, what would I get? I would get 0 squared at the denominator, which is 0. 1 over 0 is undefined, so therefore it can't be 0. So we're going to look at what happens as we approach from the left and from the right. Well, in this case, we have our x, we have our f of x. If I were to plug in plus or minus 1, right, because it's squared. So no matter what value I plug in for the negative or the positive, it's going to have the same outcome because this is an even function. If I plug in 2, it'd be 1 over 2 squared. If I plug in negative 2, it'd be 1 over negative 2 squared, which would still both be 1 over 4. So if I plug in 1 or negative 1 into this, I end up getting 1. If I were to plug in, right, because we want to get closer to 0. So if I plug in 0.5, then this would be 0.5 squared, which is 0.25. 1 divided by 0.25 is going to give me 4. If I plug in 0.2, I would get 25. If I plug in 0.1, I would get 100. So what's happening with this function as I'm approaching 0? Well, it appears that the value is getting bigger and bigger and bigger, and it's growing a lot faster as I get closer and closer to 0. Which, if then, in that case, it looks like from the left and from the right, it approaches infinity. Now, there's going to be times where your left value from the left does not match what is occurring from the right. In this case, we would say that limit does not exist. But in this case, a limit does exist. It's just that it diverges to positive infinity. No matter what value I plug in here, the closer I get to 0. So this would look something like this, right? I have this at 0. I know that whatever I have is going to go bigger and bigger and bigger, never touching at x equals 0. So it might look something like this. And we kind of briefly showed an example of something like this before, which was 1 over x squared. And here on the slide, you can just see an image of what I just drew on the board. So our vertical asymptote of f of x equals 1 over x squared is at x equals 1. We have an asymptote here, meaning that it will approach, but it can never actually touch that value. So therefore, even though we have that the limit approaches infinity, we would have for a specific limit that this does not exist. A limit L does not exist for limit as x approaches 0, 1 over x squared. Now looking at this example, you're going to see that we have a graph, but we don't have the actual equation for what the function is that defines this graph. So now normally I would actually have some sort of scale so you know exactly what these values are, but we're just going to kind of estimate it for the point of the example. So looking at this image here, we have that as we go to the left, it looks like it's kind of going down towards negative infinity. We're going to reach a certain point coming to the right where it's going to be included in the function, and then it's going to make a jump downward, but just not included. And then from there, it's going to increase until it hits a point that it cannot be, and then it's going to continue by going down and then approaching some possible value or maybe coming back up. I don't 100% know. But I'm not looking at the behavior as it goes to infinity. I want to look at it at specific points. So the first part is, what is the limit as x approaches 2 from the left on our function? So I'm guessing that's where that point is, where there's the dot and then the jump. So as it approaches from the left, it looks like it approaches some value of, I'm going to say 3 or 4. Okay, I had 3 for this example. What is the behavior then for when it approaches from the right? So the next one over, it says 2 from the left, but it should be from the right. Well, in this case, it looks like if I'm coming from the right, I'm probably approaching some value around 1. If I look at what is the function at x equals 2, right? So if I were to look at f of 2, I know that because the dot is at the top, that is what the value would be. So when I have f of 2, this should be equal to, in this case, 3. But what is the limit as I approach from the left and from the right? Well, they don't have a specific limit where both are approaching. So in this case, the limit does not exist. So if I just said, what is the limit as x approaches 2? The answer is does not exist because the left side limit, 3, does not equal the right side limit, 1. The next question is, what is the limit as x approaches 4, which is where that next hole is? Well, in this case, if the first one we were at was 3, I'm going to assume that this one I had written as 4, which means that from the left, I'm approaching and I'm getting 4. From the right, I'm also getting 4. So therefore, in this case, the limit would be equal to 4 because the limit from the left is equal to the limit from the right. So in this case, we get 4. Now, what is the value of the function at 4? Well, the fact that I have an open circle means that a value does not exist at x equals 4. So therefore, the answer would be does not exist. So in the previous example, we had a graph, but we didn't know what the function was that actually described it. So what we were doing is we were using the graph to try to say what the behavior was at specific points, at the limits for them as they approach specific points based on that function. Well, what about if we went the other direction? We now have the outcomes of different limits on our functions, and we want to draw a graph. So the first thing I'm going to do is I'm going to draw my x, y axes. So I've got my y, I've got my x. Now, before I begin, first thing I'm going to do is I'm going to quickly look through these to see where I'm actually going to be doing my limits to try to figure out where I need to kind of focus. So the first one looks like we're approaching limit as x equals 1. So I'm going to put a line right here to represent 1. The second limit, it looks like second and third limit, it looks like I'm approaching 0 from the left and the right. So that means that I know something's going to happen here to the left and to the right of this value. And then we're going to look at as x goes to infinity and as x goes to negative infinity. So first thing, let's look at our limit as x approaches 1. So this line right here, f of x. And we have that it approaches infinity. Now notice this does not have a plus or minus next to it. This means that we are not taking the limit from the left or from the right. If a limit exists, so as the limit as x approaches 1, it means that both the left and the right are approaching the same value. And in this case, it looks like both are approaching infinity. So this means that we have an asymptote here where we have, from the left, it's approaching infinity. From the right, it's approaching infinity. Now, let's look at what's happening around 0. So we have the limit as x approaches 0 from the right. So if we look at 0 is here, as we're approaching from the right, that's this side. And we have that it's approaching negative infinity. So if I were to then make that happen, looks something like this. So as it approaches 1, from the left, it's going to infinity. As it's approaching 0 from the right, it's approaching negative infinity. For my limit as x approaches infinity from the left, I also have that it is approaching negative infinity. My limit as x approaches infinity off to this direction is that it's going to go towards negative infinity. So that means that maybe it does something like this. I don't know exactly what the behavior is, right? We don't know the function. We don't know how fast it's decreasing. We don't know if it's hitting a certain point and going linear. We don't know if it's, doing something like this where it curves and then goes straight down. We don't know if it just kind of is sloping down. All I know is it's going towards negative infinity. And then my last one is, what about when my limit as x approaches negative infinity? Well, in this case, it says it's approaching 0, which means that as I go further and further to the left, I'm going to approach 0, but I'm never going to touch it. So now I have a graph that looks something like this. And looking at the slide, you can kind of see that it matches in general what I was drawing. Now, because we don't have these specific values, for example, as x approaches infinity, because I don't have the actual function, I don't know how it's decreasing to negative infinity. I just know that it is decreasing. So I drew it kind of slanted, whereas on the first graph I drew on the slide, I drew it more like what was on the other side of 1. Now let's formally define what a limit is. So we're going to say, let f be a function defined on some open interval that contains a number a, except possibly a itself, right? We looked at a case of this where we approach a, but we don't actually have the value a itself. Then the limit as x approaches a, so f of x equals L, if for every number epsilon is greater than 0, there's a corresponding delta that's greater than 0, such that if I have 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus the limit L is going to be less than that epsilon, which is the distance between the limit and the function. So what does this actually mean in practice? Well, what we're saying is this, is that let's say that we have some function, right? So let me draw my x and y axis. And let's say that I have some a right here. And my function is doing something. There might be a hole at a, there might not be. And pretty much what we're saying is that I have the limit as x approaches a on some function f of x, and this is equal to L. This is the limit. This is what I'm actually approaching, whether it's included or it's not. This is the value that I'm actually approaching from the left and from the right. What we're saying is that the distance from where my x value is, so this value here is x minus a, and then we're taking the absolute value of that, because whether we're approaching from the left or from the right, in this case, it would be same thing. It would be the negative of this. So this is actually going to be a minus x, and this would be x minus a. Either way, though, the distance, whether we're coming from the left or the right, if I take the absolute value of that, so the distance from my actual, where I'm located on the x-axis, minus how far away, so basically this is the distance from A that I am. If this is greater than 0, meaning I'm not on A, but it's less than some delta, this delta just represents some threshold value, then this says that my function, because remember, wherever I am on x, this is going to be f of x. This value that's on my line is going to be where I'm actually located. So what this is saying is that the function f of L in this case, which is going to be, or f of x is going to be based on some distance between f of x and my value L, which is based on the limit it is. So we have f of x minus L, and again, I could be above, I could be below, depending on what the limit is and the direction of all that kind of stuff. So the absolute value of this will be less than some epsilon. So this is what the formal definition is of a limit, that basically that as I am away from A and I'm getting closer and closer, that there exists some threshold where I'm greater than 0, but I'm below some threshold value, which is represented by delta. And with that, I will have some distance that is a measurement of how far away I am at f of x from that limit that I'm approaching, which will be less than epsilon. And we'll use this if you were formally sort of proving different things about calculus. This is actually very important to that. Now, for this course, we're focusing more on the actual calculation and how to use calculus. So in this case, we won't really be looking at this unless we decide later on to look at more formal analysis. Let's say, though, that we actually did want to use it just for a really quick proof to show that the limit as x approaches 3, 4x minus 5 is equal to 7. So in this case, what we're saying is that we want to have some epsilon, which is greater than 0, right? Because we said that our absolute value of x minus a has to be between 0 and epsilon, meaning that our epsilon also has to be greater than 0. We have that our limit a, so this a equals 3, this is the limit that we're approaching. Our limit that we actually are getting when we approach a from the left and the right is equal to 7. Then what we need is for delta to be such that 0 less than the absolute value of x minus 3, because that's x minus a, we plug in 3 for our a, is less than delta. Then our absolute value of our f of x, 4x minus 5, minus the limit L, is less than that epsilon value. So remember, what we're saying is this, is that we had 0 is less than the absolute value of x minus a, is less than epsilon, and we had the absolute value of f of x minus my limit L is less than delta. And in this case, we have a is equal to 3, we have L is equal to 7, and we have f of x is equal to 4x minus 5, right? Because our original limit was the limit as x approaches 3, 4x minus 5 equals 7. So what we're doing is we're starting with the fact that we're going to be looking at the absolute value of this here, right? So we have 4x minus 5 minus L, which we said was 7, and we have that this is going to be less than some delta. So we start with the absolute value of 4x minus 5 minus 7, which is going to be absolute value of 4x minus 12 is less than delta. So now what we're going to do is we're going to focus on this here, and we're going to plug f of x in, so 4x minus 5 into f of x. We're going to plug 7 into L, and we will have that 4x minus 5 minus 7 for L is going to be less than our epsilon. So minus 5 minus 7 is going to be absolute value of 4x minus 12 is less than epsilon. Now, the fact is both of these terms have a 4 in them, which the absolute value of 4 is just 4. So I can actually pull this 4 out of my absolute value. So this is going to be 4 is absolute value of x minus 3 is going to be less than epsilon. So then in this case, I'm going to divide by 4. So I'm going to get absolute value of x minus 3 is going to be less than epsilon over 4, which then going back to this here, we have x minus a, which we said a was equal to 3. So we have x minus 3, and the absolute value, which is this, is less than delta. So now going back, we have absolute value of x minus 3, which if you look up here matches with this. Absolute value of x minus a. So we plugged in a is 3 based on what we had. So we have absolute value of x minus 3 is less than delta. Well, we have the absolute value of x minus 3 is less than epsilon over 4. So therefore, we have that delta is equal to epsilon over 4. Similarly, what if we wanted to show the limit that x approaches 0 from the right, square root of x is equal to 0. Now you might wonder, why are we specifically doing the limit from the right? Well, because if we plugged in values to the left of 0, that would be a negative, and we'd have a negative in the square root, in which case it would be complex issues. So we're just going to focus on the limit from the right. So we're going to start with the same stuff we did before. Well, in this case, our a is going to be equal to 0. Our L is going to also be 0. So then kind of doing what we did here, we have f of x is equal to the square root of x. So we're going to take the absolute value of f of x minus L. So we're going to take the absolute value of square root of x minus 0. And then this is going to be less than our epsilon e. Now, in this case, square root of x minus 0 is the same thing as just saying square root of x. So this is going to be equal to absolute value of square root of x is less than epsilon. Now, because we're taking the limit only from the right, this means that we can only have positive values. So the absolute value of square root of x is the same thing as just saying, in this case, the square root of x. So we have the square root of x is less than epsilon. So then if we wanted to isolate our x, we're going to square both sides. We would get that x is less than epsilon squared. So in this case, because we're looking at this, our absolute value of x minus a, which we just said is equal to x in this case, because with the steps we just did here, this is going to be less than our delta. Well, this means that our delta is equal to epsilon squared. Now, we're not going to do much more with this. I just wanted to kind of briefly show you the idea behind the formal definition of a limit, but we're going to be mostly focusing on, going forward, applications, how to solve them, different rules, and things like that, and then build out till we get to derivatives, integration, things like that. Hello everyone. In today's lesson, we're going to be looking at algebraic methods for calculating limits. To begin with, we're going to be looking at the limit laws. So our first limit law says that if we have the limit as x approaches a for two functions, f of x plus or minus g of x, this will be equal to, so we have the limit as x approaches a for f of x plus or minus g of x, then this will be the same thing as the limit as x approaches a on f of x plus or minus the limit as x approaches some value a on g of x. Our second limit law says that if we have the limit as x approaches some value a and it is some constant times our function f of x, this is going to be equal to c times the limit as x approaches a on our function f of x. Our third limit law is that if we have the limit as x approaches a and we have some function f of x and then times some function g of x, this is the same thing as the limit as x approaches a function f of x times the limit as x approaches a on g of x. If we have the limit as x approaches a for our function f of x divided by the function g of x, this is equivalent to the limit as x approaches a on our function f of x divided by the limit as x approaches a on the function g of x. Now, this is specifically if the limit as x approaches a on g of x does not equal to 0, because in that case we would have our fraction would have a 0 in the denominator. So this implies that the limit as x approaches a on g of x cannot be equal to 0. Then we have the limit law. If we have the limit as x approaches a, if we have our function f of x and we take this entire thing to a power, let's say n, this will be equivalent to the limit as x approaches a on our function f of x, the entire thing, including the limit, to the power n. And this is for when n are positive integers. We also have the limit as x approaches some value a on a constant c will just be equal to that constant c. We have the limit as x approaches a on some variable x. This will be equal to that constant a. If we have the limit as x approaches a, x to the n, this is equal to a to the n. Because what's happening here is that if you have x to the n, this is the same thing as taking the limit as x approaches a on x, taking the whole thing to the nth power. We said limit as x approaches a on x is equal to a, so this should just be a to that power. We have the limit as x approaches a, nth root of x, and this is equally going to be, just like before, it's going to be the nth root of whatever that value a is, where n has to be a positive integer. Just like before, if we have the limit as x approaches a on some function f of x, and we're taking the nth root, this is the same thing as taking the nth root of our limit as x approaches a on our function f of x. And this is because, again, our nth root is the same thing as just saying a function of x to some power, just like we did here. The only difference, though, is instead of being to the nth power, where n is a positive integer, now we would have that n is some fraction integer. So it'd be like saying limit of x approaches a, f of x to the 1 over n power, in which case we could take the 1 over n power of the entire thing, so it ends up being the equivalent rule. Our next definition is that if we have the limit as x approaches a on some function f of x is equal to L, which, if you remember, this is our definition of a limit. This is true if and only if the limit as x approaches a from the left side on f of x is equal to L, and the limit as x approaches a from the right side is equal to L. And this is because we are going to have to consider left side limits and right side limits. So the limit itself, this statement is only true if both approaching from the left and the right are converging on this same value L. So if f of x is a continuous function, then the limit as x approaches a, f of x equals f of a. So that is to say, if we have a continuous function, then the limit as x approaches a, f of x will be equal to our function at a. And this is called our direct substitution property. So what this means is this definition here is true if it's approaching some value L, even if it cannot be that value. So this might be something like if you have some function, you have a whole, let's say, and then something like this. Or if you have something like this, and instead maybe for some reason it jumps here, or something like that. In which case, both of these would be true because from the left and from the right, we are approaching the same limit. This is saying that if we have some continuous function, meaning there's no whole, that is, as I'm approaching from the left and as I'm approaching from the right with f of x, this would be the same thing as the specific point, the function at a. This is called our direct substitution property. So now that we have all these rules, let's do some examples to see how they hold up based on different scenarios. So let's say that given we have the limit as x approaches 3, so this is our a in this case, on our function f of x is equal to 1, we've got the limit as x approaches 3 for g of x is equal to -2, and our limit as x approaches 3 for h of x is equal to 0. So we have 3 different functions, and we're looking at what happens with each of them as we approach, using the limit, as we approach 3. So the first question then is, what would the limit as x approaches 3 on f of x plus 3g of x be? So what I'm going to do is I'm going to break this down by focusing on doing every single one of our limit rules as we do this. So the first thing I'm going to look at is the fact that when I have the limit of some function f of x plus or minus some function g of x, I can actually rewrite this as the limit of the first function plus or minus the limit of the second function. So this is going to be equal to the limit as x approaches 3 f of x plus the limit as x approaches 3 times g of x. Now what we're going to do is we are going to use our property where if we have the limit of some constant times a function, this is the same thing as the constant times the limit of the function. So this then becomes the limit as x approaches 3 f of x plus 3 times the limit as x approaches 3 g of x. And now with this, we can actually solve for this because we know that the limit as x approaches 3 on f of x is equal to 1. And then so plus 3 times the limit as x approaches 3 for g of x is equal to negative 2. So we are left with 1 plus 3 times negative 2. 3 times negative 2 is equal to negative 6. So 1 minus 6 would give us negative 5. So next what we're going to do is we're going to look at what if I have the limit as x approaches 3 for g of x cubed. So this is going to be using the property where this is the same thing as saying the limit as x approaches 3 on g of x all cubed. So we said the limit as x approaches 3 g of x is equal to negative 2. So this is equal to negative 2 cubed, which is equal to negative 2 times negative 2 is positive 4. Positive 4 times negative 2 gives us negative 8. And then for our third example, we have the limit as x approaches 3 square root of f of x. And again, this rule was that if we had the square root of f of x and we're taking the limit of that, that's the same thing as saying we're taking the limit as x approaches 3 on our function f of x, and we will take the square root of the entire thing. Well, the limit as x approaches 3 f of x we said was equal to 1, so this is equal to the square root of 1, which is equal to 1. And looking here at the slides, you can actually see that this agrees with exactly what we did in these three problems. Next, we're going to be looking at the limit as x approaches 3 to f of x divided by g of x, the limit as x approaches 3, g of x over h of x, and the limit as x approaches 3, g of x times hx divided by fx. So we'll start with the first one, where we have the limit as x approaches 3, 2 times f of x divided by g of x. Now, as before, this would be equal to the limit of the numerator divided by the limit of the denominator. So we have the limit as x approaches 3, 2 times f of x divided by the limit as x approaches 3, g of x. Now this limit as x approaches 3 g of x, we're good to go on that one, but here we have some constant, right? This is not the same thing we have written here. We have limit as x approaches 3 f of x. We don't have limit as x approaches 3 2 f of x. So what we're going to do is we're going to use our property where we can pull this constant out. This is going to be equal to 2 times the limit as x approaches 3 f of x divided by the limit as x approaches 3 g of x. So in this case, this is going to be equal to 2 times the limit as x approaches 3 f of x is equal to 1, and the limit as x approaches 3 g of x is equal to negative 2. This gives us 2 over negative 2, which is equal to negative 1. For the next one, we have the limit as x approaches 3 g of x divided by h of x. So in this case, when we have the limit of a fraction, this is just going to be the limit as x approaches 3 g of x divided by the limit as x approaches 3 h of x. Now in this case, we actually have both of these terms here. So the limit as x approaches 3 for g of x is just going to be equal to negative 2. The limit as x approaches 3 hx is going to be equal to 0. So in this case, we can't do this operation because we have the limit as x approaches 3 hx equals to 0, which gives us a 0 in the denominator, which means that this one does not exist. So what we might have to do in this case is if we wanted to try this, if we knew anything else about this function at hx, we could possibly look at what is happening as we approach 3 from the left side, what is happening as we approach 3 from the right side, and then from there we might be able to get its limit. So for the last one, we have the limit as x approaches 3. We have gx hx divided by f of x. So this is going to be equal to the limit as x approaches 3 of my numerator. So this will be gx times hx divided by the limit as x approaches 3 f of x. Now this top one, I can't take the limit as x approaches 3 gx times hx. So what I'm going to do is I'm going to use my property where the limit of one function times another function is the same thing as the limit of the first function times the limit of the second function. So this is going to be equal to the limit as x approaches 3 gx times the limit as x approaches 3 hx divided by the limit as x approaches 3 f of x. Now this I can solve because the limit for g of x is equal to -2 times the limit of hx is equal to 0, and then the limit of f of x is equal to 1. So this would give me -2 times 0 is 0 divided by 1, which is equal to 0. So in looking at the slides, you can see that this matches exactly what we got when we were working this out together. For our next example, we want to evaluate the limit as x approaches 5 for 2x squared minus 3x plus 4. Now we're going to be using the property where we have the limit of some function plus or minus some other function, but in this case we have 3 functions. Well, this still works. It follows the same trend, so this is going to end up being the limit as x approaches 5, 2x squared, minus the limit as x approaches 5, 3x, plus the limit as x approaches 5, 4. Now again, we can solve some of these, but not all of them. And again, I don't want to skip any steps because I don't want anyone to wonder how we got to any particular point. So what I'm going to do now is this one, we have a constant times x squared. So I'm going to pull that constant out first. So this is going to end up being the limit as x approaches 5. I'm going to pull that 2 out, so this will be 2 times that limit, x squared. Minus, again, I have a constant, so I'm going to pull that constant out, 3 times the limit as x approaches 5, x, and then plus, I can actually just evaluate this one now, and I'm going to do it to save myself from writing. The limit as x approaches 5 on some constant is just going to be the constant. So this is going to be plus 4. Now this one, we're actually good to go. 3 times the limit as x approaches 5 on x. This one though, we have x squared. So what we're going to do is we're going to use the property where if we have the limit of x to some power, it's the same thing as whatever the limit of x would be to that power. So this is going to be equal to 2 times the limit as x approaches 5 on x, and then I'm going to square whatever this would be. And then minus, I'm going to leave this the same for now, limit as x approaches 5 plus 4. And now that we have it in this form, we can actually solve for this by doing our direct substitution method. Can I plug in the limit as x approaches 5 on the function x? Well, yes, we just said that the limit as x approaches some a, x would be equal to that value a. So this is going to be equal to 2 times 5 squared minus 3 times the limit as x approaches 5 to x is going to be 5, so this is going to be minus 3 times 5, and then plus 4. So 5 squared is going to be 25. 25 times 2 is going to be equal to 50, minus 3 times 5 is going to be 15, plus 4. So negative 15 plus 4 is the same thing as saying negative 11. 50 minus negative 11 is going to give us 39. And then looking here at the slides, you can see that this agrees with exactly what we did. For our next example, what we want to do is we want to evaluate the limit as x approaches -2, and we're going to have our numerator of our fraction is going to be x cubed plus 2x squared minus 1 divided by 5 minus 3x. First thing we're going to do, I'm going to take this as the limit of the numerator divided by the limit of the denominator. So this is going to be the limit as x approaches negative 2, x cubed plus 2x squared minus 1 divided by the limit as x approaches negative 2, 5 minus 3x. Then I'm going to take that limit and I'm going to apply it to every single function within our numerator and denominator. So this is going to be the limit as x approaches negative 2, x cubed, plus the limit as x approaches negative 2, 2x squared, minus the limit as x approaches negative 2, negative 1, divided by the limit as x approaches negative 2, 5, minus the limit as x approaches negative 2, 3x. So now we have a lot to do on this one. So in this case, I'm going to talk through every step, but I might skip a few steps just to make it a little bit faster. So this first one, we have the limit as x approaches negative 2, x cubed. We can take this as the limit as x approaches negative 2 on x, and we can cube the entire thing. For this next one, we have a constant that we can pull out. So I'm going to do that first. So this is going to be plus 2. And then I have the limit as x approaches negative 2, x squared. So this is the same thing as if I took the limit as x approaches negative 2, x, and then I'm going to square the entire thing. And as for this next one, it's minus the limit of a constant, which means it's just going to be that constant. So plus 1. Divided by, now this one, again, we have the limit of a constant. So this is just going to be equal to that constant. So this is going to be 5. Minus, this one has a constant in front of our x. So we're going to pull that constant out. So we're going to get minus 3 limit as x approaches negative 2, x. So now that all of our limits are in terms of x, we can actually evaluate this. So doing this, we're going to have the limit as x approaches negative 2, x is going to be negative 2. So negative 2 cubed is going to be negative 2 times negative 2 is positive 4. Positive 4 times negative 2 is going to be negative 8. The next thing we have is plus 2 times, we have limit as x approaches negative 2. This is going to give us negative 2. Squared is going to give us positive 4. And this is going to be plus 1. In our denominator, this constant is still 5, minus 3 times the limit as x approaches negative 2 on x is going to be negative 2. So this gives us negative 8 plus 2 times 4, which is equal to 8. So negative 8 plus 8 is going to be 0, plus 1 will leave us with 1 in the numerator. 5 minus 3 times negative 2. So 3 times negative 2 is negative 6. So 5 minus negative 6, same thing as saying 5 plus 6, which is going to give us 11. So this would give us 1 over 11. For our next example, we're looking at what is the limit as x approaches 1, x squared minus 1 over x minus 1. First thing I'm going to do is I'm going to first break this down just like we did before, and I'm going to be a little bit quicker on some of these just because now that we've kind of been talking through the rules, we're going to look at can we do it without necessarily showing every single step. So this might be the limit as x approaches 1 on x squared minus 1, and this will be over the limit as x approaches 1, x minus 1. Now if we were to split this, we're going to end up with the limit as x approaches 1, x squared, so this is going to be the limit on x, the whole thing is going to be squared, minus the limit as x approaches 1, negative 1, divided by the limit as x approaches 1, x minus the limit as x approaches 1, plus 1, because I pulled the negative out. So now if we were to evaluate this, if I were to plug in 1 here, I would get 1 squared. So this is going to be equal to 1 minus, I also did the same mistake earlier. This should be plus 1 because I pulled that minus out. So in this case would be minus 1 divided by the limit as x approaches 1 on x is going to be 1, and then again, minus 1. This is going to give me 0 over 0, which means that this does not exist. Now, this is actually what's called an indeterminate form, which we actually will look at a method we can use to solve this later on in the course. But one thing that we can do currently is we could try to see, is there anything we could do to do some cancellation? So let's look at this x squared minus 1 here. So if we were to break this down into x squared minus 1, what could we multiply to give us negative 1, and then adds up together to cancel out to give 0? And this would be equal to x minus 1, x plus 1. Now, if we did this, right, if we FOILed this out, first would give us x squared minus x, outer would be plus x, and then inner, or last would be negative 1. So the plus x and minus x would cancel. This would leave us with x squared minus 1. So now rewriting this using that, we could have the limit as x approaches 1, x minus 1, x plus 1 divided by x minus 1. Now, if we look at this, you might notice that we have x minus 1 on the top and the bottom, meaning that we can actually cancel these out. And now what we're looking at is the limit as x approaches 1, x plus 1, which then using our limit rules would be the limit as x approaches 1, x plus the limit as x approaches 1, 1, and this would be equal to 1 plus 1, or 2. And then looking at our slides here, you can see that this matches exactly what we did. Now again, I did break down the steps a little bit more, but you can still see that it follows exactly what's on the slides. Now what we're going to do is we're going to look at what if we were to take the limit of a piecewise function. So we're going to look at if we have limit as x approaches 1, g of x, where this is going to be equal to x plus 1 if x is not equal to 1, and this is going to be equal to pi if x is equal to 1. So now what we have to do is we actually have to consider as the limit as x approaches 1 is going to be which of these? Well, remember, when we're approaching 1, this means that we're not at 1, meaning we're going to be focusing on this when x is not equal to 1. So this means that we would have the limit as x approaches 1, x plus 1, which is just going to be the limit as x approaches 1, x plus the limit as x approaches 1 on 1. This is going to be equal to 1 plus 1 equals 2. Now, if f of x equals g of x when x is not equal to a, then the limit as x approaches a, f of x, is equal to the limit as x approaches a, g of x. So pretty much what's happening in this case is that we have some function, x plus 1, right? So it's going like this. And then suddenly at 1, where if we were to try to plug this in, we'd get 2, but it actually jumps up to pi, which means it would be above. It looks something like this. Now, one thing I want to point out is if we have some function, f of x, that is equal to g of x when x is not equal to a, then if we take that limit as x approaches a on that function f of x, this is going to be equal to the limit as x approaches a on that g of x. This means that if our functions are equal when they do not have x equal to a, then our limit is going to be whatever the limit on that function would be as x approaches a. Next, we're going to look at what is the limit as h approaches 0 for 3 plus h squared minus 9 divided by h. So if we were to first look at our substitution method, let's say we substitute 0 in for everywhere we have h. This would be 3 plus 0, which is 3, squared would give us 9. So 9 minus 9 is equal to 0. Divided by 0, this would give us 0 over 0, which again is indeterminate. So this leads us to, if we're going to be able to solve this, not using the method we'll look at later on called L'Hopital's rule, then we need to probably look to see if there's some sort of cancellation we can do. So because we have 3 plus h squared, what I'm going to do is I'm actually going to expand that out, and this is going to be the limit as h approaches 0, and then I'm going to do my first term. So first is going to be 3 times 3, outer, which is going to be 3 times h, so this is going to be plus 3h, inner, which again is going to be plus 3h, and then last is going to be plus h squared. And then I still have that minus 9 divided by h. Now, just a reminder, when I said that I'm expanding this out, I'm basically doing this. It's 3 plus h times 3 plus h, and then I'm multiplying the first terms, the outer terms, the inner terms, and then the last terms, and that's where this came from. So I had this turn into this here, and then I brought the minus 9 down. So now we're going to see, is there anything we can do for some cancellation? So I can actually rewrite this as, first of all, negative 9 and positive 9 are going to cancel. And you'll notice we have 3h plus 3h plus h squared. So this is going to be the same thing as saying 6h plus h squared divided by h. And then we're taking the limit on that as h approaches 0. Now, if we were to try to substitute now, we'd still get 0 over 0, right? Because we get 0 plus 0 divided by 0. So that still doesn't work. So now what I'm going to do is I'm going to look at, is there any cancellation I can do? And I can, because every one of these terms has an h in it. So this would be the same thing as taking the limit as h approaches 0. I'm going to pull an h out of the numerator. So this is going to be 6 plus h divided by h. These h's will cancel, and this will just leave me with the limit as h approaches 0, 6 plus h. Now I can do my substitution, plug in 0 for h, and I'm left with 6. What about if I wanted to take the limit as x approaches 0 for the absolute value of x? And we're going to say this is equal to 0. So what we have to do is we actually have to consider that when we take the absolute value, this is a piecewise function, because if you remember, the graph of an absolute value looks like this. Any value that is greater than 0 will just be that value. Any value that is less than 0 will be the positive equivalent of that value. So this means that what we're doing is when we take the limit as x approaches 0 on the absolute value of x, this is going to be equal to the limit as x approaches 0, where it's going to be x if our x is greater than or equal to 0, and it's going to be negative x if our x is less than 0. So what we're going to do is we're actually going to look at the limit from both sides to prove that this is true. Because remember, our idea is that if we have the limit from the left is equal to the limit from the right, and they're both equal to that 0, this statement would be true. So let's start by looking from the left. So we have the limit as x approaches 0. Now, because we're coming from the left, I'm going to put a little minus sign here. Now, because we're coming from the left of 0, that means we have a negative number, meaning we're going to be using this function here, negative x. So this is pretty simple to solve. You could think of this as negative 1 times x. You could pull that negative 1 out, and this is going to be the same thing as saying the negative limit of x as x approaches 0. Now, as x approaches 0, the limit of x is going to be 0. Negative 0 is just going to be equal to 0. Now, what about if we approach from the right side? So now we're going to have the limit as x approaches 0 from the right side. Now, if we're approaching from the right, that means we have a positive value, which means that it's just going to be the function x. So the limit as x approaches 0 for x is just going to be 0. So the fact that these two are equivalent, this does mean that this statement is true, that the limit as x approaches 0 for the absolute value of x is equal to 0. So we've actually shown that this is true by looking at the limit from the left side and the limit from the right side, breaking this into a piecewise function of what's happening on the left of 0 and what's happening to the right of 0. Next, what we want to do is we want to prove that the limit as x approaches 0, absolute value of x over x does not exist. So for this problem, again, we are going to be using the fact that if we have the absolute value of x, this is going to be equal to x if x is greater than or equal to 0, and negative x if x is less than 0. So we're actually going to be looking at it from two different sides. We're going to look at it as we approach from the left, and look at it as we approach from the right. So for the left, we're going to have the limit as x approaches 0 from the left, and this absolute value of x, if we're approaching from the left, is going to be equal to negative x over x. So before we actually take the limit, we have negative x over x, which if we cancel those out, we're just going to be left with the limit as x approaches 0 from the left on -1, which is going to be equal to -1. Now we're going to look at what happens if we approach as x approaches 0 from the right. Well, if we're approaching the right, this means we're coming from the positive side. This means that we are going to have our function as x over x, which of course this will just be equal to 1. The limit of 1 is going to be equal to 1. Now, because this limit as x approaches 0 from the left on our absolute value of x over x does not equal to the limit as x approaches 0 from the right, absolute value of x over x. Because these are not equal to each other, this means that the limit does not exist. And you can see that exactly here in the slide. Because -1 does not equal 1, therefore our limit does not exist. For our next example, we want to find the limit as x approaches -9, 2x plus 18 divided by the absolute value of x plus 9 if it exists. So the first thing I might look at is if I were to plug in -9, what's going to happen? Well, I get 2 times -9 is -18. -18 plus 18 is 0. And then if I plug -9 in here, I get -9 plus 9 is 0. Absolute value of 0 is 0. I have it dividing by 0, so that's not going to work. So what we're going to have to do is, again, we're going to have to look at breaking this into a piecewise function. So if you remember, what happens with our function by having that plus 9 in it is it's taking every value we have and it's shifting it to the left by 9. So instead of having our absolute value where it's around the origin, it's actually going to be the same thing, but around the point -9. So this means that, in this case, the absolute value of x minus 9 is going to be equal to x plus 9 when x is greater than or equal to -9, and it's going to be equal to minus x plus 9 when our x is less than -9. So all we've done is we've shifted by 9. So meaning if I were to plug in a -9 here, I would get -9 plus 9 would be 0. If I plug in any value that is greater than -9, for example, -8, I would get some positive value. If I were to plug in -9 into this, I would get -9 plus 9 is 0. Take the negative of that, so it would be -0. But if I get any value that's less than -9, let's say -10, I would have -10 plus 9 would be -1. Take the negative of that, get +1. So it's same idea, except for we've shifted over by 9 to the left. So what I'm going to do is I'm first going to break this down, again, into two limits. Limit as x approaches -9 from the left, and the limit as x approaches -9 from the right. So this is going to be, when I'm approaching from the left, this is 2x plus 18 divided by, now remember, from the left, this is going to be minus x plus 9. When I'm approaching from the right, this is going to be 2x plus 18, x plus 9. Now with this, we're able to solve both of these limits. So what do we do? Well, first things first, if I were to distribute this negative, if I were to plug in my -9, what's going to happen? So in this case, what I'm going to do is I'm going to pull a 2 out of this numerator. So I'm going to have the limit as x approaches -9 from the left, pull a 2 out, and I get x plus 9 divided by minus x plus 9. These x plus 9s will cancel, and I'll be left with 2 over -1, which is equal to 2. I'm going to do the same thing over here, and this is going to leave me with, so I'm just going to say this is 2x plus 9. This x plus 9 is going to cancel with this x plus 9. So this is going to leave me with the limit as x approaches -9 from the right is going to be 2 over 1, which is going to be equal to 2. So then comparing my limits, as I approach -9 from the left, I came to -2. As I approach -9 from the right, I got 2, which means that the limit does not exist. This statement is not true because it's not approaching the same value. Next, I want to introduce what's called Squeeze Theorem. So this says that if we have f of x, which is less than or equal to g of x, which is less than or equal to h of x, where x is very near a, and the limit as x approaches a on f of x is equal to the limit as x approaches a on h of x is equal to L, then that means that the limit as x approaches a for g of x has to also be L. So what this pretty much means is this. If I have, let's say, some function f of x, which is here. Let's say it approaches some value as x approaches a. We'll just say that a is right here. And if I have h of x, which is equal below here, and also approaching this a value. If I have some g of x, which is always between these two values, then as f of x approaches a and h of x approaches a, then this means that whatever g of x is, it will also have to approach that a as I take the limit L as x approaches a. Suppose that we have 3x minus 2 is less than or equal to our function f of x, which is less than or equal to x squared minus 3x plus 7. And we want to find the limit as x approaches 3 on f of x. So what we're actually going to be doing is we're going to be looking at the limit of our left side of our whatever function this is and the limit of our right side function, and we're going to see, do they actually converge on something, because we said that our function f of x is always between these two values. It's always greater than or equal to our first function, always less than or equal to our second function. So then if we were to take the limit as x approaches 3 on 3x minus 2, if I were to plug 3 into this using my direct substitution, this is going to be 3 times 3 is 9, minus 2 is going to be 7. And if I were to take my limit as x approaches 3 on this function, which is going to be x squared minus 3x plus 7, this means that if I were to plug this in, 3 squared is 9, 9 minus 3 times 3 is 9, so 9 minus 9 is 0, plus 7 is going to be equal to 7. So this means that the function that is below f of x, or equal to, converges to 7 as x approaches 3. The function that is greater than or equal to f of x also converges to 7 as we take the limit as x approaches 3. This means that because these two are equal and f of x has to be between these two functions, this means that the limit as x approaches 3, f of x is equal to 7. And looking at the slide, this is a lot of times the way we'll actually write it, is that we'll have our two functions, we'll take the limit of those two functions while leaving it in terms of the inequality, and then we'll solve for each of those, and if it's between these two values, that shows you where your limit as x approaches 3 for f of x has to be. Now, one thing I want to point out is that with our squeeze theorem, the idea is that if you have two functions that are one above, one below, as they come together, that means that it's going to squeeze that middle function, because this has to be true, into the same limit. Now, if for whatever reason you had some limits that were not equal to each other, but this one was greater, the larger function was greater than the smaller function, this would give you a range of values. So let's say that instead you had 3 is less than or equal, the limit as you take this is 3, limit as you take this is 4. That would mean that you know that the limit as x approaches 3, f of x would have to be something between 3 and 4. We don't know the exact limit, but we would at least have a range of possible limits. So now let's do another example where we have the limit as x approaches 0, x squared sine 1 over x. And we're going to check if this is equal to 0. We're going to show that this is true. So first thing I'm going to do is I'm going to consider that if I plugged in 0 in the denominator here, we know that this is just going to be undefined, therefore we can't just do our direct substitution. So what we're going to do is we're going to consider the fact that if I have some sine function, that I know that this has to be between -1 and +1, right? And because I have some value that is close to 0, meaning that it's less than 1 or greater than -1, and I'm squaring that, that means that this value is actually going to be making it smaller. So if I can show that -1 is less than or equal to sine 1 over x less than or equal to 1, if I can show that the limit as these two approaches 0, then I should be able to show that this is true. So looking at this, we have this statement is true because the sign of anything will be between -1 and 1. So this means that we have a limit on what our possible functions can be. Now, because we have x squared times this, what we're actually going to look at is we're going to say that, okay, well, if I multiply every one of these by x squared, this would be -x squared is less than or equal to x squared sine 1 over x is less than or equal to x squared. So now all I have to do is I have to see, is the limit as negative x squared and limit of x squared, as they approach 0, do they approach the same value? And if so, then that means that this would have to be squeezed into that same limit. So what I'm going to do is I'm going to take the limit as x approaches 0 on negative x squared less than or equal to the limit as x approaches 0, x squared sine 1 over x less than or equal to the limit as x approaches 0, x squared. Now, if I take the limit of negative x squared as x goes to 0, right, I can pull that negative out, same thing as multiplying by negative 1. So this would be negative, the limit as x approaches 0, x squared. 0 squared is 0. 0, so negative 0, still 0. So we have 0 for our leftmost term. So we have limit as x approaches 0, x squared sine 1 over x less than or equal to. Same thing, if I take x squared and I take the limit as x approaches 0, 0 squared would be equal to 0. So therefore, we've shown that this, which is less than our x squared sine 1 over x, is approaching 0 as x approaches 0. And this x squared, which is greater than or equal to our x squared sine 1 over x, is also approaching 0 as x approaches 0. This means that it's squeezed in, meaning that as our limit as x approaches 0, x squared sine 1 over x also has to be equal to 0. And you can see that here on the slide, following exactly what we did. So now let's look at the limits of a couple of our trig functions. If we have the limit as theta approaches some value a, cosine of theta, this is going to be equal to cosine of that value a. If we have the limit as theta approaches a, sine of theta, this is going to be equal to sine of a. And then also if we have the limit as theta approaches a, sine of theta divided by theta, this is going to be equal to 1. So let's do some quick examples. Let's say that we have the limit as x approaches a, and we have sine 7x divided by 4x. Now, this doesn't really fit any of these, right? Because if we were to plug in a, we would have sine of 7a over 4a, which really doesn't help us. So what we're going to do to try to get rid of this sine of x is we're going to look at what's inside of it, and we're going to multiply by 7 over 7. So if we were to do that, multiply by 7 over 7, we now have the limit as x approaches a, 7 sine of 7x over 4x times 7. Well, because multiplication is commutative and associative, I can rewrite this as 4 times 7x. Now, the reason we can do this, remember, 7 over 7 is the same thing as 1, and we're just multiplying by 1. We haven't actually changed anything. So sine of 7x divided by 7x is equal to 1. So now we have the limit as x approaches a, 7 over 4, which will give us 7 over 4. Which, looking at the slide, you can see that it follows exactly what we just did. For the next example, we're going to be looking at the limit as theta approaches 0, cosine theta minus 1 divided by theta. Now, this one is a little bit more complicated because we can't really use any of these rules right now, because if we were to just try to plug in 0, we would have cosine of theta would be cosine of 0, which would be 1. 1 minus 1 would give us 0 divided by 0. We'd have an undefined solution. So what we need to do is we need to think about, is there anything we can do and multiply the top and the bottom by that would allow us to get it into one of these forms? So in that case, what we're going to do is we're going to multiply by the reciprocal like we did earlier in this class. So this is going to be times cosine of theta plus 1 divided by cosine of theta plus 1. Now, as before, cosine of theta plus 1 over cosine of theta plus 1, same thing as multiplying by 1, so this doesn't change anything. So now what happens when we do this is this is going to be equal to the limit as theta approaches 0, and then what I'm going to do is I'm going to distribute this, so this is going to be cosine of theta times cosine of theta, which is going to be cosine squared theta. And then I'm going to do my outer terms. So my outer terms would be cosine of theta times 1. My inner terms would be minus 1 times cosine of theta. So those two would cancel. And then my last terms, negative 1 times 1 would be minus 1 over, and this would be cosine of theta times theta plus 1 times theta. So I'm just going to leave this the same. Theta divided by cosine of theta. Now what do we do? Well, in this case, we're going to use the fact that if we have sine square theta plus cosine square theta, this is going to be equal to 1. And what I'm going to do is I'm going to move this cosine over here. So, I'm going to move this sine over here. So we're going to have that cosine of theta. So cosine squared of theta is going to be 1 minus sine square theta. So using this fact, this is going to be equal to the limit as theta approaches 0. It's going to be negative sine squared of theta divided by theta times cosine of theta plus 1. So for the next step, what I'm going to do is I'm actually going to split one of these sine thetas over this theta, right? Because if I have the limit of some fraction where I have two values in the denominator, it's the same thing as splitting it up. So it's because multiplication. So this is going to be the limit as theta approaches 0. And I'm going to pull out sine of theta divided by, I'm going to have that theta here, times. And I'm going to have my other sine theta. This one's going to be negative sine theta divided by this cosine theta plus 1. Now, if we look at this, right, remember this limit is for the whole thing. What I can do is this sine of theta over theta, when I evaluate this, the limit as theta approaches a, sine over theta is going to be equal to 1. So this term is just going to go to 1. This is going to leave me with negative sine theta, which I can pull that negative out. So this is going to be negative limit as theta approaches 0, sine theta divided by cosine of theta plus 1. And then if I take the limit of sine theta as theta goes to 0, sine of 0, I'm going to use my substitution method, is equal to 0. Let's do the substitution method for the bottom. Cosine of 0 is going to be equal to 1 plus 1 is going to give me 0 over 2, which is equal to 0. And then if you look at the solution I have on the slide, you will see that this follows exactly what we did here. So you can see that there's a lot of things here with our limit rules, and it's very important to have a really strong grasp of these rules because you can take much more complicated problems or things that look like you might not be able to solve them and then actually break it down and break it into individual pieces that are solvable that then allow you to have a solution. Now, I mentioned later on we will learn a trick that allows us to solve these undefined answers solutions much faster. But notice that this didn't stop us from being able to analytically solve these limits. Hello everyone, in this lesson we're going to be going over continuity. So looking at this slide, you see that a function f is continuous at a if the limit as x approaches a for the function f of x is equal to the function f of a. So this is the function at that point a. If a function is not continuous at a, we would say that f has a discontinuity at a or is discontinuous at a. A function is continuous from the left if the limit as x approaches a from the left on f of x is equal to f of a, and a function is continuous from the right if the limit as x approaches a from the right, f of x is equal to f of a. So pretty much what this means is that if we have some function, and let's say we have this function here, and we are approaching some value a from the left or from the right, if this point a, which would give us f of a, is equal to what the limit is as you approach that point, then we would say it's continuous. If it has a discontinuity, this might look something like this, where instead of including that point, we have a hole here, where it might be that this point just doesn't exist, or it could be something like this point exists at another place on our graph. So looking at this slides again, you might see that the first example, like I just drew, is what's called a removable discontinuity. That is to say that it's a function and it is continuous at most places except at a, because as we approach a, that point does not exist. So the limit as I approach a is not going to be equal to f of a. The second image we have here is an infinite discontinuity. This would be that as we approach 0 from the left and the right, what's happening is it's going to go bigger and bigger towards infinity, and it's never going to be able to hit that point, meaning that there's, at that point a, in this case 0, you'll see that we actually do have a dot, so the point does exist, but neither of our limits will actually approach it. So we don't have continuity from the left or continuity from the right. The next graph is another example of a removable continuity, where again we have a hole, but this time we actually have a point somewhere on it. So that means that f of a does exist, whereas in the first one, f of a did not exist. And the last one is called a jump discontinuity. So there is a discontinuity, and it happens because as we're going from the left, we're approaching one value. As we're going from the right, we're approaching a different value, and it sort of makes a jump from one to the other. So it'd be something like this. You might see it as what we have here on this graph, where you have something like this, where it gets to this point, and then suddenly it makes a jump up to here. Or you might see it in this another case as sort of like a step function. Something like this, where you have a line, and then not included, and then maybe it jumps up, and then you have a line, and then it jumps up. And it does something like this, where you have multiple discontinuities, where each of these are a jump discontinuity. It jumps from one level to another, whereas if I'm taking the limit from the left, it will not be what the limit is from the right, just like with this one, right? When I approach the limit from left, I'm approaching this point. When I take the limit from the right, I'm approaching this point. They're not equal to each other. So while f of a does exist, and it's continuous from the right, because this is my f of a in this case, the point that's filled in. So my limit from the right is continuous, but my limit from the left is not. So let's say we have this graph here, and we want to label the discontinuities. So looking at this graph, as we go from the left, you will see that we have a discontinuity where that hole is. The limit from the left is equal to the limit from the right, meaning that they're approaching the same value, but that value does not exist. So for example, this might be x equals 2, which is a removable discontinuity, right? It's just missing, it's removed. As we approach from the right from there, you'll see that our limit from the left continues to go down and down and down until it gets to some point where then it does a jump discontinuity. So we have a jump discontinuity at x equals 5. And then continuing on to the right, we have another removable continuity where, again, it approaches the same value from the left and the right, so the limit exists, but the f of a at that point is a different point, meaning that it is not continuous at a. In this case, a equals 9. So based on this, this means that this graph is going to be continuous from negative infinity up to that first discontinuity of 2. And then it will be continuous starting at that discontinuity 2. Again, neither of those are inclusive, up to 5, not inclusive. And it'll start at 5 to 9, and then 9 up to infinity. So this might look a little bit like when we do a domain, but it's a little bit different, because if you actually look at the graph we have here, you'll see that we do actually have a point at x equals 9. So this is not the domain, because I can in fact plug in x equals 9. I just have this removable discontinuity, but the point does exist. So now let's do some examples to see which of the following functions are discontinuous, or where they're discontinuous. So our first function, we have f of x is equal to x squared minus x minus 2 divided by x minus 2. So similarly to when we are trying to determine what our domain is, we first need to look at, is there anything that this function I cannot plug an x in for, right? So if I look at this, I cannot plug an x in at 2. Because if I do plug in 2 here, I'm going to get 2 minus 2 in the denominator, in which case this is going to give me 0 in the denominator, which we can't do. It's undefined. So that means f2 is undefined, which means that it's a discontinuity, right? We can't ever hit that point. So what's going to happen is, as we take the limit from the left and or the right, it's going to probably approach some value, maybe going up to infinity, maybe going down to infinity, or maybe one side's going up to infinity, one side's going down to infinity, but it'll never actually be able to reach that point. So we'll never be able to have the limit as x approaches 2 on this function f of x be able to be equal to f of a, because at f2, it does not exist. The next function we have is gx is equal to 1 over x squared if x is not equal to 0, and it's equal to 1 if x is equal to 0. So we have this piecewise function here. So we have to consider what's happening whenever we have this function here. Well, on this first one, 1 over x squared, this is for whenever x is not equal to 0. So if we were to kind of graph this out, anywhere that's not equal to 0, this is the function that we're going to be using, 1 over x squared. And we could look at what happens as we plug in values, right? If we plug in 1, we get 1 over 1, so that's going to be 1. If I plug in 2, it's going to be 1/2. If I plug in 3, it's going to be 1/3. It's going to get smaller and smaller and smaller. And what happens as this value gets, the value x gets smaller and smaller? Well, it's going to cause the entire fraction to become bigger and bigger. Now, what about if we plugged in a negative value there? Well, what happens with a square when you plug in a negative? Well, it becomes positive. So it actually is going to have the same behavior. So what happens here is that we get something like this as we approach 0 from the left and from the right. Now, what do we actually get at 0? Well, according to our piecewise function, at 0, we have 1. So this means that we have a discontinuity at 1, because you'll see here that this goes off to infinity, this goes off to infinity. We do have the point, which means that the domain is that I can plug in any x value, but my limit as I approach 0 does not equal to what my function does at 0. So the limit as x approaches 0 on g of x is equal to this limit here, but it is not equal to g of 0. The next one we have is, what about if we have the function hx equals x squared minus x minus 2 divided by x minus 2 when x is not equal to 2, and we have that it's equal to 1 if x is equal to 2. So we're going to do the same sort of idea here, is that we're looking at what happens as we approach 2. So we're looking at the limit as h approaches 2 on, I'm sorry, not h, as x approaches 2 on our function hx. So when we're not equal to 2, meaning when we're approaching 2, we would be using this function here. So we're taking the limit as x approaches 2 for x squared minus x minus 2 divided by x minus 2. And in this case, we can't plug in 2, but we have an option for when the function is equal to 2. We said that it's going to be equal to 1. So again, we would need to look at what is the behavior of this function as we try to do that. So what I'm going to do is I'm actually going to split this into the limit as x approaches 2, and then this x squared minus x minus 2, I can set as x minus 2, x plus 1. Now, if we want to double check this, what we'll do is we'll just see if we can distribute this back together, see if we get the same thing. So we get x times x, or first outer inner last, so we get x squared. We get our outer, which is plus x, our inner, minus 2x, and then our last, minus 2. Well, x minus 2x is going to give us negative x, negative 2, so yeah, that looks good. So now what I'm going to do is I'm just going to cancel out these x minus 2's, and I'm going to have the limit as x approaches 2, x plus 1, which means that if I plug this in, I'm going to get a limit of 3. So my limit as x approaches 2 is going to be equal to 3. But my function, h of 3, is equal to 1 according to this piecewise function, which is not equal. So therefore, we have a discontinuity at 3, because 3 does not equal 1. The last one we have here, this is, so we have capital F of x equals the floor function of x, which means basically whatever values we plug in for x, we are going to be taking the greatest integer. So for negative 1, we would have a value of negative 1. And then it'll stay negative 1 until you get to the next integer, which is 0. And then suddenly it makes a jump up to 0. And then from 0 to 1, not including 1, it will be at 0. Once it gets to that next integer, 1, it's going to jump up to 1. And then we'll have a line at 1 up until it gets to 2. Then it jumps up to 2. Then it stays that line until it gets to 3. So this is actually a step function, and if you look at it, we actually have a discontinuity at every single integer, because if you look at -1, we start at -1, and then once we get to 0, we jump up to 0. Once we get to 1, we jump up to 1. Once we get up to 2, we jump up to 2. So in this case, this one actually has a whole bunch of discontinuities, which means that if we were to look at this, this is actually continuous only from the right, because if we're coming from the right, the function at that integer is equal, right? So if we look at this graph, let's say we look at f of 1. F of 1 is going to be equal to 1. Well, if I take the limit from the right of 1, so the limit as x approaches 1 from the right, it will be equal to 1. So it is continuous from the right. But if we look from the left, as we approach that point, again, say 1, so we have the limit as x approaches 1 from the left, the limit is approaching 0, but the function is equal to 1. So in this case, it is continuous from the right, but not continuous from the left. For our next example, we want to show that the function f of x is equal to 1 minus the square root of 1 minus x squared is continuous on the interval -1 to 1. So that means on the interval from -1 to 1, inclusive, meaning it includes -1 and includes +1, we want to show that this is continuous, which means that we want to say that if we have f of -1, what is this equal to? So if I plug in -1, I'm going to get -1 squared is 1. 1 minus 1 is 0. Square root of 0 is 0. So this is going to be equal to 1. If I plug in +1, I'm going to again get 1 minus 1 squared. 1 squared is 1. 1 minus 1, square root of 0 is going to be 1. So we have right now that f of -1 and f of 1 are both going to equal to 1. So in this case, if let's say that we have some a that is between these two values. So we're going to have a that is between -1 and 1, right? Our two x values. Right, so we're just saying that a exists somewhere in this interval. So what we're going to do is we're going to take our limit as x approaches a, and we're going to plug in our function. So we're going to have 1 minus the square root of 1 minus x squared. And then, of course, using our limit laws, this is going to be the same thing as the limit of 1 minus the limit of this. So it's going to be limit as x approaches the point a, 1, minus the limit as x approaches a, square root of 1 minus x squared. Well, this first term, we have the limit of a constant. That's just going to be the constant. So limit of 1 is just going to be equal to 1. Now we have minus, so we have 1 minus the limit as x approaches a, square root of 1 minus x squared. Now, using our limit laws, we can actually rewrite this as, we have 1 minus, I can take the limit of the function that's inside all to the square root, right? If I have the limit of a square root, it's the same thing as taking the square root of the limit. So this is going to then be the square root of the limit as x approaches a, 1 minus x squared. So right now we have this, and we can evaluate it just like we did before. I can take the limit of the first thing, it's constant 1, so it's going to be 1, and I take the limit minus the limit of this. So we're going to have 1 minus the square root of 1 minus the limit as x approaches a, x squared. And last thing we're going to do is we are going to plug our a value in, which is going to be 1 minus the square root of 1 minus a squared. And then I can actually see if I can solve this. Is this equal to f of a? Well, it is equal to f of a because if you remember, based on our original setup that we had 1 minus the square root of 1 minus a squared, which is the same exact thing that we would have in our original function. So that means that f of x is in fact continuous on -1 to +1 inclusive, right? So all we did basically is we showed that by solving the limit and plugging a in for x, we still get a function that f of a, which is equivalent to what we did with when we had it in terms of x for our function f of x. So pretty much what we've shown is that if I take the limit of this, it will still be equal to the same thing. Therefore, it does, in fact, it is continuous in that interval. So next what we want to talk about is if we have two functions, f and g, that are continuous at a, and we have some constant c, then this means that the following are continuous at that point a. If you take the function f and add it to the function g, it will still be continuous at a. If you take the function f and you subtract the function g, it will be continuous at a. If you take the function f and multiply it by the function g, it will be continuous at a. And if we take the function f and divide it by the function g, this will also be continuous at a, as long as g of a does in fact exist. Because again, we have a fraction, we can't have a 0 in the denominator. If g is continuous at some point b, and the limit as x approaches a for g of x is equal to b, then this means that the limit as x approaches a for f of g of x is going to be equal to the function f of b. So what does this mean? It just means that if we have that our limit as x approaches a on g of x is equal to b, we could then substitute that in for g of x as x approaches a, which means that we'll have the function f of what that is equal to now is b, so f of b. Or, that is to say, if we take the limit as x approaches a, f of g of x, this is going to be equal to f of the limit as x approaches a, g of x. So we can substitute in that limit, which we said was equal to b. And if g is continuous at a, and if f is continuous at ga, then f of g of x will equal to f of g of x, and it's going to be a continuous function. Right? So in this case, we're just writing it in the two forms and saying that, in fact, it is continuous here if you take a composite of two or more functions. As long as they are each continuous individually, they will all be continuous together. Some other rules that are actually really useful is any polynomial that you have is continuous everywhere. So polynomials are continuous everywhere. That is to say that it is continuous for all real numbers, meaning it has a continuity from negative infinity up to infinity. Any rational number, root function, or trig function is continuous at every number in their domains. That means, for example, if I have something like f of x is equal to the square root of x, this means that if I know my domain, which in this case the domain would be from 0 inclusive up to infinity, this means that it is continuous from 0 to infinity. If I have something like 1 over x, let's say we have g of x is equal to 1 over x, then in this case, what is my domain? My domain is I can plug in anything that's not 0. So the domain for this one would be from negative infinity up to 0, union 0 up to infinity, meaning that this function would be continuous everywhere except 0. For our next example, we're going to start with the fact that f and g are continuous. I'm just going to put cont. If f of negative 1 is equal to 2, and the limit as x approaches negative 1, 3 f of x minus g of x is equal to 0, let's find g of x. So how would we go about doing this? Well, we're going to start with this limit here. We have our limit as x approaches negative 1 for 3 f of x minus g of x. And we're going to then use our limit rules to take the fact that we can take the limit of this minus this as the limit of this minus the limit of this. So this is going to be equal to the limit as x approaches negative 1, 3 f of x, minus the limit as x approaches negative 1, g of x. And now that we have it in this form, we have the limit of a constant times our function. I can pull that constant out, so I'll have 3 times the limit of x approaches negative 1, f of x, minus limit as x approaches negative 1, g of x. So let me write that down real quick. We have limit as x approaches negative 1, sorry, we got the 3 on the outside, f of x, minus the limit as x approaches negative 1, g of x. Now, based on the facts that we were given, f of negative 1 is equal to 2. And if we plug in a limit as x approaches negative 1, what we can do is we can plug that negative 1 in. And as long as it exists, we'll be able to get the limit. So this is going to end up being 3 times plug in negative 1, which is going to give us 2. And if we were to plug in negative 1 into this g of x, we'll just replace that. So now we have minus g of negative 1. So now we have 3 times 2 minus g negative 1. Well, we did say that this entire limit was going to be equal to 0. So we're going to set this equal to 0. So we have 3 times 2, which is equal to 6. So 6 minus g at negative 1 is equal to 0. So with this now, I want to isolate my g of negative 1. So because this is negative, what I'm actually going to do is I'm going to add g of negative 1 to both sides, which is going to give me 6 is equal to the function g at negative 1. So therefore, we now know what is g of x as the limit as g of x as we approach negative 1, right? Because I actually wrote this wrong. This should have been g of negative 1. Sorry about that. In this next example, we want to consider that we have the function f of x is equal to x squared minus x divided by x squared minus 1 if x is not equal to 1, because if we plugged in 1, we would get 0 in the denominator, and 1 if x is equal to 1. So we have this piecewise function, and what we want to do is we want to find the limit as x approaches 1 for f of x, and then of course we also want to figure out what is our function at 1. So we're going to start with our limit. So our limit as x approaches 1, well remember, our limit as we approach 1 is not equal to 1. It's everything but 1 as we get closer and closer and closer, infinitesimally close, but never actually touching it. So we're going to be using this function up here. So we're taking the limit of x squared minus x divided by x squared minus 1. Now, if I were to really quickly just try to plug in 1, we already talked about the fact I'm not going to be able to do this because I'm going to get 1 in the denominator, so 1 squared is 1, 1 minus 1 is going to be 0. So I need to do something to try to simplify this to make it where I can actually take that limit. So what I'm actually going to do is I'm going to take the limit as x approaches 1, and I am going to pull one of these x's out from the top. So we have x squared minus x. Both have x in it, so I'm going to pull one of these x's out. I'm going to get x times x minus 1. And for the bottom, I have that this is a square function, x squared minus 1, which means that I can actually rewrite this as x plus 1, x minus 1. And if you just want to double check, as we always do, FOIL it out. X times x is going to give me x squared minus x plus x minus 1. The minus x and plus x will cancel. I'll be left with x squared minus 1. Now, based on this, the top and the bottom both have an x minus 1 that I can cancel. So now I am left with the limit as x approaches 1, x over x plus 1. Now, if I were to evaluate this limit, I would use my limit laws. I would take the limit of x over the limit of x plus 1, and then I would split the limit of x plus the limit of 1. 1 is a constant, so it would just be 1. But I'm just going to plug it in, and I'm going to get 1 over 1 plus 1, which is equal to 1/2. So next thing we're going to do is we're going to look at, this is our limit of f of x, right? We talked about our limit as x approaches 1, f of x, we said is equal to 1/2. Now what we want to do is we want to figure out what is our function at 1. And this is going to be equal to 1, because we said if x is 1, f of x is equal to 1. So in this case, it is equal to 1. And we're going to look at, is it continuous? Well, if it's continuous, this means that the limit as x approaches 1, f of x would have to be equal to the function at 1. And these two are, in fact, not equal, meaning it's discontinuous at x equals 1. So when a is equal to 1, this is discontinuous. For the next example, I'm going to find the limit as x approaches 1 for 8 plus the square root of x divided by the square root of 8 plus x. So in this case, if I were to try to plug in 1, what's going to happen? Well, I'm going to get 8 plus the square root of 1 divided by the square root of 8 plus 1. So the square root of 1 is just going to be equal to 1. So the top's going to be 8 plus 1. 8 plus 1 is 9, so I'm going to have the square root of 9, which is going to give me 9 over 3, which is equal to 3. So in this case, I actually got a limit just by plugging it in, which means that if this is my function, 8 plus square root of x over square root of 8 plus x, and I plug in 3, so I would get f of 3, I'm going to get 3. When I took the limit as x equals 1, I also got 3. So therefore, in this case, this would be a continuous function, because the only thing that's going to cause an issue is if, in this case, I tried to plug in a negative 8 or something that's going to make it negative, which means anything less than negative 8, right? So if x is less than negative less than or equal to -8, this would cause it to not exist. So the domain of this function is -8 up to infinity, meaning that this is actually continuous anywhere on this domain, because this would be a rational function or irrational function or any of those other ones we talked about, which means that it is in fact continuous at x equals 1. What about if we wanted to find the limit as x approaches pi on the function 2 sine x plus sine of x? So in this case, we're going to take the limit of 2 sine, and within the sine is x plus sine x. So whenever you have something like this, and this is why the first step I always say is, first let's see if we can plug it in. If we plug it in and we get a value, then we have the limit. We don't have to do any tricks. We don't have to do any ways of canceling anything out. So what we're going to do is we're just going to try plugging this in. So if I plug this in, which means I'm going to evaluate this limit, I'm going to have that this is equal to 2 sine of pi plus sine pi. Now, what is the answer of sine equals pi? Well, let's look at what a sine wave does. So a sine wave starts at 0, goes up, goes down, comes back up. And of course, it's at 0 at 0. It's at 1 at pi over 2. It's back to 0 at pi. It's -1 at 3 pi over 2. And it's back to 0 at 2 pi. And then it's going to repeat this over and over again. So at sine of pi, we have that the answer is it's equal to 0. So this is going to go to 0. So now we have 2 sine of pi plus 0. Well, pi plus 0 is just pi. So that means we're basically looking at what is 2 sine of pi. Well, we just said sine of pi is equal to 0. So this is going to end up being 2 times 0, which means that the answer is 0. So looking at this slide, we're going to be looking at, for these different functions, where are these functions continuous? So the first one we have f of x equals x to the 100th power minus 2x to the 37th power plus 75. Now in this case, because this is a polynomial function, remember that first rule we had, polynomial functions are continuous on the real number line, which means all possible values. So this one will be continuous from -infinity to infinity. The second function, g of x equals x squared plus 2x plus 17 divided by x squared minus 1. Now in this case, because this one is a fraction, a rational function, whatever you want to consider it, it's wherever its domain is, that is where it's going to be continuous. So we want to look for where we cannot plug in an x value. What is its domain? So looking at the denominator, so the top is a polynomial, meaning the top doesn't have any restrictions. It can be any value. But if we look at the bottom, I have x squared minus 1. So if I were to plug in a positive 1, I would get 1 squared is 1. 1 minus 1 is 0. I'd get a 0 in the denominator. If I plug in a -1, -1 squared is positive 1. Positive 1 minus 1 gives me a 0 in the denominator, meaning that x cannot be -1 or 1. This means that this function will be continuous from -infinity up to 1, not inclusive, union, -1 to 1, not inclusive, union, and then 1 to infinity. So basically it is continuous anywhere on the number line except at -1 and positive 1. For the third function, we have hx is equal to the square root of x plus 1 over x minus 1 minus x plus 1 over x squared plus 1. So in this case, again, we're looking at the fact of where can we not plug in an x, meaning it's not part of our domain, that would cause this to fail. So I'm going to start by looking at the last part of this function, x plus 1 over x squared plus 1. Now, I can plug any value in for x here, because even though there's something in the denominator with an x, what's going to happen is if I plug in a positive value, I'm going to get a positive outcome. So positive value plus a 1 is going to be equal to something positive. If I plug in a negative value, that square is going to make it positive, giving me the same thing. So the last term has no restrictions on it. Then we're going to look at the middle term, x plus 1 divided by x minus 1. The numerator has no restrictions on it, but x minus 1 does. It says that we cannot plug in a 1 into this part, because if I plug in 1, the denominator will be 1 minus 1 or 0. So x equals 1 is something it's not in our domain. Now we look at the first term. We have the square root of x. Well, we talked about before, the square root of x can be any value from 0 inclusive up to infinity, meaning that this function, this part of the function, is anything greater than or equal to 0, which means that our domain would be 0 inclusive, so square bracket 0, up to 1, parentheses, union, parentheses, up to 1, up to infinity. So in this case, this is where it would be continuous. It would be continuous anywhere from 0 to 1, not including 1, and anywhere from 1 to infinity. For this next example, we're going to have a constant c that we want to determine where this would cause our function f to be continuous on our number line negative infinity to infinity. So if we have the function f of x is equal to the constant c x squared plus 2x if x is less than 5, and we have that this function is equal to x cubed minus cx if x is greater than or equal to 5. So we have this piecewise function. What we want to do is we want to see what value of c would cause this to be continuous. Now remember, for this to be continuous, it means that as I take the limit from the left, it has to be equal to the limit from the right. So this, when x is less than 5, means that as I approach 5 from the left, this is my function I'm going to use. Because this one is x greater than or equal to 5, as I approach 5 from the right, this is the function I'm going to use. So what I'm going to do is I'm going to set the two functions equal to each other. So I want the limit as x approaches 5 from the left on my function f of x, and I want this to be true where it is equal to the limit as x approaches 5 from the right on my function f of x. So now what I'm going to do is I'm going to plug both of these in. Well, I said that as I'm approaching from the left, it's going to be this. So this is going to be the limit as x approaches 5 from the left is going to be cx squared plus 2x, and then this is going to be equal to my limit as I approach from the right, so limit as x approaches 5 from the right, and I'm going to plug this function in, x cubed minus cx. And so now what I'm going to do is I'm going to evaluate what both of these would be if I were to plug in 5. So this first one, right, because basically what's happening is, we want to think of it piecewise, is that I'm going to take the limit of this first term plus the limit of the second term. That c is a constant, I can pull that out. So actually, you know what, I'll do that just to show you guys the steps. So this would then be the limit as x approaches 5 from the left, cx squared, plus the limit as x approaches 5 from the left, 2x. I'm just going to focus on the left right now. This is a constant c, so I can pull this out. This 2 is constant, so I can pull this out. So I'm going to be left with the limit as x approaches 5 from the left. It's going to be c times that, x squared, plus 2 limit as x approaches 5 from the left, x. Now, if we look at the right side, it's going to be the same idea. I can take the limit of the first term minus the limit of the second term. So this is going to be the limit as x approaches 5 from the right, x cubed, minus the limit as x approaches 5 from the right, cx. Now, because I have this constant in front, I can pull this out. This is going to be equal to the limit as x approaches 5 from the right, x cubed, minus c, limit as x approaches 5 from the right, x. And now what I'm going to do is I'm just going to plug in 5 for anywhere that I have x. So in this case, this is going to be c times 5 squared plus 2 times 5 equals 5 cubed minus c times 5. And I just need to solve for my c now. So this is going to be 25c. I'm going to pull this over here. This is going to be 25c plus 10 is equal to 125 minus 5c. And now I just need to solve for c. So I have 125. If I were to subtract 10, so I'm going to subtract 10 from both sides. I'm going to add c to both sides. I'm going to be left with 30c is equal to 115. And then I'm just going to divide both sides by 30. And I will be left with c is equal to 23 over 6. And now this would be the c that if I were to plug this in to this original function, right, this piecewise function, this would make it continuous, which means that as I take my limit from the left, it is going to be equal to my limit from the right, and they're going to meet at the same point. So we're going to end off this lesson by looking at the intermediate value theorem. So suppose you have some function f is continuous on a closed interval a to b. Let n be any number between f of a and f of b, right? So we have our boundary conditions a and we have our boundary condition b. And we have n is some number between the function at a and the function at b, where f of a is not equal to f of b. Then that means that there exists some number c in our interval a to b such that the function at c will be equal to that n. So looking at this graph, what this kind of means is that if I have my boundaries a and b, and I have some points on a and b at the boundaries which are not equal to each other, that means that somewhere in this interval there will be some c where it is the function at c will be equal to that point n, meaning that it has to hit every intermediate value. So if I have some a, right, so let's say we have this. If I have some a here and I have some b here, and let's say that I have a dot here and a dot here, at some point between these two, at least one point, but it could be more, I'm going to have to cross whatever value n is between these two. So if n is here, let's say, this means that I could have a straight line where I will hit n right here, or it could be something like this where I go up, I go down, and I come back up. Well, guess what? I've hit n here and here and here. So what this is saying is just that if I have this closed interval a to b, that to get from f of a to f of b, at least somewhere in this interval, I will have to cross this point n, which is between f of a and f of b, right? So f of a is here, f of b is here, and if n is between f of a and f of b, as I go from a to b, I will have to have crossed n at least one time, right? So pretty much what it's saying, it seems pretty intuitive. To get from a to b, I would have to cross every point between here, right? I'd have to go from every point from f of a to f of b, meaning somewhere in here, this n will get crossed at least one time. Now, in some cases, as I said, you may be able to find more than one number. So if you kind of look at this slide here, I have a graph kind of like what I drew here, where I have a sort of sine wave looking kind of function where it goes up, it comes back down, it goes back up between f of a and f of b, which means that in this case, it would actually hit at some c1, some c2, and some c3. It'd have 3 points where it actually crossed that point n. That's between f of a and f of b. Now, note, this intermediate value theorem does not tell you how many times you will cross, just that you will have to have had crossed at least once. So it's sort of like a proof of existence. There exists somewhere in this interval where it has to be true that this outcome exists. So in this problem, we want to use the intermediate value theorem to show there's a solution for a given equation on an interval 1 to 2. So we have x to the 4th power plus x minus 4 is equal to 0. So our function f of x is equal to x to the 4th plus x minus 4. Now this is continuous because this is a polynomial function. As we said, polynomial function is continuous on the entire real number line. So what we're going to do is we're going to first figure out what our boundaries are. So we have f of 1, and we're going to plug in 1 wherever we have an x. So 1 to the 4th power is 1 plus 1 minus 4. So we're going to get negative 2. Then we're going to plug in our our right side boundary, which is going to be 2. So we're going to plug in 2. 2 to the 4th power plus 2 minus 4 is going to give us 14, which means f of a is equal to negative 2. F of b is equal to 14. That means that to check whether this point, there in fact is some solution to this problem, x to the 4th power plus x minus 4 equals 0, we would need to show that, in fact, the 0 exists somewhere between negative 2 and positive 14. So, and it does, right? If I'm going from negative 2 up to 14, I will have to cross every value on the real number line between negative 2 and 14, meaning that, and 0 is in that interval, which means that there is at least one solution where this is true. X to the 4th plus x minus 4 equals to 0. Similarly, if we want to show that the equation x to the 4th plus x minus 3 equals 0 has a solution on this interval 1 to 2, we do the same idea, right? We have our f of x, which is equal to x to the 4th plus x minus 3, which again, polynomial, which means it's continuous in that interval from 1 to 2. I'll plug in my boundary condition, so I plug in 1, I get 1 plus 1 minus 3, which is going to give me negative 1. That's going to be less than 0. For our right side boundary, we're going to plug in 2, which we're going to get f of 2 is equal to 2 to the 4th power plus 2 minus 3, which can be equal to 15. And this is greater than 0, meaning that basically to go from a negative value, which is less than 0, up to a value greater than 0, means we would have had to have crossed 0 at some point to get there. So this by our intermediate value theorem, then we can say that there exists some number c on the interval 1 to 2 where f of x does in fact equal 0. Now, as a reminder, this does not tell us how many solutions there are. There could be more than one. All this states is that at least one solution to x to the fourth power plus x minus 3 equals 0 exists on the real number line in this interval between 1 and 2. Hello everyone. In this lesson, we're going to be looking at derivatives and rates of change. So to do this, we're first going to begin by looking at the slope of a line through 2 points. So suppose that we have 2 points, x1, y1, and x2, y2. And if we want to know what the slope is between these 2 points, right? So let's say we have one point here. This is x1, y1, and this is x2, y2. We want to know what is the slope between these 2 points. Normally what we would do is we would try to figure out what is the rise over run, or the rate of change of y over the rate of change of x. And the reasoning behind this is, let's say that this is on our Cartesian plane, and we want to know how far have we moved in the y direction. So what we would do is we would figure out where is y1 and where is y2. We would take the distance from y2 to the origin. Then we would take the distance from y1 to the origin, subtract that off, and we're left with the distance between these two. And then we would do the same thing for x1 and x2. And this would give us how much we've moved in the y direction over how much we've moved in the x direction. So this is then going to be y2 minus y1 over x2 minus x1. And since we have that f of x is usually can be written as y, this can be written as the change in f of x divided by the change in x. So what does this slope actually represent? Well, it represents the average rate of change between 2 points. So if I wanted to know what is the average rate of change from this point to this point, I could just consider the slope between those 2 points. So now we're going to learn about tangent lines. The word tangent comes from the Latin word touching. A tangent is a straight line that just touches a curve at one given point. And the slope of a tangent line represents the instantaneous rate of change at that single point. So let's say, for example, that we have some function, something like this. This means that if I wanted to take the tangent line at this point, it would be the slope at that particular point. Or if I took one here, it'd be the slope here. Or if I took one here, it would be the line that goes through right here. It is a line that touches just at that single point, telling us what the slope is at that exact moment, that exact point, giving us the instantaneous rate of change. So remember previously when we talked about dropping a ball from a tower, and if we knew the distance that it fell, the amount of time, we could figure out the average rate of change. Well, now with the idea of a tangent line, if we could map out the function that describes that ball falling from a tower, we could figure out what the instantaneous rate of change is at any given time, not just the average over the entire ball drop or between 2 time periods. Now to do this, what we're going to be doing is we're going to be looking at how do we find derivatives. So we call the slope of a tangent line to that given point on a curve its derivative. And the process of finding a derivative is called differentiation. Derivatives are called instantaneous rates of change. And as an example, velocity is the derivative of position. And acceleration is the derivative of velocity. So for example, if we took the derivative, it would tell us the amount of change of that particular variable. So velocity is the rate of change of position. Acceleration is the rate of change of velocity. And we're going to use the notation f prime of x to represent that we are going to be doing differentiation. Now, since the derivative of a function at some given point represents the slope of the tangent line at that point, we're going to be using formulas for slope to find our derivative. So if you remember, like I said, if we have the points x1 and y1 and x2, y2, we would have that the slope, I'm going to write this as m because when we do line slope formula, this would be y2 minus y1 over x2 minus x1. Now, if we were to change our y's into f of x to represent their function, then this would become f of y2 minus f of y1 divided by x2 minus x1. Now let's actually look at the slope of a tangent line to some point A. So we'll write this as to A, f of A. And this is the actual point that we want to find the tangent line for, meaning that, if we had some slope, for example, and this is our A value, then we would have some associated f of A or y value with that for that point. So then now what we're going to have is we're going to have our slope m equals the limit as x2 approaches that point x1, basically as it gets closer and closer and closer until it touches it, f of x2 minus f of x1 divided by x2 minus x1. And what's happening now is that we're taking the limit as this slope formula is the points are getting closer and closer and closer. So let's say that this was my x. My x was right here. So I would have some point here. This is my f of x. And pretty much we're taking the limit as this x approaches this a, and our function, our f of x approaches this f of a, and we're getting closer and closer and closer until we are just at that point where we're infinitesimally close to where we're getting a slope at that single specific point. So now what I'm going to do is, because we're approaching this value a, is I'm going to replace my x1 with this. So this is going to then be equal to the limit as x approaches a, f of x minus f of a divided by x minus a. So in this case, all I did was I replaced, instead of saying x2, I'm just calling this x. And instead of saying x1, I'm calling this a. So pretty much as my, originally what was x2 gets closer and closer to x1, or now we're referring to it as my x value gets closer and closer to that a that I'm actually interested in. So then we're going to rewrite this now in terms of the distance between the two. And this formula is going to be the limit as h goes to 0, f of a plus h minus f of a divided by h. And all h represents is the distance between this x and a. So what we're saying here then is, if I'm going to redraw this so it's a little easier to visualize. I'll put them a little further away so you can see what I'm talking about. Let's say that x is right here, and let's say that a is here. So the distance between them is h. So of course, if I get my x, I'm going to have some f of x here. My a is going to have some f of a here. But now, instead of looking at f of a, we're actually replacing this with f of x plus h, because if I took x plus h, this is the same thing as a. So now this term is going to be f of x plus h. And if you actually watch the review we did originally, this is where we're using what's called the difference quotient. So we're taking the difference quotient from some point x to some point a, where the distance between them is h, and we're taking the limit as that h goes to 0. So let's do an example. The first one we have is we want to find the slope of the tangent line for the hyperbola y equals 3 over x at the point 3, 1. So in this case, first thing we're going to do is we're going to set up our definition of a derivative, which is going to be the limit as x approaches a, f of x minus f of a divided by x minus a. And in this case, our a is that value that we're approaching. So in this case, it's going to be 3, right? We're changing our x value. So in this case, a is equal to 3. So if we look at our function then, our f of x for this is going to be this hyperbola that we had. So this is going to be 3 over x. And now, if I were to plug in f of a into this, so f of a is just going to be f of 3, which is going to be 3 over 3, or 1. So now we know what, for our actual point that we're approaching, we know our x value, we know our y value, and it matches what we have here, so that makes sense. So now let's plug it in to our limit. So we have the limit as x approaches 3, and then I'm going to plug in my f of x. We said our f of x was this 3 over x minus my f of a, which we just said is equal to 1, divided by x minus a. Well, my a is 3, so we're going to have x minus 3. So now we have this. So now what we need to do is we need to try to solve to figure out what this limit is. We want to figure out what the slope is there. So what I'm going to do is, because I have a fraction subtracting 1, I'm going to get it to a like base. So this is going to be the limit. And don't forget, you leave the limit until you're actually ready to evaluate it. This is going to be 3 over x minus, and then to make 1 in terms of over x, it's going to be x over x divided by x minus 3. And now with this, I can actually split this into two parts. I can have 3 minus x over x, and then times 1 over x minus 3. Now, why is that? Because basically what we're doing is this. We're saying that this is the limit as x approaches 3, and then I'm going to combine these terms together. So this is going to be 3 minus x over x divided by x minus 3, which, of course, we have fractional division. So if you wanted to, you could think of this x over 3 as x over 1. So then I'm going to bring this term here. I'm going to bring this term here. So this is going to cause it to become the limit as x approaches 3, 3 minus x times 1, so that doesn't change, divided by x times x minus 3. And of course, if I have something like this where it's like, I don't know, I'm just going to put 3 minus x over a times b. This is the same thing as 3 minus x over a times 1 divided by b, right? So if I were to multiply this out, the 1 doesn't change it, and this just becomes ab. So that's what I'm going to do in this case. So this is going to become the limit as x approaches 3, and then I'm going to be left with 3 minus x divided by x times 1 over x minus 3. Now, if I were to try to evaluate this now, this would still be a problem because I have this x minus 3 in the denominator. And if I plug in 3 there, it's going to be 3 minus 3. I'm going to get a 0 in the denominator. And 0 times the x, which is 3, is still going to be 0. So we have a problem here. So what I'm going to do is I'm actually going to pull a negative out of this term here so that I can make it the same as this. So this is going to be the limit as x approaches 3 minus, so this will be minus minus x becomes plus x, and then 3, I'm going to make this negative 3, right? So you can always check it by trying to redistribute it. This becomes minus x plus 3, so 3 minus x, same thing. And this is going to be over x times 1 over x minus 3. By the way, you didn't have to do this step. You could have left it all together. I just did this so it's a little bit clearer to see. So now what we have is we have this x minus 3 cancel with this x minus 3, and we're left with the limit as x approaches 3, negative 1 over x. So we have the limit as x approaches 3, negative 1 over x. And now we can plug in our 3, and it doesn't have a 0 in the denominator. So when I evaluate my limit, I plug in 3 for x, I get that the slope at this point is negative 1/3. Now what we're going to do is I'm going to use the difference quotient to show that we get the same answer and how it's just a little bit different, but it's the same idea. So that's why I'm going to leave this here so we have something to compare it to. So first we're going to set up our difference quotient, which is the limit as h goes to 0, and I will set up f of a plus h minus f of a over h. Which, by the way, later on, a lot of times I'm just going to write this as f of x because x or a, it doesn't really matter. It is an x value. It's just the value that we're approaching. So if I consider the distance from x to my value a is h, I can use a instead of x, and it's the same distance, just in the other direction, but then it flips sign. It doesn't change anything. So we have this. We still have that a is equal to 3, because that's the value that we're approaching. So we're starting at 3, and we're changing by some distance h, whether it be to the left or to the right, right? So that's why it doesn't change anything. So first things first, I'm going to figure out what is f of a plus h. Well, if our f of x was 3 over x, and what we have here is we are going to be plugging in, right, because our a is 3, this is going to be 3 plus h. We are going to plug it into this function right here, and we're going to get 3 over 3 plus h. So that's our f of a plus h, or f of 3 plus h. Then I'm going to find my f of a. So my f of a, which is just equal to f of 3, which just like we did before is 3 over 3 or 1. And now what I'm going to do, I'm going to take these, I'm going to plug them into this limit here. So I'm going to bring the limit down here. So this is the limit as h goes to 0, and I'm going to plug in f of a plus h, which is this term right here. So this will be 3 divided by 3 plus h minus f of a, so minus 1, divided by h. And I can't take the limit to begin with, because if I evaluate the limit now, I'm going to have a 0 in the denominator. So I have to do some rearranging to get it in terms that I can actually do some cancellation to solve for it. So just like before, I'm going to change this 1 so it's in terms of whatever the denominator is so I can combine them together. So this can be 3 plus h. So this is going to be the limit as h goes to 0, 3 over 3 plus h minus 3 plus h over 3 plus h. And then this is all divided by h. And now that I have these two in terms of the same denominator, I can combine these together. So this is going to become the limit as h goes to 0. So 3 minus 3, and then I could consider it minus 3 plus h, which if I were to distribute that negative, it would be minus 3 minus h. I'll leave it this way for now. Divided by 3 plus h divided by h. Okay, so now we have this so far. Now I could consider this as the same thing as, right, if I did fractional division, this h is just going to come over here, you got a 1 over here. So this is kind of the same thing as saying times 1 over h. So I'm just going to get rid of that term so it's a little clearer what we're looking at. So now what we're going to do is we're going to cancel out these 3's. And of course, remember, this negative goes to this h. So I have the limit as h goes to 0 minus h divided by 3 plus h times h. Right, because I had the times 1 over h, so it's the same thing. So this h is going to cancel with this h. And now what I'm left with is the limit as h goes to 0 minus 1 over 3 plus h. Now at this point, I can evaluate, because as h goes to 0, I can plug this in here and I won't get a 0 in the denominator anymore. So now that I'm evaluating, I don't need to carry my limit over anymore. So this is going to be negative 1 over 3 plus 0, or negative 1/3, which if you look at what we got for our original answer, it matches exactly what we got. And by the way, so in this course, generally this is the form that we're going to be using, not this one, because this actually has some properties that make it a little easier to solve. I know it seems like we're basically did the same thing, and generally it is true, but there are certain times where this will actually be a little bit more intuitive to solve. Okay, now that we've found the derivative, remember, this derivative is our instantaneous rate of change at this point, a equals 3. This means that this is the slope, but we want to figure out what the tangent line is. So what we're going to do is we're going to use the point slope formula. So we're going to use our point slope formula, or point slope formula line, which is going to be y minus y1 equals m times x minus x1. And we're going to plug this in, and we're going to solve to determine what our line is. So first things first, we're going to plug in our slope, and we're going to plug in our x and our y for that point that we're at. Remember, because this is the instantaneous rate of change at this point, 3, 1. So then this becomes y minus, our y value is 1, equals negative 1/3 x minus 3. And this is going to allow us to solve for our slope-intercept form of our line. So first thing I'm going to do is I'm going to distribute this negative 1/3. So this is going to be y minus 1 equals negative 1/3 x. I don't know why I put the x down here. 1/3 x. And then minus 1/3 times negative 3 is going to give me positive 1. So plus 1. And now what I'm going to do is I'm going to bring this 1 over. So I'm going to add 1 to both sides. So plus 1, plus 1. This is going to be y equals negative 1/3 x plus 2. And this is the slope for our tangent line at the point 3, 1. It has a slope of negative 1/3, and then we could draw the rest of the line using this form. Next, we're going to do an example where we're going to find the derivative of this function, f of x equals x squared minus 8x plus 9 at x equals a. So first thing we're going to do is we're going to say, okay, we want the derivative of fa, which is going to be our limit as x approaches a, f of x minus f of a divided by x minus a. So we have our f of x here, so I'm going to plug this f of x in to see what our limit becomes. So in this case, we have the limit as x approaches a, x squared minus 8x plus 9 minus, and now I'm going to get f of a, which is the same thing, but instead of x squared minus 8x plus 9, it's going to be a squared minus 8a plus 9. But remember, I'm subtracting this. So what I'm going to do now is I'm just going to flip all the signs. So this is going to be minus a squared plus 8a minus 9 divided by x minus a. So looking at this, we have plus 9 and we have minus 9 that we can cancel. So rewriting this, we have the limit as x approaches a, x squared minus 8x minus a squared plus 8a divided by x minus a. Now what is this equal to? Well, we could try to solve this. We could try to, for example, put the 8's together and then pull them out. We could put the x's together, or we could put the square terms together and try to do something with that. But really, I wanted to show you that this is sort of the pitfall of using f of x and f of a. So now what we're going to do instead is let's actually look at why it's simpler to solve this using our difference quotient where we had h going to 0. So using the difference between the 2 points rather than the 2 points themselves. So rewriting this, we would have f prime of a is equal to f of a plus h minus f of a divided by h. And then we're going to do the same idea. But first thing we're going to do is we're going to figure out what is our f of a plus h. So if we have f of a plus h, this is going to be the same thing as plugging a plus h into every one of these x values. So this is going to be a plus h squared minus 8 times a plus h plus 9. So of course, now I'm going to factor this, and I'm going to distribute this, and we'll figure out what this is. So this one I'm going to do FOIL it. So first I get a squared. I'm going to do outer, inner, which is going to be ah. So I'm going to have plus 2 ah plus h squared. For this, I'm going to distribute the negative 8, so negative 8a minus 8h, and then plus 9. And now what I'm going to do is I'm going to combine like terms if I have any. Looks like I don't have any, so that's perfectly fine. So now let's figure out what is our FA, right? We're looking for FA now. So FA, same idea, except for I am plugging in a into each of these x's in my original function. So this is going to be a squared minus 8a plus 9. Now let's bring these and put them back into our limit. So this is going to be equal to, I forgot to write my limit as h goes to 0. So this is going to be equal to the limit as h goes to 0. I'm going to plug in my f of a plus h. This is going to be a squared plus 2ah plus h squared minus 8a minus 8h plus 9. And then, remember, it's minus f of a. So all these terms, a squared becomes minus a squared, negative 8a becomes positive 8a, and plus 9 becomes minus 9. So this is going to be minus a squared plus 8a minus 9. And then all of this is divided by h. And now let's see if we can do some any cancellation. Well, we can, right? So we have a squared, we have minus a squared. We have 9, we have minus 9. We have minus 8a, we have plus 8a. So we are left with the limit as h goes to 0, and then we have h squared plus 2ah minus 8h. So we have h squared plus 2ah minus 8h. h divided by h. So every term here has an h. So what can I do with that? I can pull the h out. So this is going to become limit as h goes to 0, pull out my h. So if I pull an h out of h squared, this is going to be h. Plus, if I pull an h out of 2ah, this is going to be 2a. If I pull an h out of minus 8a, it's going to be minus 8. Divided by h, these h's cancel, and I'm left with the limit as h goes to 0, h plus 2a minus 8. I can evaluate my limit now by plugging h in. So I plug in 0, and I'm going to get that this derivative is equal to 2a minus 8. So pretty much what this is telling us is that our derivative is dependent on what that a is. So if I'm approaching the point 3, it would be 2 times 3 minus 8, and that would give me the slope at that point. If my a was 7, it would be 2 times 7 minus 8, and that would give me the slope at that particular point. So the slope is different based on that initial point that we are going to. So let's find the tangent line using this, and we're going to be going through the point 3, negative 6. So we want the tangent line to the formula y equals x squared minus 8x plus 9, and going through the point 3 minus 6. So if we were to look at our f prime of a, that's our slope, that's our derivative at that point. If we were to plug in 3 into this, f prime of 3, this would be 2 times 3 minus 8. So 6 minus 8 gives us a slope of negative 2. And now we're going to use our point slope formula to figure out what is the equation for our line. So we're going to have y minus y1 equals mx minus x1. I plug in my negative 2 for my m, so I'm just going to put my slope in first. And this is going to be x minus, my x value is 3. And then y minus, my y value is negative 6. That's going to be plus 6. So then I'm going to distribute that negative 2. So this is going to be y plus 6 is equal to minus 2x. And then minus 2 times minus 3 is plus 6. So when I subtract 6 from both sides, I'm going to be left with y equals negative 2x. So this is the line that describes this, this particular derivative at the point 3, negative 6, is that it is the line y equals negative 2x. For our next example, we want to find the tangent line for the graph for y equals gx, where at x2, so at x equals 2. So if g of 2 is equal to negative 5, and if we have a derivative g of 2 at 2, which is equal to 4, how can we find this line? Well, looking at this, remember that g of x is really just saying the function of x. You could think of this like your y. So we specifically said we're at x equals 2, and when I plug in 2 into this function, I get a y of negative 5. So we're really asking, we want to find the tangent line at 2, negative 5. With a slope, right, because that's what this prime means, is that this is the slope at 2 for this function g of x, which is equal to 4. So we can plug this directly in and we can solve for our tangent line. So we have y minus y1 equals m x minus x1, and then we just plug in our x and our y values, we plug in our slope, and then we can solve for our line. So this is going to be y minus negative 5, so y plus 5, equals m, it says is 4, x minus, our x is 2, so x1 is 2. I'm going to distribute this 4, so we get y plus 5 equals 4x minus 8. I'm going to subtract 5 from both sides, so this is going to give me y equals 4x minus 13. So if you already know what the slope is, and you have a particular point that you're going through, you can actually directly solve for the line, right? So in this case, this was the information I gave you. We had that y is equal to some function g of x, and we were at the point x equals 2. Now, we gave you the output of that function, so g at 2 is equal to -5. So that's us saying if we plugged in 2 into this function, we get a y of -5. And then we even gave you the derivative at that point, meaning that at the point x equals 2, we know that the point is actually 2, -5, and it has a slope of 4. So there we have all the information, because to use the point slope formula, you need 3 pieces of information: your x value, your y value, and your slope at that point. Next, we're going to find our tangent line for y equals f of x at the point 6, 2. So in this case, instead of giving you the function at this point 6 and telling you it's equal to 2, we're just giving the y value. So we're giving you the points of our x and our y here. And we're saying that it passes through 0, 1. And what we want to do is we want to find, we want to find f6, and we want to find f prime at 6. We want to find the function at 6, and we want to find the derivative at 6. So what we're going to do in this case is we have 2 points, right? So we're going to go back to that. Our first point we have is 6, 2. So we have a point 6, 2, and we have another point 0, 1. And we want to figure out what is the difference between the two. So in this case, we're going to have that our slope is going to be y2 minus y1 divided by x2 minus x1. Well, y2 is going to be 2 minus y1 is going to be 1 divided by x2 is 6, x1 is 0. So we're going to get 2 minus 1 over 6 minus 0, or 1/6. So now we have the slope for our line. This is f prime of x, right? Because our slope is our derivative. We have our derivative, which is going to be the slope, and our slope is 1/6. And now that we have this slope, we have a point, we can actually find the formula for our line. In fact, I'm going to show you that we can actually do it using either of these. So the first one we have is y, well, first of all, let's write down our formulas. Y minus y1 equals m, x minus x1. So the first one, I'm going to plug in 6 and 2. So I have y minus 2 equals 1/6 x minus 6. So of course, if I were to distribute this 1/6, this becomes y minus 2 is equal to 1/6 x, and then minus 6 times 1/6 is going to be minus 1. I'm going to add 2 to both sides, and this is going to become y equals 1/6x plus 1. Now, what if we had plugged in 0, 1 instead? Okay, so we have y minus, my y is 1, equals m, which is 1/6, x minus, my x1 is 0. So this is going to be y minus 1 equals 1/6 x. Add 1 to both sides, and I get y equals 1/6x plus 1. And you will see that these two are exactly the same. So if you have your slope and you have a single point, as long as it is on that function, then it will give you the line, the tangent line at that point. If I have 2 points and they're both on that same line, in this case, because this is a line, then it is going to be the same regardless of which point I choose, right? Because if I took the tangent line here, it's the same as the tangent line right here, or it's even the same as the tangent line here. It's the line because the tangent line is the same on all of them because it's constant, right? So this is the thing, is that the tangent represents the rate of change, and in this case, it's constantly changing at a constant rate. So therefore, no matter what point I pick on this line, I will get the same formula for this line. If I had a function that was not changing at a constant rate of speed, for example, let's say it's something like this, this really doesn't work, because if I have a point here, my tangent's going to be something like that. If I have a tangent here, it's going to be something like that. If I have a tangent here, my line's going to be something like that. If I have a tangent here. So notice each of these would have a different line. But if it's a line, which means constant rate of change, this does work. Any point on the line will give you the same tangent line. So that's it for our introduction to derivatives and how we would solve them using our basic definition of what a derivative is, which is a limit as the distance from some point x gets infinitesimally close, so basically as h approaches 0, to that a value of interest. And as that happens, our f of a plus h, which is f of a plus the distance between the 2 points, as that distance becomes closer to 0, they become they merge kind of together, right? So f of x becomes similar to your f of a. And then from there, we were able to solve for what the instantaneous rate of change is. In our next lesson, we're going to be looking at what are some rules we can use to actually make calculating derivatives a lot simpler, a lot faster, and allow us to do a lot more complex derivatives. Because you can see like the way that we're doing it, this, by the way, is true. It always works. But sometimes if we have an overly complex function or set of functions we're trying to take the derivative for, then it might be very difficult because just very complex algebra to get it into the form that will allow us to eventually solve it, especially if we're trying to solve it analytically. Now we're going to be looking at rules on how can we solve basically any derivative for any function, no matter what it is. Hello everyone. In this lesson, we're going to be learning about the derivative as a function. So first, we talked about the fact that a derivative is just the instantaneous rate of change at a particular point. So looking at our derivatives, if we wanted to look how to graph our derivative, we first have a couple things to consider. If we have the derivative of f of x is equal to 0, where f of x, this is where f of x has a minimum, a maximum, or a point of inflection. So if we were trying to graph this, what this means is that the derivative would be 0 wherever you have, for example, something like this, where it goes from going upward to going downward. So the derivative at this point, if we were to take it, we would have a tangent line that is horizontal. If we were to have it going from downward to upward, again, we would have a derivative that is equal to 0. Or if we had an inflection point, which is to say it looks like it goes flat and then it goes the same direction it was going. So in this case, we also would have a derivative that is equal to 0. So this would be how you would graph having a derivative equal to 0. And we'll use this later on when we look at our derivative rules and tests to check whether we have a maximum, a minimum, or an inflection point. If we have that our derivative is greater than 0, this means that the direction of your graph is that it's increasing. Remember, this is the rate of change of your graph, not the graph itself. So the function in this case right here, if we were looking at this, our function is going up. But if you look at the rate of change, what's happening with this function is that while it is going up, the rate of change is that it's going down. So this means that the rate would be decreasing. And then what's going to happen is we're going to have a certain point where about here, where this kind of goes from decreasing to now suddenly it's increasing. So you can kind of see that if you kind of follow it, this is increasing. So if f prime of x is greater than 0, it means that our rate of change is going up. It's increasing. If our derivative f prime of x is less than 0, this would mean that our rate of speed is decreasing. So in this case, we have this is increasing, this is decreasing, and when it's equal to 0, it's either a minimum, a maximum, or it's an inflection point. So this is really important to think about because when you're thinking about the derivative, again, it's the rate of change of your function. Think of it like you're driving a car. A positive derivative means that you are going forward. A negative derivative means that you are going backwards. If you were looking at the function, a positive function means that you have gone some distance forward. A negative function means that you've gone back some distance. And the second derivative actually tells you about how this rate of change is changing, right? So in this case, let's look at this function here for a second. In this function, this point is negative, meaning that the function is negative at this point, meaning that it is, if you were, again, driving a car, it means like you're back some distance from where you started. Up here, we have that the function is positive, meaning that you are forward some distance. The rate of change is that from this point to this point, you were in fact going forward, right? You're going forward, you're still going forward, but like I was talking about with your derivative being the rate of change, is that if we look at this, I was actually talking more about the second derivative, which is the rate of change of the rate of change, which would be that while we are going forward, we're slowing down. And then here, we're continuing to slow down until we get to a certain point, and now we start to speed up. So this is why you have to kind of think about rate of change and the actual position and the rate of change differently. Because again, using the car analogy, function tells you where you're located. Did you go are you forward or are you back from where you started? The derivative tells you the direction that you're progressing, right? So I may be forward a mile, but I'm backing up. Or I may be back 100 feet, but I'm going forward. It's telling me the direction of movement. The second derivative, which for position, the first derivative would be velocity, the second derivative would be acceleration. I can be going 70 miles an hour, but slowing down. Or I could be going 20 miles an hour and speeding up. So if my second derivative was 0, means my rate of change, my velocity, is not changing, meaning I'm maintaining a constant speed. If I have a 0 derivative, it means I'm not moving. It means that while I might be in a forward position from where I started or behind where I started, I am not moving currently. I'm not going forward. I'm not going backwards. So this is why you have to kind of think of the derivative as the rate of change of whatever your original function was. And of course, if you take the second derivative of that, it would be the rate of change of this rate of change. How is this changing? Is it getting higher? Is it getting lower? So now let's talk a little bit about our notation for derivatives. The most common notation we're going to use is the one I used previously, which is going to be this f prime of x. And this means that I'm taking the first derivative. If I was taking the second derivative, in this case, you would add more tick marks for each derivative. So this would be the second derivative, 3 tick marks for the third derivative, and then after that, you kind of start doing a number, right? So you'd say something like the fourth derivative of x, something like this. We also could see the fact that because our function, right, if we start with f of x, is equal to y, you could also write the derivative as y prime. Or the more precise notation we might be used later on, basically, especially if we're doing things with different variables, is we might do something like dy dx. And what this means is I have some function y, and I'm taking the derivative with respect to x. This is the variable that's within my function. Or you might see sometimes something like df dx, so the derivative of this function. Now, this is going to be really important later on, because later on, if we have more than one variable that we're looking at, we may have to specify, for example, if I have the term xy, which has both x and y in it, am I taking the derivative dy dx? Am I taking this derivative with respect to x? Or am I taking this derivative with respect to x? And this is going to be super important later on, again, when we have more than one variable. Your differentiation operators, you might see something like this. We also might sometimes write d dx f of x. And this just would be the same sort of thing as here. So we're taking the derivative with respect to x of some function f of x. You may also, in some books, see a capital D representing the derivative. So it would be d f of x. Or you might see, again, if you want to specify with respect to which variable, you might see d with a little sub x f of x. And these are all ways that we can write derivatives. Now, this is the notation that we use based on the fact that most calculus that we do is based on Leibniz notation. If you were to go further back in time into text, if you were to look at things based on Newton's work, you would actually see completely different notation for when he was dealing with what he called things like fluxions and things like that. So even though, everyone generally says that Newton created calculus, there is some controversy over that, because him and Leibniz kind of co-created it separately at the same time frame. Well, we use this sort of notation because while Newton is kind of given precedence of creating calculus for the most part, this notation is a lot easier for most people to work with, to understand. It's a little bit more precise, and it just works a little better in most cases. Now, going back to what we talked about previously with continuity, if our function f is differentiable at some point a, then it's continuous at a, though continuity does not imply that it's differentiable. So that is to say that if we had something like the function f of x is equal to the absolute value of x, right? We have an absolute value, so if we were to graph this, it would look like this. In this case, this is continuous, right? It has a derivative that is approaching a specific point from the left, the same point if you take the limit from the right, and the point does exist. This is continuous, but it's not differentiable at 0. So if you can take the derivative of some function, it is continuous. But just because a function is continuous does not mean that it's differentiable, because the derivative of this would be equal to, well, it does not exist. So it doesn't equal anything. Does not exist. So let's do an example using our definition of a derivative. So let's say that we have the function f of x equals the square root of x. And we want to find the derivative f prime of x. So the first thing we're going to do, we're going to use our definition of a derivative, and we are going to take the limit as h goes to 0, and we're going to use f of x plus h minus f of x divided by h. So just like before, when we were first looking at how we can do this, we have f of x is equal to the square root of x. So what we need now is we need to figure out what is f of x plus h. So if we were to then just plug x plus h into our square root, we would get the square root of x plus h. So now we can find our derivative by taking the derivative f of x is equal to f of x plus h, which is going to be the square root of x plus h minus f of x, so the square root of x. And then, of course, we're taking the limit as h approaches 0, forgot to write that in, and divided by 0. Now, let's go back to our tricks and rules that we used when solving limits. So in this case, if I were to just plug in h goes to 0, I would get a 0 in the denominator. So we're not going to be able to do that. So just like before, you could try dividing by the highest power of whatever's in the denominator. In this case, though, all you would end up with is square root of x plus h over h minus square root of x over h, and then h over h, this term would go away. You'd be left with the exact same thing. The only thing is basically it's like you split it, which you can do right now. So what we're actually going to do is we're going to multiply by its reciprocal, like we did previously. So I'm going to multiply this by the square root of x plus h plus the square root of x. And of course, anything I do, I have to do it over itself, so it's equal to 1. So this is going to be x plus h plus square root of x. And now that I have this, I can solve this out. So what do we get? We do our first, outer, inner, last. So first, we're going to get that this is equal to the limit as h goes to 0. And then this is going to be square root of x plus h times square root of x plus h. This is going to be x plus h. And then for our inner and outer terms, we're going to get minus square root of x times the square root of x plus h plus the square root of x times square root of x plus h. So those two are going to cancel. And then we're going to have minus square root of x times square root of x. So that's going to get rid of the square root, and it's going to be minus x. And then this is going to be divided by h square root of x plus h plus square root of x. Okay, so now, next step, we have our x, we have a minus x. So now we have h over h times square root of x plus h plus square root of x. Well, our h's can cancel. So then this is going to be the limit as h goes to 0, 1 over the square root of x plus h plus the square root of x. Now, I can plug in this h goes to 0, because if I plug into 0, wherever I have an h, this is going to give me, and remember, I'm evaluating my limit, so the limit goes away now. This is going to be 1 over the square root of x plus 0 plus the square root of x. So square root of x plus 0, just square root of x. We have square root of x plus square root of x means that I'm going to get 1 over 2 square root of x. So I have my derivative. This means that whatever x point I have for this function, f of x, which of course, based on the fact that it's square root, we have that x has to be greater than or equal to 0. So whatever x value we have, that's going to be our a, right? That's the point that we're taking our limit as it approaches. This will be the derivative at that point, 1 over 2 times the square root of that x. So let's say my x value was 4. This would be 1 over 2 times the square root of 4, or 2. So 1 over 2 times 2, or 1/4. So what's happening is that if we were to look at what this looks like, it looks something like this. So what's happening is as we go to the right, our derivative is getting smaller and smaller and smaller as my x increases. And this will be true for our domain that x is greater than or equal to 0. So in this case, we would have that our domain is 0 to infinity. But if you look at our derivative here, what's going to happen if we plug in 0 in for our x? We're going to get 1 over 2 times 0. So we can't actually do x equals 0. So instead, our domain is going to end up becoming 0 to infinity with parentheses, because 0 actually can't be included, because we have to consider now what can be plugged in for our function, but also what can be plugged in for our derivative. Now let's do a slightly more complicated example. Let's say that we have the function f of x is equal to 1 minus x divided by 2 plus x. So we have this function and we want to find our derivative. So as always, we're going to be using the fact, I'm going to write it down here, so I'll just continue on with it. We're going to take the limit as h goes to 0, f of x plus h minus f of x divided by h. So we have f of x, right? That's our function that we're given. We need to figure out what f of x plus h is. So f of x plus h is going to be, wherever there's an x, I'm going to plug in x plus h. So this is going to be 1 minus x plus h, which is going to be, I'm going to distribute that minus, so it's going to be minus x minus h, divided by 2 plus x plus h. So this is my f of x plus h. So I'm going to plug these values into this, and we're going to get the limit as h goes to 0, f of x plus h, this is going to be 1 minus x minus h, divided by 2 plus x plus h, minus f of x. So we're going to subtract this entire thing. 1 minus x over 2 plus x. All of this divided by h. Now for this case, I have two fractions with different denominators. So what I'm going to do is I'm going to multiply this first fraction by the denominator of the second fraction. For the second fraction, I'm going to multiply it by the denominator of the first fraction to get them in terms of the same denominator. So this is going to end up being the limit as h goes to 0, 1 minus x minus h divided by 2 plus x plus h times, and then of course, remember, I'm actually just multiplying by 1, so this has to be 2 plus x divided by 2 plus x. And then now I'm going to go to my second term, so minus 1 minus x divided by 2 plus x times, and again, I'm going to do the same thing with the denominator from the first fraction. 2 plus x plus h divided by 2 plus x plus h. And then, of course, still all divided by h. So this is going to end up equaling, first of all, now both of these are going to have denominator 2 plus x plus h times 2 plus x. So I'm just going to leave that the way it is for now. I'm just going to put that this is 2 plus x plus h times 2 plus x, and put those in parentheses. So this is going to be the denominator now for the new fraction. It's going to be really big. And we're going to distribute these terms together. So we're going to have 1 times 2, so 2, plus 1 times x, so x, minus 2x, minus x squared, minus 2h, minus xh. And then remember, this is going to be minus this entire thing. So minus, I'm just going to put this in parentheses now so we don't lose track. We'll distribute it after. 1 times 2, so this is going to be 2. 1 plus x plus h minus, so that'd be, in this case, it's going to end up being plus, minus x, 2x minus x squared, and then minus xh. Oops. Minus xh. And then I'm going to distribute this negative just to make this a little bit easier, so we're doing cancellation. So by getting rid of this parentheses, this is going to be minus 2 minus x minus h plus 2x plus x squared plus xh. So we're going to take the limit still as h goes to 0, and this entire thing is still divided by h. So now we're going to see if we can do any cancellation, which we will, because that's the whole reason of multiplying by, getting everything in terms of everything. So this 2 is going to cancel with this minus 2. This x is going to cancel with this minus x. This negative 2x is going to cancel with this 2x. This negative x squared is going to cancel with this positive x squared. This minus xh is going to cancel with this positive xh. And then we have minus 2h minus h. So this is going to end up giving me the limit as h goes to 0 minus 3h divided by 2 plus x plus h times 2 plus x, and then this entire thing divided by h. So as always, what I'm going to do now is I'm going to do fractional division, right? So you're going to do multiplication by the reciprocal, and you can think of this h as h over 1. So this is going to take the term and flip it. So this is like bringing the h up to this term and the 1 up to the top. So I'm going to have an h here and a 1 here. This h will cancel with this h, and I'm left with the limit as h goes to 0 minus 3 divided by, and then this whole thing, 2 plus x plus h times 2 plus x. So at this point, I can actually evaluate my limit by plugging in h goes to 0. So in this case, if we do this, this term is going to go to 0. And now that I've evaluated my limit, I don't have to include the limit anymore. This is going to be minus 3 over 2 plus x times 2 plus x, which is just going to be minus 3 over 2 plus x squared. And as other times we took the derivative, this means that as my x from my original function changes, this is going to change what the derivative is in this case. For our next example, let's say that we have the function f of x equals x squared minus x. So if we were to graph this, it would look something like this. Okay, I'm going to create my Cartesian plane, and I know that it's going to cross at -1 and +1, and it's going to look something like this. And the reason I know this is because if I took the derivative, this is the function f of x. The reason I know this is because if I were to plug in 0, I would have 0 minus 0 equals 0. If I were to plug in -1, I would get -1 squared is 1. I get 1, so that'd be +1. So I know it's going to cross at 0 here, here, and here. Now what I want to do is I want to graph the derivative function for this. So what we're going to do is we're going to be looking at what is the direction at any given point. And from there, we can write where it's going to be on this graph. So first thing we're going to focus on are these points where it crosses 0, right? Because our derivative is looking at where on the graph, like what direction are we facing, right? So in this case, we have that we are going up at this point, we're going down at this point, and we're going up at this point. So if I were to now consider where is my derivative going to be equal to 0? So my derivative is going up until it reaches this point right here. My derivative is going downward until it reaches this point right here, and then from there it's going up. On your derivative graph, wherever it is going up, that is to say that your f prime of x is greater than 0, it's going to be in the upper 2 quadrants. Wherever your derivative is less than 0 or negative, it's going to be in your lower 2 quadrants. And where it's equal to 0, which would be here and here, this is where it's going to be crossing your x-axis on your derivative graph. So we know that this is going to be between 0 and -1. So let's say that this is -1. We know that it's going to cross in between the two, I think at -1/2 probably, something like that. And we also know that it's going to cross somewhere between 0 and 1. So from there, we just have to look at what side or what direction is it going from this case? Well, in this case, to the left of this, it's in the positive, right? So it's going up. That means that it's going to be somewhere over here. And then once it hits that 0, now suddenly my derivative is negative. So I need to be drawing it in the negative part of our graph until it gets to this point where now it becomes positive. So in order to be in the negative, but to go positive after that, I would have to come back up and cross this point. So my derivative would look something like this. Now, one thing when you're graphing derivatives is it kind of throws people off at first because you have to consider the direction, right? So here, the function is negative. Here, the function is positive. Function is negative, function is positive. For the derivative, it's the direction. Direction is positive, direction is negative, direction is positive. Another thing, though, is whenever you're taking a derivative, every derivative you take, you will have one less curve in your graph, meaning that if I took the derivative of this, because it has 2 points where it goes from positive to negative back to positive, in this case, your derivative is only going to have 1 from negative to positive. Let's take it one step further. Let's say, what would the second derivative graph be? So I'm going to take the derivative graph of this. Well, again, I'm just going to roughly draw this one. If we consider right now, what's the direction of this graph? It's going negative, meaning that I know that I'm down here until I reach this point where now suddenly the derivative is equal to 0, and now it's positive. So the second derivative graph would look like this. Notice that we went from 2 curves to 1 curve to 0 curve. Each time you take a derivative, you will be losing 1 curve at least from your graph. So if you look at the slide here, you can see an example though of what we just drew by looking at our function graph and then drawing our derivative graph based on that function. Now we're going to do an example that's really going to kind of set up the next section. Let's say that we have the function f of x is equal to x cubed minus x. And I want to find the derivative of this function. And then I want to find the second derivative of this function. I want to find the third derivative of this function. And then I want to find the fourth derivative of this function. And the reason we're going to do this is because I really want to kind of show that for every derivative you are performing when you do a derivative using calculus, you are actually using the form that we have done so far in this section, right? We're using the form that the derivative of x is equal to the limit as h goes to 0, f of x plus h minus f of x over h. But in the next section, we're going to be learning derivative rules, which is going to make this all significantly easier. So while you do have these rules you'll learn, which will allow you to solve derivatives significantly faster, significantly easier, this is actually what you're doing in the background, right? These rules are just cases of the fact that if you were to do this, these things also will be true. So you're kind of shorthanding it, right? You're using a trick to go much faster. You're doing this in the background, but what you're actually performing is a much more simple and mechanical calculation. So while it's doing this in the background, what you're actually doing is performing a much simpler and mechanical operation when you do this. So as always, first things first, let's figure out what our f of x plus h is. So if f of x is x cubed minus x, my f of x plus h is going to be x plus h cubed minus x. Now what I'm going to do is I'm going to distribute out this cube function. So this is going to be x plus h times x plus h times x plus h, and then minus x. So first thing I'm going to do is I'm going to distribute this term. So this is going to be first, right? So we do first outer, inner, last. This is going to be x squared. Then we do outer plus xh, inner plus xh, and then last, which is going to be plus h squared. So of course, this is still multiplied by x plus h, and we then have minus x. These two terms together are 2x plus 2xh. Now I'm going to do the same thing. I'm going to distribute this, so this x squared times this x is going to be x cubed. X squared times h is going to be plus h. plus, now I'm going to use my 2xh. So 2xh times x is going to be 2x squared h. Now 2xh times h is going to be plus 2xh squared. And then h squared times x is going to be plus, I'll just do xh squared. And then h squared plus h is going to be plus h cubed. And then, of course, don't forget my minus x. Now we're going to see if there are any terms that I can bring together. I've got an x cubed term, I have an h, and I have an x squared h, I have an xh squared, I have another xh squared, I have an h cubed, and I have an x. So the only terms that look like they can come together are going to be these two. 2xh squared plus xh is going to give me 3xh squared. So now it's time to plug this into this. So let's do it. We have the limit as h goes to 0, f of x plus h. So we're doing this part now. So this is going to be x cubed minus, I'm going to try to put some of my like terms closer together. So this is going to be minus 3x squared h plus 3xh squared. Wait, did I miss one here? I did this. So 3xh squared and then 3x. I forgot to write down a term. I forgot to do, when I was distributing this, I had the x squared times h. I forgot to put the xh squared. So this actually would go also to, or sorry, x squared h. So this would actually go to 3x squared h also. So just, I missed that when I was doing my distribution. It's a little bit easier when you're writing this on paper than on the board. But okay, so we'll continue on though. Plus h cubed minus x minus h, and then minus our f of x term, which is going to be minus x cubed plus x. Cool. So now this is all divided by h, and I'm going to cancel out this negative x with this positive x, and I don't have, where's my x cubed? And then x cubed and minus x cubed. So these are going to cancel out. So I'm left with the limit of negative 3x squared h plus 3x squared h. Sorry, this should be plus. I don't know why I put a negative there. 3x squared h plus 3xh squared plus h cubed minus h over h. Every term in this has an h. So what I'm going to do is I'm going to pull an h out. So this is going to be the limit as h goes to 0, pull an h out. This is going to be now, so we have 3x squared h, this is going to be 3x squared, plus 3xh squared is going to leave me with 3xh, plus h cubed, pull an h out, I get h squared, and then minus h, I am left with minus 1, all divided by h. These will cancel. And I have 3x squared plus 3xh plus h squared minus 1. Now I'm going to evaluate this limit. I'm going to plug in 0 anywhere I have an h. So when I evaluate this, 3xh, so 3x times 0 is going to go to 0. 0 squared is going to go to 0, and I'm going to be left with 3x squared minus 1. So this is the derivative for this function. That's our f prime x. We have that it is 3x squared minus 1. Now we're going to take the second derivative. So we're going to do the same thing. So we have f double prime of x is going to be the limit as h goes to 0, f of x plus h minus f of x divided by h. But now this is our f of x that we're going to be using here. So this is going to be the f of x we plug in here. So let's figure out what f of x plus h is. So f of x plus h, we plug in x plus h wherever we have an x here. So this is going to be 3 times x plus h squared minus 1. This is going to give us we got to do our square first. So 3 times first, which is going to be x squared. Outer inner is going to be plus 2xh, and then last plus h squared, then minus 1. Distribute the 3. This will be equal to 3x squared plus 6xh plus 3 h squared minus 1. We're going to take this, we're going to plug this in for our f of x plus h. We're going to take this, plug it in for our f of x, and we're going to do the same operation, figure out what our second derivative is. So this is going to be the limit as h goes to 0, 3x squared plus 6xh plus 3h squared minus 1 minus f of x. So minus 3x squared plus 1. All of this divided by h. So the 3x and the minus 3x cancel with each other. The minus 1 and plus 1 cancel with each other, leaving us the limit as h goes to 0, 6xh plus 3h squared divided by h. So I'm just going to pull an h out while I'm rewriting this. So I'm going to pull h out, and this is going to give me. So 6xh will be 6x plus 3h squared will leave me with 3h. Divided by h, the h's cancel. And now I'm going to evaluate this where h equals 0. Well, if h is equal to 0, this term is going to go to 0. I'm going to be left with 6x. So this is going to be my derivative or my second derivative of this function, that is equal to 6x. And you'll notice each time it's going to get easier. Now let's take the third derivative, which is again going to be the limit as h goes to 0, f of x plus h minus f of x divided by h, where this is now my f of x for the third derivative, right? Because if I think of this as the function, this would be the derivative of that. So this is going to be my f of x, so I got to figure out what my f of x plus h is. Well, this one's actually pretty easy because f of x plus h is just going to be 6 times x plus h, which is equal to 6x plus 6h. So plug it into this, we get 6x plus 6h minus 6x. And of course, we're taking the limit of this as h goes to 0, and this divided by h. The 6x and the minus 6x cancel with each other, and we're left with the limit as h goes to 0, 6h divided by h, which the h's will cancel. So I have the limit as h goes to 0 of 6. Well, if you remember from our limit rules, the limit of a constant is just the constant. So finally, we're going to take the fourth derivative. So if we were to take our limit as h goes to 0, f of x plus h minus f of x divided by h, if this is f of x, and if I were to plug in x plus h anywhere there's an x into this function, what would I get? Well, there is no x. So this means basically that it's going to be 6. So 6 minus 6 is going to be 0 divided by 0. Basically, what's going to happen is you're going to do, if you were to follow through with the steps for this, you're going to end up getting that we have, here, let me just write it out. F of x plus h is equal to 6. F of x is also equal to 6. So this is going to end up becoming the limit as h goes to 0, 6 minus 6 over h, which is going to be the limit as h goes to 0, 0 over h, which in this case is, as this goes to 0, it's just going to equal to 0, right? Because the derivative of a constant is going to be 0. So now what we've done is we started with this function, xh cubed minus x. We found the derivative, we found the second derivative, we found the third derivative, and we found the fourth derivative. And notice what happened each step of the way. For the first derivative, we got that it went from a cube function to a square function. For the second derivative, it went from a square function to a x to the first power function. The next time we took a derivative, it went to a constant, and the next time it went to 0. So what's happening each time is that our derivative is going to be 1 power less until we get down to 0. So you can continue taking the derivatives. Now in the next section, we are specifically going to be looking at ways that we could calculate this significantly faster. Instead of filling up an entire page of limits, we'll be able to do it in seconds. The last thing I want to talk about before we finish up this section and then move on to the next section on the rules for derivatives, there are a couple examples where we have non-differentiable functions. The first you can see here is when you have these sharp corners. So in this case, we have some function that is coming from the left and it's increasing until it reaches some sharp point and then it goes decreasing from there. In this case, this would be non-differentiable. This sort of is like our example where we did the absolute value. It had a limit from the left, it had the limit from the right, it was continuous, but we said it was non-differentiable, and that was why, because it had a sharp corner. The second example you can see here is when you have discontinuous functions. That is to say, if you have a jump or missing point at that point, things like that. Derivatives do rely on the fact that your function is continuous. And the third is if you have a vertical tangent. That is to say, if you have some point on your function where you end up having a vertical line where if you were to take the tangent, it would be a vertical line, because this would end up being a case where you're dividing by 0 and it causes all sorts of problems. So that's it for this lesson. In the next lesson, though, we're going to learn all about some of our derivative rules, which will make doing derivatives significantly easier and a lot faster. Hello everyone, in this lesson we're going to be talking about our basic differentiation formulas. So if you watched my previous lesson, you'll remember that we did a fairly long limit where I showed you as you took the first, second, third, and fourth derivative how it took a lot of steps, there was a lot to it, and now we're going to find some rules or differentiation formulas which will make doing differentiation a lot easier. So our first differentiation rule is that if we have the derivative of a constant. That is to say, if we take some derivative, d dx, so derivative with respect to x, of some constant c, the derivative will always be 0. Because remember, a derivative is a rate of change. A constant is not changing, right? So for example, if I had that f of x equals 4, and you say, okay, well, how much is it changing? Well, it's not. It's always going to be 4. So the derivative of a constant is equal to 0. The next is our power rule. The power rule is that if we have some d dx of some function x to the nth power, the way that we can solve this one is it's going to end up being n times x to the n minus 1 power. Meaning, if, for example, if I take the derivative of x to the 4th power, I would bring the 4 down, so this becomes 4x to the n minus 1, or 4 minus 1, or third power. So it'd be 4x to the third power. Our third rule is the constant multiple rule, which is if we have d dx and we have some constant times our function f of x, this will be the same thing as taking the constant times the derivative with respect to x of our function f of x. So what does this mean? It means something like, for example, if I have 3x to the 4th, like we were just looking at, x to the 4th, this would be the same thing as if I took the derivative of x to the 4th times 3, or whatever number it was that I said. So you could actually pull that constant out, take the derivative of the function, and then multiply that by the constant, and you'll get the same derivative. Okay, so now we have the sum and difference rules, which is to say, if I have the derivative d dx of two functions, f of x and g of x, so plus or minus g of x, this is going to be equal to the derivative of f of x plus or minus the derivative of g of x. And this is just like when we did limits. If I had the limit of some function f of x plus or minus g of x, I could take the limit of f of x plus or minus the limit of g of x. This still holds true for derivatives. So if I have the derivative of f of x plus or minus g of x, this will be the same thing as the derivative of f of x plus or minus the derivative of g of x. Our next rule is whenever we take the derivative of a natural exponential function, that is to say d dx of e to the x, this is just going to be equal to e to the x. So this is actually one of the easier functions to do. Now later on we will learn more about this when you have something that's more complex within the power. For example, this will be using something called the chain rule, which we'll talk about later. But for now, if you have e to the x, take the derivative of it, and you're just going to get out e to the x. And then a couple more for some trig functions. If we have the derivative d dx of sine of x, this is going to be equal to cosine of x. And if we have the derivative d dx of cosine of x, this is going to be equal to negative sine of x. So these are some of our basic building blocks we're going to be using as we start building out our derivative rules that we can use. So these are always going to be useful, right? If you ever have a derivative of a constant, it's always equal to 0. The power rule, that's what we're going to be focusing on mostly in this section. If you have a constant times some function, you can take the derivative of the function, then multiply it by the constant. If you have the derivative of two functions added or subtracted, you can take the derivative of the first, added or subtracted to the derivative of the second. If you have the derivative of the e to the x function, then you'll just get out e to the x. If you have the derivative of sine of x, you'll get out positive cosine x. If you take the derivative of cosine x, you'll get out negative sine x. And then, of course, you can actually kind of go back and forth with this. So if I took the derivative of that negative sine x, sine x, right, you could think of this multiplying by -1. This would become cosine x times -1 or negative cosine x. If I did the derivative of negative cosine x, I would get negative sine x, which would be positive sine x. And basically, it's just going to cycle through them every 4. So let's look at some quick examples. Let's say that we have, by the way, I'm going to leave these rules here as we work through the problems, so you always have them to reference while we're looking at this. Let's say that we have the function f of x is equal to e to the x minus x. And we want to take the derivative, the second derivative, and the third derivative. So using our definition of a derivative, what we would have had to do is we would have had to take the limit as h goes to 0, f of x plus h minus f of x divided by 0. So we'd have to divided by h. We would have had to plug in x, this would be our f of x. We would have had to plug in x plus h in each of these. We would have had to then solve for this, get rid of the h in the denominator, solve for as h goes to 0, and you would get your first derivative. Then you'd have to do the same thing for the second, same thing for the third, any derivative you want to do. But what we're going to do now is we're going to be using our rules. So we have f prime of x, which we're going to be looking at the fact that we have the derivative of e to the x minus x, which using this rule right here, we have e to the x, we have x, and they're subtracted from each other. So this is going to be the same thing as taking the derivative d dx of e to the x minus d dx x. Now, again, using our rules, what is the derivative d dx of e to the x? Well, according to rule 5, this is just going to be e to the x. Okay, what would be the derivative of, what would be the derivative of x? Well, you could think of this x as x to the 1. Using our power rule, if I have x to the 1, I bring down the 1, and then I have x to the n minus 1. Well, n in this case is 1, so if I have x to the 1 minus 1, this is the same thing as saying I have x to the 0. So this would be e to the x minus 1 x to the 0. Anything to the 0 power is just equal to 1, so this ends up being e to the x minus 1. So the next thing we're going to do, we're going to take our second derivative. So this is going to be f double prime of x. So we're going to take the derivative of this function. So this is going to be d dx e to the x. And we're going to split it because we have minus some other function. In this case, it's 1. So this is going to be d dx 1. Again, looking at our rules, derivative of ex, e to the x, is going to be equal to e to the x minus derivative of a constant, 1 is a constant, is equal to 0. So e to the x minus 0 gives me e to the x. And then if I take my third derivative, I'm going to take d dx of e to the x, which is just going to be e to the x. And just like we talked about previously, what happened with my original function as I took the derivative? Well, e to the x doesn't change, but I went from x to the 1 to x to the 0 to a constant that then just goes to 0. So each time it got less complex as I took the derivatives. So now what we're going to do is we're going to take some functions and use the power rule to solve for them. So our first function is going to be f of x is equal to x to the 6th power. So using our power rule, what's going to happen is we're going to pull, so we take the derivative, we're going to pull that 6 down. So we're going to get 6 x to the n minus 1, or 6 minus 1, which is going to be 6x to the 5th power. If we had y is equal to x to the 1000 power, using 1,000, we're going to use the same rule. What's going to happen is that we're going to pull out 1,000. This is going to be x to the n minus 1, so 1,000 minus 1 would be x to the 999th power. If we had g of x is equal to 7, when we take the derivative of this, so we have g prime of x, this is going to be the same thing as saying 7x to the 0. So what I would need to do now is I would pull this first term down, right? So I pull my n down. In this case, it's going to be, actually real quick, if you want to be technical, we're actually using this one first. Constant times a function. If we take the derivative of that, is the constant. So this is actually going to be 7 d dx x to the 0. So now let's do that. So we have 7 times, I have a 0 in power, I'm going to bring that down, 0, x to the negative 1. Well, anything times 0 is going to be what? 0, and then 0 times 7 is also going to be 0. Our next function, h of x, is going to be 3x to the 4th power. So again, we're going to, if you wanted to kind of follow all these rules, generally we just do it all in one step, but just to be precise, this is the same thing as taking 3 times d dx x to the 4th. So I'm going to bring that 4 down, so this is going to be equal to 3 times 4 x to the 4 minus 1, or 3rd power. This is going to give me 12x cubed. My next function, f of x, is going to be equal to 1 over x squared. So this one is a little bit more complicated because we have to actually put it in terms of a power. So if I have 1 over x squared, remember, a negative power will take something from, if you have it up in the numerator, it'll bring it down to the denominator as a positive. If you have something in the denominator that is positive, it's the same thing as saying that I have x to the negative 2. Taking our power rule, my power is negative 2. So I'm going to pull that negative 2 down. So it'd be minus 2x, and then n minus 1. Negative 2 minus 1 gives me negative 3. And then if I wanted to write it back in its original form, this would just be equal to negative 2 divided by x cubed. And then the last one we'll look at for now is going to be if we have hx is equal to the cube root of x squared. So as before, when we have some power that's in the denominator, you could switch it by making it a negative power. The root function is a fractional power. So this would be x squared to the 1/3, or x to the 2/3 power. So we have x to the 2/3 power. We're going to use the same rule though. We're going to bring down our n, which in this case is 2/3. Oops. This is not true. This is h prime of x. So we're going to bring down our 2/3. So this is going to be 2/3 x to the n minus 1. So 2/3 minus 1. So 2/3 minus 3/3 is going to be negative 1/3. Now, if we wanted to write it back in sort of its original form, this is going to be equal to 2 over 3 x to the negative 1/3. Well, x to the 1/3 would make it a third root or cube root. The negative is going to bring it into the denominator. So this is going to be 2 over 3 times the cube root. Let me write that because I made it too small. This is going to be 2 over 3 cube root of x. For our next example, what we're going to do is we're going to find the tangent line and the normal line, which is the line that's perpendicular to the curve y equals x square root of x at the point 1, 1. Because we're going to need some specific point to find the tangent line, right? Because the derivative tells us the instantaneous rate of change at any given point. To find a tangent line, we have to know what point we're finding the tangent at, and then from there we can figure out what the normal line is to it so that it's perpendicular. So the first thing we're going to do is we have this function f of x is equal to x square root of x, which I'm going to rewrite in terms of a power so I can use my power rule. So this is going to be equaling f of x equals x times the square root of x is just going to be x to the 1/2. Now, if you watched our review or you just remember how to deal with powers, you can consider that x to the 1/2 times x, which is x to the 1, you just add those two powers together. So this would be x to the 1 plus 1/2, or x to the 3/2 power. So what we're going to do first now with this is we're going to take the derivative in order to figure out what is my instantaneous rate of change. So this is going to be d dx x to the 3/2. So using our power rule, we're going to bring down 3/2, x, and then this is going to be n, so 3/2 minus 1. Well, in this case, 1, because I want it to be in terms of halves, would be minus 2 over 2. So 3 over 2 minus 2 over 2 is going to leave me with 3/2 x to the 1/2 power. And then, of course, rewriting this in terms that we did when we had our original function, this would be the same thing as saying 3 square root of x over 2. Now what we want to do is we want to figure out where is our tangent line. This is our instantaneous rate of change. But we had a specific point, 1, 1. So if I plug in 1 for x, so f prime of 1, this is going to be 3 times the square root of 1 over 2, which is going to be, so square root of 1 is 1, so we have 3/2. So this is our slope of our line. And now what we're going to do is we're going to use our point slope form for our line, which is going to be y minus y1 equals m times x minus x1, and we're going to plug in 1 and 1 for y1 and x1. So this is going to be y minus 1 equals my slope of 3/2 x minus 1. We're going to distribute our 3/2, so this is going to go to y minus 1 equals 3/2 minus 3/2. I'm going to add 1 to both sides. Cancel. I'm going to get y equals, I forgot my x, 3/2 x, and then we have minus 3/2 plus 1. So just like before, I can make this 2 over 2. So I have 2 over 2 minus 3 over 2, which would be minus 1/2. So this is my tangent line. I have an intercept of negative 1/2. So let's say this is negative 1. I'm intercepting here, and I have a slope of 3 over 2. So it'll be 1, 2, 3, 1, 2, something like this. And now what I want to do is I want to figure out what is the line that is perpendicular to this at that point right there. So what I'm going to do in this case is I'm going to take my slope, which we had was 3/2, and I'm going to flip it and take the negative of it to get the slope of the normal line. So this is going to go to m equals negative 2 over 3, right? Because that's how we would get. So if this is 3 over 2, the slope of this would be negative, and it would be negative 2 over 3. So we have our slope, we have our same point, so then we're going to do the same thing. We're going to have y minus 1 equals negative 2/3 x minus 1, and we'll solve it exactly the same way. Y minus 1 equals negative 2 over 3x plus 2/3. We're going to add 1 to both sides. We're going to get y equals negative 2/3 x. And then so we have plus 2/3, and then this would be 3 over 3. So plus 3 over 3 would be plus 5/3. And this would be our normal line to our tangent line at the point 1, 1. So now that we've looked at some examples of using our power rule, let's look at some examples using our constant multiplication rule, which is this rule right here. So let's say that we had d dx 3x to the 4th power. So if I wanted to take the derivative of this, well, based on our constant times a function rule, what we can do is we can pull that 3 out. So this is going to be equal to 3 d dx x to the 4th power. So this will be 3 times 4x cubed, which is going to give me 12x cubed. If we wanted to take the derivative of the function negative x, you could think of this negative x as negative 1 times x. I can pull that negative 1 out, so this would end up being negative 1, or just negative, d dx x. If I take the derivative of x, which is x to the first power, I pull 1 down. 1 minus 1 for the power gives me a power of 0. This would be equal to negative 1. If I took the derivative, so d dx of negative 6 cosine of x, same idea. The derivative of a constant times some function, I can pull that constant out, so this will be equal to minus 6 d dx cosine of x. And then based on our limit rules, if we take the derivative of the cosine of x, this is going to be equal to negative 6 times negative sine of x. And we have a negative and a negative. This would give us 6 sine x. Let's look at a more complex function to kind of bring some of these rules all together. Suppose we have d dx of x to the 8th power plus 12x to the 5th power minus 4x to the 4th power plus 10x cubed minus 6x plus 5. So if we wanted to do this derivative, first thing I'm going to do is I'm going to split up my derivative into individual derivatives using our addition-subtraction rule. So this is going to be equal to the derivative, so d dx of x to the 8 plus 12, sorry, don't want to skip any steps, d dx 12x to the 5th minus d dx 4x to the 4th plus d dx 10x cubed minus d dx 6x plus d dx 5. I'm going to then focus on these terms that have constants in front of them. So I'll pull those out. So this is going to end up being d dx x to the 8th plus 12 d dx x to the 5th minus 4 d dx x to the 4th plus 10 d dx x cubed minus 6 d dx x plus d dx 5. And now let's solve. So we have x to the 8th power. So we're going to pull that 8 down. So there's going to be 8x to the 7th power. Plus, for derivative with respect to x of x to the 5th is going to be, we're going to pull that 5 down. It's going to be 5x to the 4th power. So 5 times 12 is going to give me 60 x to the 4th power minus derivative of x to the 4th. We're going to pull that 4 down. So this is going to be minus 16x, and then that 4th power goes down by 1, so cubed. Here we have plus 10. We're going to pull that 3 down. So this is going to be plus 30. X cubed becomes x squared minus 6. So x to the 1, we already talked about this. Derivative of x is just going to be equal to 1. So this is going to be minus 6. And then the derivative of a constant is going to be plus 0. So that term goes away. So we have 8x to the 7th plus 60x to the 4th minus 16x cubed plus 30x squared minus 6. And you can imagine plugging this into our definition of a derivative where we're taking the limit of f of x plus h minus f of x over h. This would be a lot more complicated to do because when we did the x plus h, we would have to take into account an 8th power, a 5th power, a 4th power, a 3rd power, and a x to the 1st power. That would be a really long function that we would have to then take the limit of. There'd be a lot of cancellation. You'd be able to do it, but this is so much simpler just using our derivative rules. Now for our next problem, we have y equals x to the 4th minus 6x squared plus 4. And we want to find where this function has a tangent line that is horizontal. So first things first, whenever we want to find a tangent line, we need to take the derivative. So we're going to get y prime is equal to, bring the 4 down, so it's going to be 4x cubed, minus, we're going to bring the 2 down, so it's going to be minus 12x, and this constant is going to go to 0. So we have 4x cubed minus 12x as our derivative. Well, the way that we find where the tangent is equal to 0 is basically what we're saying, remember, is that the rate of change is equal to 0, meaning wherever we have a tangent line that is horizontal. So this would be when it's equal to 0. So we need to set this equal to 0. So we have 4x cubed minus 12x equals 0. What I'm going to do now is each of these terms have an x in them, so I'm going to pull an x out. So we have x, 4x squared minus 12 is equal to 0. So first of all, I can get 0 by plugging in x equals 0. So now let's focus on this term here. Where is 4x squared minus 12 equal to 0? Well, as before, if I wanted to, I could pull a 4 out of this. So this is going to be 4x squared minus 3 is equal to 0. So divide each side by 4. 0 over 4 is 0. So we get x squared minus 3 is equal to 0, which would be x squared is equal to positive 3. So what does this mean? Well, this means then that my x's where I can have this equal to 0 would be x equals negative square root of 3 and x equals positive square root of 3. Because remember, whenever you have a square term, you have to consider that both the positive and the negative can make this true, right? Because if I took negative square root of 3 and I squared it, this would just end up being negative square root of 3 times negative square root of 3. Negative and negative makes it positive. Square root of 3 times square root of 3 just makes it equal to 3. So you have to consider that there's both the positive and the negative. So this means that this function would have a tangent line that is equal to 0 at x equals 0, x equals negative 3, and x equals negative square root of 3, and x equals square root of 3. If we were to plug these back into the original function, we could actually find out those points. So if I were to plug in x equals to 0, I would get 0 minus 0 plus 4. So I would get 0, 4 for the first point where I have a tangent line or tangent that is equal to 0. For the second one, I'm going to plug in the square root of 3. So if I plug in the square root of 3, this becomes the square root of 3 to the fourth power should be 3 squared, which is going to be equal to 9 minus 6 times square root of 3 squared, which is going to be times 3, so minus 18, plus 4, which is going to give me negative 5. And then, of course, if I plugged in positive square root of 3, I would get the exact same value. So negative square root of 3 minus 5. So these are the 3 points where our tangent line would be equal to 0, or that is to say we have a horizontal tangent line. And later on, we'll talk more about this when we talk about maxima and minima. These would be the points where we either have a maximum, a minimum, or an inflection point. For our next example, let's say that we have a position function of a particle that is s is equal to 2t cubed, which t is time, minus 5t squared plus 3t plus 4, where s is going to be measured in centimeters and t is our measurement in seconds. We want to find the acceleration as a function of time and then find out what is the acceleration after 2 seconds. So the first things first is this s of t. This is our position of our particle based on some amount of time. So we have st is equal to 2t cubed minus 5t squared plus 3t plus 4. So we're going to find our derivative to figure out what is the velocity of our particle. So this is going to end up being 6t squared minus 10t plus 3. This would be the velocity. But the question asks us for the acceleration, meaning we want to take the second derivative of our position with respect to time. So this is going to become 12t minus 10. Now that we have our second derivative, which tells us the acceleration, if we wanted to know what is the acceleration after 2 seconds, we would just plug 2 into this. We would get 12 times 2 minus 10, which is going to be equal to 24 minus 10, or 14 centimeters per second squared. The next question we want to look at is, at what point is the curve y equals e to the x, at what point is the tangent line parallel to the line y equals 2x? So what does it mean that if the tangent lines are parallel? It means that the derivative of this, which is of course going to be e to the x, is going to be equal to the derivative of this, which is going to be equal to 2. So pretty much what we're saying is, when is e to the x equal to 2? So we'll set it up with e to the x equals 2, and we want to solve for what x makes this true. So to deal with this e to the x term, what we're going to do is we're going to take the natural log of both sides. So natural log of e to the x equals the natural log of 2. The natural log and the e cancel, and you will get x is equal to the natural log of 2. So this would be the x value for the point for when y equals e to the x is parallel to y equals 2x. So now what we need to do is we need to plug in that natural log of 2 into our original function, which it should be either function, because remember we're saying they're equal here. That means that if we plug that into our original function, we would get natural log of 2 e to the natural log of 2, right? So we have e to the natural log of 2. Again, these two would cancel. You'll just be left with 2. So the point where these two, the tangent lines are parallel to each other, would be natural log of 2, 2. So this would be our x value, and this is our y value. If we have the function y equals 3 sine of theta plus 4 cosine of theta, what would be the derivative for this function? So first things first, let's do y prime is equal to d dx 3 sine of theta plus d dx 4 cosine of theta. And we're going to use our constant rule to pull the 3 and the 4 out. So this is going to be 3 d dx sine of theta plus 4 d dx cosine of theta. Now, using our derivative rules, the derivative of sine of x is equal to cosine x. So this is going to be in this case, theta, would be 3 cosine theta plus 4, and then the derivative of cosine is going to be minus sine. So this means that we're having negative sine of theta. What about if we had the function f of x is equal to cosine of x, and we wanted to figure out what is the 27th derivative of, the 27th derivative of this function? Well, what we're going to do is first we'll take the first derivative. So we have f prime of x, and this is going to be equal to negative sine x. So we have negative sine x. We'll take the second derivative. So we'll take the derivative of negative sine x, which would be negative cosine x. We'll take the third derivative of x. So we take the negative derivative of cosine x is negative sine x. Negative negative will give us sine of x. And then we'll take the fourth derivative of x, and this is going to give us cosine of x. So now we're back at the beginning. So pretty much what's happening is every 4 derivatives, we are going back and forth from cosine x, negative sine x, to negative cosine x, to positive sine x, to positive cosine x. So if we were to repeat this, we basically are going to say, okay, well, if we want to take 27 and we want to figure out how many times we can divide this by 4, so we're going to look at how many ways can 4 go into 27, which is going to be 6. So 6 times 4 is going to be 24, which would give us a remainder of 3, meaning that it is going to be equivalent to the third derivative. So f27 is equivalent to the third derivative of f of x, which in this case would be sine of x. So the 27th derivative of cosine x would be sine of x. Now, the last thing I want to do in this lesson is I want to go back to our function that we looked at in the prior section. So we had f of x was equal to x cubed minus x. And what we did is we found the derivative, we found the second derivative, we found the third derivative, and we found the fourth derivative. So I just want to quickly show how fast we can do this now and to make sure that it fits with what we got previously. So when I take the first derivative, so f prime of x, I am taking the derivative, so technically I'm taking the derivative of x cubed minus x, which is equal to the derivative, so d dx x cubed minus d dx x. Well, using our power rule, this is going to be 3x squared, and this d dx x is just going to be equal to 1, so minus 1. So that matches what we got. Now we're going to take the second derivative. And this is going to be equal to, I'm going to bring down a 2, so it's going to be 6x. 2 minus 1 is going to be 1. This 1 is going to go to 0, 6x. Now I'm going to take the third derivative. So this is going to be d dx 6x. I'm going to pull that constant out. This is going to be equal to 6 d dx x. We just talked about the fact this is going to be equal to 1. So this is going to be 6. And then for my fourth derivative, we are taking the derivative of 6, which the derivative of a constant is always equal to 0. So if you look at these terms, we got the exact same thing. And you see how much faster it is using this power rule. And in fact, and also the constant rule and stuff like that. But in fact, I'm writing down more steps than you really need to even solve this, right? If I have x cubed minus x, I just need to pull out 3, so 3x squared minus 1. Next one, I have the derivative of 3x squared minus 1. That becomes 6x, and then the other term goes away. Take the derivative of 6x. I know x to the 1 is just going to be equal to 0 when I take the derivative, so it's going to be, equal to 1 when I take the derivative, so it's going to be 6, and then derivative of constant is 0. So we went from basically a full board of calculations to figure out these 4 answers, or we could pretty much do it in our head, and it takes seconds. And this is sort of the power of these derivative rules that we're using. Now remember, even though we're using these rules and we're very quickly figuring out the derivative of some power or a constant times a function, things like that, but what you're fundamentally doing underneath the hood is you're using that definition of a derivative that we talked about earlier. The difference is, though, now is we're not showing all the individual steps because this has been rigorously proven to be true. So we're basically using a shortcut now to solve these very quickly. Hello, everyone. In today's lesson, we're going to be going over the product and the quotient rule for solving derivatives. So let's start with a couple rules. The first is our product rule. So our product rule says that if we have the derivative d dx of two functions multiplied by each other, f of x and g of x, let's say, then this is going to be equal to f of x times the derivative with respect to x d dx on the function g of x plus the function g of x times the derivative d dx on the function f of x. Or you could think of this as g f prime plus f g prime. Now you may have noticed that I flipped these around, right? So if you actually looked at the way I wrote it originally, it was f g prime plus g f prime. I actually switched this because these are associative and they're commutative, so it really doesn't matter what order we put them in. But the reason I did this is because as we go into our quotient rule, which states that if we are taking the derivative d dx on two functions f of x divided by g of x, in this case, the order is going to matter. And this is going to be equal to g of x d dx of the function f of x minus f of x d dx g of x. And then this entire thing is divided by g of x squared. So you can think of this one as g f prime minus f g prime divided by g squared. And this is the reason why I wrote our product rule this way, because that way, if you remember this one, all you have to remember for the quotient rule is that instead of plus, it's minus and divide by g squared. So what this means is for the product rule, we're going to take our g of x and we're going to leave it alone. And then we're going to multiply that by the derivative of f of x. And then we're going to add that to leave our f function alone and multiply that by the derivative of g of x. for our quotient rule, we're going to take our g function, leave it alone, and multiply that by the derivative of our f function, minus leave our f function alone, and multiply that by the derivative of our g of x, and then divide the entire thing by g of x squared. Now, we also have a couple more things we want to cover in this section, which is some more trig functions. So we already talked about two of them, which are if we have d dx of sine of x, this is just going to be equal to cosine of x. And if we have the derivative d dx of cosine of x, this is going to be equal to minus sine of x. Now we're going to add to this and say that if we have our function d dx on tangent of x, this is going to be equal to secant square of x. And if we have the derivative d dx on cosecant of x, this is going to be equal to minus cosecant of x times the cotangent of x. If we have the derivative d dx for the function secant of x, this is going to be equal to secant of x tangent of x. And then finally, if we have the derivative d dx of cotangent of x, this is going to be equal to minus cosecant square of x. Now, you can actually solve these using our definition of a derivative, right? We've talked about using this. It works for everything, but these rules will also be true when you have these. And a lot of times the way you want to solve this is you want to use things like the property that if I have the tangent of x, this is going to be equal to having sine of x divided by cosine of x. And then from there, a lot of times this is going to lead to cancellation or changing this into different things like cosecant. Or for example, if I have tangent, sine over cosine, cotangent would be cosine over sine. So in this case, once you get it in terms of sines and cosines, when you do a bunch of cancellation and moving things around, you can actually figure out these doing it that way. So now we're going to do some examples. Now, if you notice in the side here, I put the product rule and the quotient rule so we can reference them while we're doing these problems. So the first one says that we want to differentiate y equals x squared sine of x. So if you look at this, this is going to be our product rule, right? This x squared is going to be our f, and this sine of x is going to be our g. So looking at our product rule, we have g f prime plus f g prime. So the first one, we're going to leave our g alone. That's our sine of x. So the derivative of this, y prime, is going to be sine of x times. Now we want to take the derivative of our f of x, which is x squared. So we use our power rule. X squared becomes 2x. The square is 2 minus 1 with a power, so that gives us x to the 1. So this becomes 2x plus. Now for our second term, we have f g primes. We want to leave our f alone. So this is going to be x squared. And then we want to take the derivative of our g of x, which is going to be sine of x. We take the derivative of that, we get cosine of x. And then, of course, just rewriting this, just to have the x's in the front, this is going to be 2x sine of x plus x squared cosine of x. For my next example, I want to take the function f of t, which is equal to the square root of t times a plus bt. And I want to differentiate this. Now, a couple things before we do this. First of all, is that I'm actually going to change this square root of t into t to the 1/2. This will make it easier when we're actually taking the derivatives. Second thing I want to mention is that this a and b are just constants. So this is going to be t to the 1/2 a plus bt. So this t to the 1/2, this is going to be our f. This a plus bt, that's going to be our g. And because we're multiplying them by each other, this is going to again be our product rule. So when we take the derivative of this, f prime of t, this is going to be equal to, well, first we leave g alone, so this is going to be a plus bt. And then we multiply by our f function. So t to the 1/2, we bring down the 1/2. And then we have t to the 1/2, so 1/2 minus 1, which same thing as saying 2 over 2. So 1/2 minus 2 over 2 gives us t to the negative 1/2. Plus, Now, for our second term, we leave f alone, so this is going to be t to the 1/2. And then we're going to multiply this by this g, derivative of g. So a is a constant, so the derivative of a is going to be 0 plus derivative of bt. Well, you can think of t as t to the 1. You bring the 1 down, it becomes t to the 0. T to the 0 is equal to 1, so this just means it's going to be times b. Now, just to eliminate some confusion, so I don't confuse this as a 6, I'm going to write this as a capital B from now on, just so that I don't accidentally end up multiplying by 6, because I've done this in the past. Okay, so now I'm going to simplify this sum. So the first thing I'm going to do is I'm going to rewrite this as a plus bt, and then I have 1 over 2, so this is going to be over 2, and then t to the negative 1/2. T to the negative 1/2, remember the negative power makes it go to the denominator, so this would be over t to the 1/2. And then I'm just going to put it back in terms of square roots just to get it back into its original form. So this is going to be square root of t in the bottom, because it's 1/2 means it's a square root. And then this is going to be plus b square root of t over 1. Now, in order to simplify this, first thing I need to do is I need to get both of these fractions in terms of the same denominator. So I'm going to take this one and I'm going to multiply by 2 square root of t over 2 square root of t, which I can do because this is 2 square root of t over 2 square root of t, same thing as 1, which means I'm not really changing this. So if I were to then solve for this, this is going to end up being a plus bt plus, and then we have 2b square root of t times square root of t gives us t. And then this is all divided by, because we got 2 square root of t over 2 square root of t. So this is going to be 2 square root of t. And then finally, what I'm going to do is I'm going to combine these two terms, right? I've got bt plus 2bt. So this is the same thing as saying a plus 3bt divided by 2 square root of t. What about if we have a problem like we've had before, where we have what the outcomes are, but we don't know what the actual functions are? So in this case, we have that h of x is equal to x times g of x. We have that g of 3 is equal to 5. We have g prime of 3 is equal to 2. And we want to figure out what is h prime of 3. So the fact that h of x is equal to x times g of x, right? X in this case is our f, g of x is our g. So whenever we're solving for this, we know that we want to take g f prime. So in this case, we're going to take g of x, which in this case is for 3, times the derivative of x, which is going to be d dx x plus. Now we're going to leave f alone, so this is going to be x times the derivative d dx of g of x, which in this case is g of 3. The derivative of d dx of x is just going to be, if you could think of this as x to the 1, this is going to be the same thing as multiplying by 1. So g of 3 is going to be equal to 5 times 1 plus, now for x, because we're not changing it, we're just plugging in this 3, right? Because this is h prime of x, x is equal to 3, so this is going to be 3 times the derivative of g at 3, which is going to be equal to 2. So we're going to have 5 times 3 times 2, which is 6, is going to give us 11. Okay, so we've done some examples with the product rule. Now let's do one with the quotient rule. So we have y is equal to x squared plus x minus 2 divided by x cubed plus 6. And we want to figure out what is the derivative. So we want to figure out what y prime is. So in this case, this top term is my f, this bottom term is my g. So we're going to be using the quotient rule, g f prime minus f g prime divided by g squared. So then plugging that in, our first thing, g, we're going to leave this alone. So this is going to be x cubed plus 6 times. Now we want to take the derivative of our f term, which is going to be x squared plus x minus 2. So we'll take the derivative of that, of course, x squared, right? Because if I take the derivative of x squared plus x minus 2, it's the same thing as taking the derivative of x squared plus the derivative of x minus the derivative of 2. So the derivative of x squared, we're going to use power rule. This is going to be 2x. We take the derivative of x. This is going to be equal to 1. And then, of course, we take the derivative of a constant. Derivative of a constant is always equal to 0. So now we're going to subtract f. So we're going to leave our f alone this time. So this is going to be x squared plus x minus 2 times the derivative of g of x. So we're going to take the derivative now of this. Same thing, I can take the derivative of x cubed plus the derivative of 6. Derivative of x cubed is going to be 3x squared plus the derivative of a constant. Derivative of a constant is equal to 0. So we're just going to be left with 3x squared. And then all of this is divided by g squared, which means that we're going to take this bottom term, x cubed plus 6, and we're going to square the entire thing. So now let's see what we can do to simplify this. So the first thing I'm going to do is I'm going to FOIL out these first two terms. So I have 2x times x cubed. This is going to be 2x to the 4th power. Plus, now we're going to do our outer terms. X cubed times 1 is going to be x cubed. Now we're going to do our inner terms. 6 times 2x is going to give me 12x. And then I'm going to do my last terms. 6 times 1 is going to be plus 1. And then I'm also going to distribute this 3x squared into each of these. Remembering that I'm subtracting this. So whatever I get, I'm going to flip the sign. So I have 3x squared times x squared is going to be minus 3x to the 4th power, right? Because it's 3x to the 4th power. It's positive, but then the minus makes it negative. And the next one is going to be minus 3x cubed. And then the last one is going to be 3x squared times negative 2 gives me negative 6x squared, but then the negative is going to make it positive 6x squared. So plus 6x squared. And this whole thing is still divided by x cubed plus 6 squared. Okay, so let's see if there's any cancellation. So the first thing is that I've got 2x to the 4th and I've got minus 3x to the 4th. So this is going to give me minus x to the 4th power. So I've used this one and I've used this one. Now let's look at our cube terms. We have x cubed, we have minus 3x cubed. This is going to give us minus 2x cubed. And again, we've used this one and this one. Now let's look at our square terms. Well, it looks like the only square term we have is going to be the 6x. So plus 6x squared. Next, we look at our x's. We have plus 12x. And then finally, we have, for our constants, plus 1. And then don't forget our denominator, which is going to be x cubed plus 6 squared. And this is about as simple as we're probably going to be able to make this one. So in this case, this would be our final answer. For my next problem, I want to take the function y is equal to e to the x divided by 1 plus x squared. And I want to find the equation for the tangent line at the point 1/1/2 e. So to find the tangent line, first thing we need to do is we need to figure out what is the derivative. That's going to give us our slope. So to find our derivative, y prime, we're going to use the fact that because this is e to the x divided by 1 plus x squared, we know this is going to be the quotient rule, where e to the x is f, 1 plus x squared is our g. So we're going to have g, we're going to leave g alone, so this is going to be 1 plus x squared times. Now we're going to take the derivative of e to the x. Well, derivative of e to the x is just e to the x. Minus, now we're going to leave f alone, so this is again going to be e to the x. And we're going to multiply this by the derivative of our g term. So derivative of 1, derivative of constant, is equal to 0, plus derivative of x squared is going to be 2x. So this is going to be e to the x times 2x. And then this entire thing is going to be divided by gx squared. So we're going to take 1 plus x squared squared. Now there's two ways you can solve this. Since we want to find it at the point 1/1/2 e, you could plug in your x now, which then would give you y prime of 1 is going to be equal to 1 plus 1 squared is equal to 1 e to the x minus, oh sorry, actually plug in 1 for that too, e to the 1, e to the x, plug in 1 for x, times 2 to the x. So this is going to end up being two e minus 2e over 1 plus, I forgot to put the 1 in here, so this should have been 1 plus 1, or 2 squared, which is equal to 4. So we get 0 over 4. The other way you could do it, going back to this, is whenever we found this, we actually could pull an e out, right? This has an e to the x, this has an e to the x. So we would have that y prime of x is equal to e to the x 1 plus x squared minus 2x over 1 plus x squared squared. Now, if I were to then plug my x equals 1 in now, this is going to become 1 plus 1 minus 2. So this would be e to the x 1 plus 1, which is equal to 2, minus 2 over, again, plug this in, this becomes 4. So 2 minus 2, this term is going to go to 0. We end up with the same thing, 0 over 4. So if you had simplified it first, you would still get the same answer. So now we have what our slope is at x equals 1. Our slope, m, is equal to 0. So now what we need to do is we need to figure out what is the formula for our tangent line. So we're going to plug in x as 1 and y as 1/2 e, and we're going to plug this into our point slope formula, y minus y1 equals m x minus x1. So this would be y minus 1/2 e equals 0 times x minus 1. So of course I'm going to distribute the 0. 0 times x is 0. 0 times negative 1 is 0. So we're going to have y minus 1/2 e equals 0, which is going to give us y equals 1/2 e. So this is the function, or this is the formula equation of our tangent line at x equals 1, y equals 1/2 e. It is just y equals 1/2 e. For our next example, we want to solve the function. We have the function f of x equals 3x squared plus 2 square root of x divided by x. And we want to figure out what is the derivative of this without using our quotient rule. So in order to do this, what I'm actually going to do is I'm going to take my f of x and I'm actually going to change it around a little bit so that, first of all, this is this x square root of x is going to be x to the 1/2. So we're going to have 3x squared plus 2x to the 1/2 divided by x. And then what I'm actually going to do is I'm going to split this into two separate fractions. So this is going to be 3x squared divided by x plus 2x to the 1/2 divided by x. So then this x is going to cancel with one of these x's, leaving me 3x plus. Now, when I have this x here, this is the same thing as, I'm going to rewrite this. So we have 2x to the 1/2 times x to the negative 1, right? Because remember, just a negative 1 just brings it to the denominator. So if I have something in the denominator, in this case x, if I give it a negative power, it's going to take it into the numerator. So if I have two x's with different powers multiplied by each other, you just add them together. So x to the 1/2 times x to the negative 1 is the same thing as x to the 1/2 plus negative 1, so minus 1. I can change this 1 into 2 over 2, so I have x to the 1/2 minus 2/2 leaves me with x to the negative 1/2. So this means that my function is now 3x times, plus 2 times x to the negative 1/2. And now I can actually solve this just using my power rule. So I have 3x, you can think of this as x to the 1. So when I take the derivative of this, using my power rule, 3x just becomes 3 plus, and then if I do my power rule on this, it's going to be, I'm going to bring down a negative 1/2. So I'm going to get minus, so I got the 2 over here, so 2 over 2. And then I'm going to subtract 1 from my power, so this is going to be minus 3 halves. And then 2 over 2 just gives me 1, so I'm left with 3 minus x to the negative 3 halves, which if you remember, the negative is going to put this in the denominator. So I'm going to have 1 over x to the 3 halves. And then rewriting this, I will get that this is equal to 3 minus 1 over x to the 3 halves. The 3 means that it's x cubed, and the 1/2 power means that it is the square root. So this means that my final derivative is 3 minus 1 over the square root of x cubed. Now the reason I actually wanted to show you this example is to show you that sometimes there are a lot of different ways that you could solve this. For example, when we got it into this original form, I could have instead used the quotient rule, right? Saying that this is f, this is g, and I could solve this and I would get the same exact thing. In fact, you know what? Let's try that. So if I take my derivative, f prime of x, this is going to be equal to g, so we're going to leave g alone, that's x, times the derivative of 3x squared, which is going to be 6x, and then plus the derivative of 2x to the 1/2, so bring down the 1/2, this is going to be plus 2 over 2, which would just be 1, and then 1/2 minus 1 is going to give me to the negative 1/2. Minus. Now for my f term, I'm going to leave this alone, so this is going to be 3x squared plus 2x to the 1/2 times, now I'm going to take the derivative of my g term. Derivative of x is just equal to 1. And then I will take my g value, so in this case x, and I will square that. So now, solving for this, what do we do? Well, first things first, I'm going to distribute this x. So this is going to become 6x squared plus x to the negative 1/2 times x. So negative 1/2 plus 1 gives me x to the 1/2. So to the positive 1/2. And then this one, I'm just going to distribute the negative. So minus 3x squared plus 2x to the 1/2 divided by x. Now, of course, I can now divide everything out by this x. So in this case, actually, first thing I'm going to do is I'm going to take this x to the 1/2 and I'm going to bring it over here with this 2x to the 1/2, which should have been negative because I distributed a negative. So we have x to the 1/2 minus 2x to the 1/2 gives me, so this would be 6x squared minus 3x squared. I should actually need to combine those terms too. X to the 1/2 minus 2x to the 1/2 gives me minus x to the 1/2. Still divided by x squared. 6x squared minus 3x squared, so this is going to be 3x squared minus x to the 1/2 divided by x squared. Now, if I were to split this like I did before, this is going to be 3x squared divided by x squared minus x to the 1/2 divided by x squared. So for this one, 3x squared divided by x squared, this is just going to be equal to 3. And then we have x to the 1/2 divided by x squared. So again, I'm going to treat this as x to the negative 2 power. That would be the same thing as saying negative 4 over 2. So 1 over 2 minus 4 over 2 gives me x to the minus 3 over 2, which then, of course, brings us right back to where we were. 3 minus 1 over the square root of x cubed. So just like we got before, using the quotient rule, or in fact rearranging our original function so that we could just use the power rule. For our last example, I have the function f of x, which is equal to secant of x divided by 1 plus tangent of x. So we're still going to be using our quotient rule, where this is going to be our f term, this is going to be our g term, but now we're using some of our trig identities that we looked at earlier. So first things first, leave g alone. So the derivative of this, I'm going to leave my g term alone. This is going to be 1 plus tangent of x times, now I'm going to take my derivative of my f term. This is going to be, so actually let me write this down first. This is going to be d dx secant x. Let me do that so that nobody gets lost. So the next one, I'm going to leave f alone. So this is going to be secant x. And then times the derivative d dx of 1 plus tangent x. And this whole thing is going to be divided by 1 plus tangent of x squared. Okay, so now, actually solving for this, we're going to have 1 plus tangent of x. And now what I need to do is I need to take my derivative of secant of x. This is just going to be equal to secant of x tangent of x. And then minus secant of x times the derivative of 1 plus tangent x. So the derivative of 1, which is a constant, is going to be equal to 0. So we're just taking the derivative of tangent x, which is going to be equal to secant square of x. And then this whole thing is still divided by 1 plus tangent x squared. Okay, so now that I've taken the derivative, let's simplify some. So as always, first thing I'm going to do is I'm going to distribute this to this term here. So we're going to get 1 times secant x tangent x. So we have secant x tangent x plus. Now I'm going to multiply tangent x by secant x tangent x. So this is going to be secant x tangent square of x minus secant x times secant squared of x, which is going to be secant cubed x divided by 1 plus tangent of x squared. So here what we're going to do is we're going to use a trig identity, which is 1 plus tangent square of x is equal to secant square of x. Now, you might think that I'm actually using this to get rid of our denominator, but I'm actually not, because if I were to distribute this, I would have to FOIL it out. It doesn't end up being what we're looking for. So what I'm actually going to do is I'm going to replace this, one of these, the secant squared here, this is secant cubed, by the way, so just be careful, with 1 plus tangent square x. So this is going to give me secant of x, tangent of x, plus secant of x tangent square of x minus secant of x times 1 plus tangent square of x. And again, all of this is still divided by 1 plus tangent of x squared. Now you might have wondered why I did this. Well, it's because now, if you look at this, I have secant here, I have secant here, I have secant here. So if I were to pull secant out, so I have secant x, this is going to be tangent x plus tangent square x minus 1 minus tangent square of x, all divided by 1 plus tangent of x squared. I have tangent square of x minus tangent square of x. So these two are going to cancel with each other. And this is going to leave me then with secant of x times tangent of x minus 1 divided by 1 plus tangent of x squared. And this is about as simple as I can think to make it. There might be other identities you could use. For example, you could try changing secant and tangent into sines and cosines. There might be more cancellation you can do, but honestly, I feel pretty good about this being our final answer. So not only did we take the derivative using the quotient rule, we were able to distribute all the terms, and then using this identity here for secant square x equal to 1 plus tangent square x, we were able to actually cancel some of our terms, giving us a slightly easier trig function at the end to work with. So that is it for our product and quotient rule lesson. I am actually going to do a supplementary lesson where I'm going to prove the product and the quotient rule that they're true using our basic definition of a derivative. So that way you don't have to use the definition of a derivative using your difference quotient every single time. These rules will always be true. So I'm just going to show you these as an example of how this works. So you should be able to find that video. I'll put a link to it in the description below. Other than that, that's it for this lesson. Hello everyone. I want to show you that we can use our quotient rule and product rule that we talked about in our actual lessons. And I'll post the link to those if you want to go back to that and see how we did it. But I wanted to show you that using our difference quotient of our definition of a derivative, that this will be true for all cases. So let's say, for example, that we have some function, capital F of x equals f of x times g of x. So in this case, this is a multiplication of two functions, f of x and g of x. So this would mean that this would be using our product rule. So first thing I'm going to do, if I want to find my derivative of f prime of x using my basic definition of a derivative, I'm going to set this up as the limit as h goes to 0, f of x plus h minus f of x all divided by h. Now, we know what f of x is. It's f of x, lowercase, and times g of x. So we need to figure out what is f of x plus h. In this case, I would plug in x plus h anywhere I have an x in our function. So this is going to be the function f of x plus h times the function g of x plus h. So now plugging this in, this makes our limit, the limit as h goes to 0, f of x plus h times g of x plus h minus f of x times g of x all divided by h. So for the next step, what I'm actually going to do is I'm going to use a trick where I'm going to add and subtract in the same value, right? So if I added in anything, let's say I added in 2x and I subtract 2x, those would cancel out, meaning I haven't actually changed the value of whatever it is that I have here. So this is going to be equal to the limit as h goes to 0. And I'm also going to rearrange things. I'm going to put it in a specific order, and you'll see why in a minute. So we have our first term here, f of x plus h times g of x plus h. And then now I'm going to bring in my first other term, which is going to be minus f of x plus h times g of x. But of course, if I added it in, I also have to subtract it. That way it equals out to 0. So I haven't actually changed what we have here. So this is going to then be plus f of x plus h times g of x. And then, of course, I will just continue on putting my minus f of x, g of x, and then this whole thing is still divided by h. Okay, so you might now wonder, why did I do this? Well, it's actually because if I look at these two terms, I have f of x plus h and f of x plus h. If I look at these two terms, I have g of x and I have g of x. So what I'm going to do is I'm going to pull those out, and this is going to become the limit as h goes to 0, pull out the f of x plus h, times g of x plus h minus g of x. Same thing here. I'm going to pull the g of x out. So this is going to be plus g of x times f of x plus h minus f of x. And this entire thing is still divided by, looks like my marker is dying, so I'm going to switch over to purple. So this whole thing is still divided by h. Now, you may see what I'm starting to do here, because now what we're going to do is, remember our limit laws. If I have the limit of something times something else, that means I can take the limit of the first thing times the limit of the second thing. So this is then going to become the limit as h goes to 0, f of x plus h, times the limit as, don't know why I put that line there, limit as h goes to 0, g of x plus h minus g of x divided by h plus, right? Because think about it this way. If I have a times b over c, I could write this as a over c times b. That's all I did. I just put the h on this term, but it's still, because these two are multiplied, doesn't change anything. Plus the limit as h approaches 0, g of x, times the limit as h approaches 0, f of x plus h minus f of x divided by h. Now looking at this, first of all, if I evaluate this limit here, the limit as h goes to 0, f of x plus h, this means that this h term is going to go to 0, and I'm going to be left with f of x times. Now look at this term right here. Limit as h goes to 0, g of x plus h minus g of x divided by h. This is just our difference quotient giving our definition of a derivative. So this is going to be equal to the derivative of g of x, so g prime x, plus the limit as h goes to 0, g of x, there's no h in it, so this is just g of x, times, again, limit as h goes to 0, f of x plus h minus f of x divided by h. This is just our definition of a limit, so this is going to be, this is just our definition of a derivative. So this is going to be f prime of x. So then rewriting this the way that we were using in the lesson, this is just going to be f g prime plus g f prime, which is our product rule. Now, of course, when I was doing it, I actually wrote it by flipping the two terms, which would be g f prime plus f g prime, and that was just to keep it kind of in the same order that we have when we do our quotient rule. So right there, I've shown though that if I have some function, in this case capital F of x equal to some function f of x times some function g of x, I've actually shown by using our definition of a derivative that this is equal to our product rule, meaning that anytime you have a function in terms of two functions multiplied by each other, this rule will always be true. So now we're going to do our quotient rule. So we have the function, again, capital F of x, and this is going to be equal to lowercase f of x divided by lowercase g of x. And using our definition of a derivative, we're going to have the limit as h goes to 0, f of x plus h minus f of x divided by h. So in this case, f of x is just equal to f of x divided by g of x. F of x plus h, I don't know why I keep doing this, capital F. This is going to be equal to f of x plus h divided by g of x plus h. So now let's figure out what our derivative is. So our derivative, f prime of x, is going to be equal to the limit as h goes to 0, f of x plus h, which we just said is f of x plus h, divided by g of x plus h, minus f of x, which is f of x divided by g of x. And then this entire thing is divided by h. So the first thing I'm going to do is I'm actually going to get both of these in terms of a like base so I can actually work with them. And I'm also going to pull this h up to here, right? Because if you think of this h as h over 1, this means that if I were to do fractional division, this 1 is going to come up to the top. This h is just going to come to this term. So to get a like base, or the same denominator, I need to multiply this one by g of x over g of x. And I need to multiply this one by g of x plus h over g of x plus h. So in this case, this is going to end up being f of x plus h times g of x. I'm actually just going to combine it all together because I'm going to end up putting it together anyway, right? They're going to have the same base, g of x plus h times g of x. This one's going to be g of x times g of x plus h, same thing. So this one is going to be minus f of x, g of x plus h. And then this entire thing is going to be divided by g of x plus h, g of x, and then of course times h. Okay, so now I'm going to use a trick just like I did before. What I'm going to do is I'm going to add and subtract out a term, which will then allow us to rearrange it into the form that we want. So we're going to have the limit as h goes to 0. And then first thing we're going to have is we have our f of x plus h times g of x. And we're going to subtract f of x times g of x, and then plus f of x, g of x, which of course, as I said before, because these two are the same term, plus this minus this, they cancel each other out to 0, so I haven't actually changed what we have on in our limit. And then minus f of x, g of x plus h, and then of course this entire thing is still divided by g of x plus h, g of x times h. Okay, so as before, we're going to see what these have in common. Well, these two both have a g of x. These two both have an f of x. So let's do what we did before. Let's pull those out. So this is going to become the limit as h goes to 0. I'm going to pull g of x out. So g of x times f of x plus h minus f of x. I'll just put this in parentheses so we know it's this g of x is multiplied by both of these. Okay, so next thing, now I'm pulling out f of x. So this is going to be minus, so I pulled out minus f of x. So minus f of x times, so if I pull out minus f of x, this is going to become positive. So this is going to be gx plus h minus g of x. Right, because all that happened is this became negative, this one became positive, and I just put the positive term first. And the whole thing is still divided by g of x plus h, g of x times h. Now I'm going to split it like I did before. So this is going to be equal to the limit as h goes to 0, g of x times the limit as h goes to 0, f of x plus h minus f of x divided by h minus the limit as h goes to 0, f of x times the limit as h goes to 0, g of x plus h minus g of x divided by h, and then this entire thing is divided by the limit as h goes to 0, g of x plus h times the limit as h goes to 0, g of x. So limit as h goes to 0, g of x. Well, g of x has no h in it, so this doesn't get touched. So g of x. The limit as of f of x plus h minus f of x divided by h. This is just going to be your derivative of f of x. So we're going to write this as f prime of x minus derivative of f of x, or sorry, limit of f of x as h goes to 0. There's no h in it, so this is just going to be f of x times limit of g of x plus h minus g of x over h. Again, just the definition of a limit. This is going to be g prime of x. And then finally, divided by the limit as h goes to 0, g of x plus h. That's going to make this h go to 0. So this is just going to be g of x. times the limit as h goes to 0, g of x, which is just g of x. So this would be g of x times g of x, or g of x squared. So if you look at this, this is just our quotient rule, right? Our quotient rule was gf prime minus fg prime divided by g squared. That's exactly what we have here. G of x times f prime of x minus f of x times g prime of x divided by g to the gx squared. So this is just to kind of show you that when we use our definition of a derivative, this is always true. We talked about this. So these rules, though, are also always true. And I've shown you that no matter what my function f of x and g of x are, these will be true, both the product and the quotient rule, as long as g of x is not equal to 0, which would be the case even if we weren't doing the quotient rule, right? Because if we got to this point where we had g of x equals 0, it would be dividing by 0, and this would cause the whole thing to not work. So this restriction would be true whether you're using the definition of a derivative or whether you're using the product or quotient rule. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.